Genetics and the Unsettled Past. 1. A.S. The American geneticist, anthropologist, and television presenter Spencer Wells boldly claims in his 2003 PBS documentary The Journey of Man, the study of genetic variation in people around the globe opens an unparalleled view into the past. One drop of blood or a few cells swabbed from the inside of the cheek, he insists, not only unveils mankind's origins in Africa, but also reveals the pathways along which human beings traveled into Europe, Asia, and North and South America. It is a compelling narrative of the body as a microcosm of the past. And, in another bold move that marries science to business, Wells and others like him have commercialized this vision, successfully translating laboratory insights from population genetics into an international collaborative science endeavor, the Genographic Project, in which individual consumers purchase DNA test kits that yield personal genetic results and scientific data toward the further elucidation of the ultimate human history. Written in our genes. Wells's recent venture is but one instance of the countless ways that this new era of genetic analysis has expanded far beyond the arena of origin stories and popular science over the last few years, connecting individuals and groups to imagined ancestors. These recent developments in genetic analysis have been employed to uncover, not only individual ancestry, but also group heritage. Genetic markers referring to tiny sections where minuscule variations on the chromosomes are evident from person to person, tiny data points standing out against the otherwise vast uniformity across all humanity, have come to be regarded as scientific portals to the past. Analysis of these markers is increasingly employed to investigate and adjudicate issues of social membership and kinship, rewrite history and collective memory, arbitrate legal claims and human rights controversies, and open new thinking about health and well-being. 2. Not surprisingly, these latest applications have attracted much attention, and at times generated intense public controversy. In 2010 alone, the debates and assertions arising over genetic analysis were almost as numerous as the genetic practices themselves. In April, the Havasupai Indians, who reside within the Grand Canyon, won their fight with academic geneticists over the analyses of their members' genes and history, which the tribe had never sanctioned. In May of this same year, Walgreens announced that it was reconsidering its plan to sell Pathway Genomics' do-it-yourself at-home DNA kit that infers genetic predisposition for several diseases after the FDA ordered testing companies to prove the validity of such products. 3. In July, DNA analysis was credited with leading to the arrest of a suspect in the 25-year-old so-called Grim Sleeper serial murders in Los Angeles. In September, as news outlets announced that the genome of an Irish man had been fully sequenced for the first time under the headline "The Irish are different genetically." That same month, a court in Iceland debated the validity of DNA findings regarding the claims of a young Filipino woman that her daughter was the child of deceased chess champion Bobby Fischer. For this diverse array of cases highlights how DNA has become central to the claims and counterclaims of many stakeholders, from university researchers to ethnic communities, from consumers to entrepreneurial companies to district attorneys, and from mothers to citizens of a nation. Coding race. As the Irish genome case suggests, one central element in the new genetics has been the remaking of individual and collective identity and the rethinking of the meaning of race and ethnicity. 5. The implications are not merely rhetorical. As Henry Greeley has noted, with enough data, population geneticists can estimate how closely related different populations of humans are to each other. But genetically based historical information could have modern political implications. 6. As Greeley anticipated, DNA analysis, much sought in order to resolve questions of ancestry, community, and justice, among other matters, has become a potent political touchstone as well as a social, legal, and historical one. Genetics today has become a standard for shaping how we think about our collective past. At the same time, this politics of genetics has real effects in the present, for example, by impinging concretely upon the rights of groups within a nation-state or redefining the very boundaries of kinship and nationality. In addition, these genetic claims can shape how future rights and responsibilities tied to these relationships are articulated. The mere hint that genetic markers are distributed in different frequencies across populations has led some people to quickly treat such variation as a proxy for racial and ethnic differences, lending renewed authority to biological conceptions of human difference and providing fodder for national debates over belonging, self-definition, and political power. 7. Although many scholars have long agreed that race is a social phenomenon rather than a biological fact, these recent developments in DNA analysis have blurred this distinction. 8. In these and many other ways, the rise of this singularly potent science has transformed scholarly and popular opinion about the nature of race. Since the early 20th century, genetics scientists have had a rocky relationship with the politics of race and nationality. The flowering of modern genetics after the rediscovery of Mendel's work on inheritance of traits brought with it bold and specious claims about how biology and heredity defined race and racial possibilities. By the mid-20th century, in response to these overblown claims, most scientists insisted that races in the classic sense do not exist. 9. They regarded the supposedly fundamental human divisions conceived by their 19th century predecessors such as Caucasian, Mongoloid, or Asian, and Negroid as problematic, because these categories were based on superficial differences only. But in recent decades, genetic science has changed its tune. To be sure, many geneticists would insist that in revisiting race they are not endorsing old racial thinking, but only creating more fine-grained statistical groupings of gene frequencies and populations which, by chance and science, overlap considerably with older racial categories. 10. Yet their analyses of genes across human populations have provoked a resurgence in race thinking and fostered efforts, not only to locate race in biology, but also to connect people today to their own scientific ancestors. In these ways, genetics has returned to its own controversial past, using gene-level differences across groups, enormous similarities, and a relative handful of variations across genomes as a template for reconfiguring groups and for building new notions of racial difference for a new era. Given the field's contentious history, it should not surprise us that each new assertion about genetic or biological group identity becomes a collision point, a nexus of often heated discussion about evidence, science, and political authority. Press headlines that readily draw conclusions about ancestry and behavior, intelligence, or drug metabolism suggest that the social conceptualization of race may be losing ground in the era of genetics, or they might be seen as illustrating the point that some scientists never did give up on its biological meaning, as sociologist Jenny Reardon proposed. 11. Furthermore, a number of geneticists and biological anthropologists as well as sociologists and political scientists have begun making bold claims based on variations of seemingly distinctive gene markers across populations, ranging from contentions about racial predisposition to cancer to the genetic transmission of political orientation. 12. Analyzing these flashpoints and tensions over the claims and credibility of genetic science are among this book's central concerns, for they have dramatic implications for the American discourses about race and biological difference, and pose potentially far-reaching implications in media and policy settings. Genetics today has become a novel yet thorny enterprise, a set of laboratory practices packaged as commodities that are undergirded by far-reaching intellectual, scientific, and technical assumptions about human difference. This book seeks to chart the development of how these assumptions about human difference are often bundled, sometimes unwittingly, into diverse genetic endeavors. In some instances, genetics and DNA analysis are being deployed as new technological advances to address old, long-standing questions about identity and history. In other instances, we are witnessing the emergence of new questions and claims about the meaning of human difference and relations of shared or broken history based on the premise that genetics can offer answers and remedies. Our aim is not to specify precisely when genetics provides access to the truth and when it does not. Although our essays have much to say about the credibility of genetic evidence in law, medicine, politics, and consumer culture, we seek primarily to describe and analyze those social contexts and political settings. In so doing, we explore how the authority of genetic evidence about race and history are linked to the social, political, and cultural utility of racialization. As the essays in this volume make clear, genetic science does not exist apart from its context and uses, nor can its claims be fully understood apart from these contexts and uses. What is particularly notable is the way in which the genetic ventures examined in the pages ahead are enacting racial projects, 13 in which race, including whiteness, and also to some extent, ethnicity, is being reconstituted, and in which notions of race and the past offer both liberating possibilities, for example, a feeling of belonging to the nation, release from false imprisonment, the promise of better health, social healing, and also confinement, for example, racial reification and the biological essentialization of the family and groups. Herein lies one paradox of genetics and the unsettled past. In relying upon genetic analysis to resolve historical mysteries or clear the way for restitution and healing, we are at the same time manipulating and transforming already politicized notions of race and the past, and implicitly making claims about the social, political, and personal significance of biological human difference. Throughout this volume we also ask how ancestry testing has transformed our notions of kinship, placing en famille those individuals whose association is based on genetic markers and pushing aside notions of family that are based on social norms, interaction, or cultural codes. To what extent is genetically fashioned genealogy overtaking other, long-practiced ways of rendering the family and, in turn, the community and the nation? At the end of the day, we argue, only a multidisciplinary approach can illuminate this collision of DNA, race, and history, and help us to identify and expose the cultural, ethical, social, and philosophical challenges and possibilities posed by genetics. Understanding and dissecting the implications of DNA in multiple realms is a complex undertaking, for its uses span across the realms of politics, the courtroom, the laboratory, the clinic, and the media. 14. The pages ahead therefore bring together scholars from history, sociology, anthropology, molecular biology, law, medicine, cultural studies, ethnic studies, and other fields to examine the emerging, and often contested, connections among race, genetics, and history. In these chapters, readers find discussions of the historical use of DNA, and claims made about DNA, in biomedicine, in genealogy, in the law, in epidemiology, and in the complex processes of memory, reparation and nation building. These 4 diverse essays also put forward commentaries and critiques of the uses and misuses of genetic race analyses within particular social settings and across cultural and national boundaries. Genes, kinship, and historical revisionism. Bold claims have become commonplace in the selling of genes as historical tools. In his influential best-selling work, The 7 Daughters of Eve, Brian Sykes, the geneticist and founder of the genetic genealogy company Oxford Ancestors, provocatively proposes that the advent of the genetics era may mark the end of historical inquiry as we know it. See Marianne Summers' detailed discussion of Sykes's enterprises in Chapter 13. Within the DNA is written not only our histories as individuals, but the whole history of the human race. With the aid of recent advances in genetic technology, this history is now being revealed. We are at last able to begin to decipher the messages from the past. Our DNA does not fade like an ancient parchment, it does not rust in the ground like the sword of a warrior long dead. It is not eroded by wind or rain, nor reduced to ruin by fire and earthquake. 15. In this volume, we explore whether we have indeed entered a new stage of historical understanding dominated by genetics and bereft of culture as Sykes suggests. If this is true, what are the implications of this new rendering of the past for how we understand race in various domains? Genetics may well be transforming the very way we define history, but it is also clear that the evidence and concepts guiding this genetic/historical revisionism must be examined closely before the nature and limits of that transformation can be fully assessed. All efforts to connect to the past are bound to be fraught with supposition and speculation, and troubled by problems of credibility of evidence. In the annals of history, new evidence and novel methods of analysis come and go, provoking the very type of question of history, revisionism, and memory that are raised by genetic analysis. Of course, what makes the genetic revision of race and history so compelling is its intimate implications for individuals, its widespread marketing and popularity, its close connection to a set of commercial products, and the promise it offers to unlock past mysteries. The new genetic data have quickly produced theories of human difference and kinship, even as they have provoked debate about the nature of the data collection and DNA analysis, about how and whether the resulting genetic evidence truly relates to social categories of identity, and about whether the evidence indeed offers a portal into the past. Despite such uncertainties, the analysis of sequences of genes when compared across large data sets gathered in patchwork fashion around the globe is being used to provide insights about the past and relationships among people in cases where there may be little other connection. 5. In some cases, this analysis comes into conflict with existing knowledge, most notably when geneticists proclaim to Native Americans, for example, that they are not originally American but, like others, merely earlier immigrants from Europe. In the process, DNA analysis is also recreating how we know the past and even how we now define the social world. The opening part, entitled History, Race, and the Genome Era, features 3 essays by Keith Wailoo, Alondra Nelson, and Catherine Lee that describe the stakes and limits of DNA analysis for individuals grappling with the personal questions of race, identity, and the past, for groups and stakeholders in different national settings who use this information in adjudicating conflicts and in pursuit of reconciliation and social justice, and for the fraught political enterprises of nation building. Around ideas of biological difference. Wailoo's essay offers a personal look at the stakes for one individual pondering multiple lineages and historical connections to the past. Nelson's illuminates the stakes for social groups and nations, viewing genetics in the broader politics of group struggles for justice and reconciliation. And Lees explores the implicit role of gender in this genetic turn and its implications for familial and nation-building claims. These essays see these realms, the personal, the social, and the political, as among the most important for understanding the stakes of DNA analysis today. A second part, entitled Decoding the Genomic Age, takes us into the science of genetic analysis, revealing precisely how genetic material is collected and analyzed, turned into detailed claims about race and identity, and how such knowledge is reworked in settings from laboratories to courtrooms and in the new entrepreneurial practices of genetic genealogy. Abram Gabriel provides an academic biologist's perspective, in contrast to that of a commercial biologist, on the advent and limits of genetic evidence about difference, and a critique of the curious rise of personalized genomics companies, with their far-reaching claims about connecting people to their ethnic roots. Scientists' efforts to construct and categorize populations have an extensive history, and Lundy Braun and Evelyn Hammonds offer historical reflection on the long-standing dilemma of racial classification and its challenging implications for gene theories of race today. Peter Chow-White situates the fascination with genetics in the broader context of the technical possibility and cultural allure of manipulating large databases. What emerges here is a portrait of the complexity and contingency of genetic classification, the ways in which these new developments relate to the long history of racial biotypologies, limitations in how DNA scientists make claims about history using specific techniques, from ancestry informative mapping, AIMS, to forensic DNA phenotyping, how geneticists strategically bracket off and answer objections to their claims, how the manipulation of large-scale databases shape these new ideas about identity, and how novel forms of genetic identity are made in the process. Also in this part, the authors ask how we should decode this genomic age, by looking closely at how genetic evidence and racial theories are developed. 6. Interpreted, and manipulated in 3 realms, the courts and policing, the clinic, and the laboratory. In 2 separate essays, legal scholar Jonathan Kahn and anthropologist/ethicist Pamela Sankar examine American legal practice as it merges forensic DNA with race thinking. Sociologists of science Ramya Rajagopalan and Joan Fujimura examine how particular techniques, such as admixture mapping, depend upon social definitions of race which are then reified in the science. Medical anthropologist Sandra Sujin Lee examines the new field of pharmacogenomics, the notion of medicine tailored to individual and group identity, and the political economy of difference upon which the enterprise is founded. A third part, entitled Stories Told in Blood, turns to an analysis of the poignant, if flawed, social narratives about DNA, blood, and racial identity that are woven by genealogists, political actors, and others in the present and used strategically in order to recount the past and lay claims on the present and future. This section describes how DNA is being used to rewrite notions of race, kinship, and nation, and how such genetic renderings are employed in the pursuit of reparations, justice, nation-building, and reconciliation. In a study of genetic genealogy in Quebec, cultural anthropologist Nina Coley-Lavin points to the influence of French-Canadian identity politics on biological renderings of the past. Bioscience scholar Amy Hinterberger relates the unfolding debate over genetic ancestry in Canada to the nation's multicultural policy regarding visible minorities and Aboriginal people. With this broad context in mind, historian of science Marianne Sommer analyzes the limits of anthropological genetics as applied history. Literary scholar Priscilla Wald unravels how these narratives of technological innovation and identity have long been embedded in commercial, colonial, and political claims and interests. In these essays, then, we see how anthropologists, sociologists, historians, and literary scholars track the expanding impact of genetics for how we understand history. What becomes evident is the way in which the past is contested and how the fraught knowledge of genetics is deployed in service of contemporary political and social goals of cultural inclusion, political exclusion, and mediating social relationships. The three final essays in this part add further richness to our understanding of the racially tinged claims, counterclaims, and stakes at the heart of these kinship genetics history disputes. Jennifer Hamilton, an anthropologist and legal studies scholar, explores genetic ancestry tracing and the legal status of the genetic ancestor in the context of recent court cases. Sociologist Michelle M. Jacob examines the use, politics, and limits of genetic analysis in Native American claims regarding land, belonging, and identity. Turning to post-apartheid South Africa, historian Jay Aronson illuminates the forensic DNA profiling of the remains of disappeared black political activists from the apartheid era as part of the politics of reconciliation and repair in that fraught national context. Here, as throughout the volume, we examine the political, scientific, and social implications of calling upon genetic analysis, in Quebec, the United States, South Africa, England, and elsewhere, to perform a kind of racially charged cultural work to 7. Repair and recast the past, to settle claims, to establish the parameters of kinship, belonging, and national identity, to validate proper and rightful claims, and to reshape identity in the present and possibly the future. Any study of genetic analyse's multiple implications for race and history demands a wide methodological and geographic sweep, multiple voices, and diverse approaches to science and its meaning. As such, some of the essays in this volume look closely at legalistic reasoning and argumentation in the court, others examine closely the nuances of biological analysis, yet others scrutinize cultural and literary representations of genes and identity, and others explore personal meanings or political speech or sociological dimensions of genetics. The diversity of approaches highlights, in its own fashion, the complex ways in which this enterprise is attempting to rewrite normative views of kinship, identity, memory, ancestral rights, national identity, and social justice. Moving us inside this new enterprise, and also beyond old debates about whether race is biological or social in nature, we emphasize the importance of understanding the expansive social life of DNA, particularly in relation to society's already fraught and complex narratives of race and history. 16 DNA analysis in our time is not merely about predicting a future that is supposedly written in our genes, warning us, for example, about our predisposition to disease. The practice also makes fundamental, if problematic, claims about the present and the distant past, and as such, the claims, credibility, and applications of the genetic sciences must be examined closely and in multiple venues. It would be a mistake for those involved with this enterprise at the clinical, legal, or scientific level to ignore these ethical, legal, and epistemological questions swirling around the field. Yet in the concluding part, entitled The Unsettled Past, sociologist Rhianne Frank examines the disturbing tendency of genetics advocates and entrepreneurs to mischaracterize critiques as stemming from ignorance of the enterprise, fear of the truth, or political correctness. The scientific and social challenge, however, is not so simple. As a final essay by Keith Wailoo, Alondra Nelson, and Catherine Lee makes clear, there are questions of evidence and credibility that sit at the heart of genetic claims about history and race, and precisely because of their sweeping implications in politics, law, and society, they must be investigated carefully. With the maturity, commercialization, and rapid expansion of the genetic sciences, particularly into the realm of the so-called racial past, the time is long behind us when geneticists could ignore the cultural world in which their work is applied or ignore the influence of cultural politics on their science. As we see it, the past is one of the principal arenas where this new story of genetic knowledge is being told and where genetic authority is being developed. The essays that follow, then, take us into the center of this conflicted terrain to reveal how historical ideas are refashioned and unsettled through the lens of DNA, to see how genetic claims about race and difference are concocted, and to observe how the distant, otherwise unreachable past has become the site for debate and conflict in the present. From this vantage point, we can observe that the collision of DNA, race, and history is as 8. Much about remapping the unsettled past as it is about shaping the unsettled present and imagining the future stretching out before us. Part 1. History, Race, and the Genome Era. 1. Who am I? 13. A fundamental conundrum at the heart of the new genetics is the question, who am I? Despite what we may believe about ourselves based on our family lore, our photographs, our documented past, or the recollections and memorabilia of our ancestors, genetics makes possible bold claims about self and family that may be at odds with these long relied upon artifacts of identity. When seeking historical guidance as to who we are, we can look backward in multiple ways: the matrilineal line, the patrilineal line, along which names are often, but not always, transferred, some combination of family lines, the mother's father's family line, for example, or in ways totally outside the biological family. Genetic science has emerged from the laboratory and clinic in recent years to add new complexity to this already complex process, and to revise our self-knowledge. No longer promising only that new breakthroughs can cure diseases and save lives, genetic technologies have entered the courtroom, the genealogy business, and popular culture, posing profound challenges to older ways of knowing ourselves. One for Americans like me, who look back across an ocean for links to ancestry and the past and who pine for answers about heritage. The possibilities inherent in the new genetics have been exciting. With a cheek swab, $1,000 or less, and a sophisticated analysis, comparing my genes to those in the company's database, which have been gathered from several populations around the world, the mystery of my roots can be unlocked. Over the past decade or so, popular media, for example, multiple covers of Time magazine have suggested that DNA's insights are far-reaching. DNA, some speculate, may define our religiosity and our compulsion to seek a higher power. Infidelity, too, may be in our genes. An I.Q gene just might explain our intellectual capacity, an A gene might explain our sexual orientation. To whatever I believed about myself, my behaviors and predilections or other features of who I am can be opened via genetic analysis. Or, so we are relentlessly told. Spencer Wells's 2002 National Geographic documentary, Journey of Man, A Genetic Odyssey, begins with an audacious assertion that the blood coursing through my veins is the greatest history book ever written. Such narratives of genetic insight and omniscience have taken a new turn with the rise of genetic genealogy, now also claiming to reopen one's past and to divulge new realities about my family heritage or about the true lineage of a community. The argument at the heart of this captivating made-for-TV drama was simple and shocking, that none of us can truly know who we are without genetic analysis. We might speculate and dream, but the blood and genes would reveal the truth. The power of Wells's program stems from skillfully borrowed science fiction tropes, in this case, a merging of the time machine/time travel theme of H.G. Wells, no relation, with the marvelous 1966 Into the Body motif of the film Fantastic Voyage, in which a miniaturized team of scientists venture into a man's body in order to destroy a blood clot and save his life. As Spencer Wells travels the world, collecting blood and comparing its patterns to the vast database of already collected samples, he stages a new fantastic voyage and odyssey, not only into the body, but back in time, weaving a compelling set of stories about how each of us is connected to one another, how we all have migrated out of Africa, and yet how we have come to be so different today. Before geneticists began to visit the past in this fashion, each of us had well-established and complex, often conflicted, ways of knowing ourselves, of pointing to a past, and of situating ourselves in the present. The fierceness with which we hold on to these older beliefs about ourselves explains, in part, the skepticism that confronts genetic revisionists. In what follows, my argument is simple: rather than seeing a fundamental tension between genetic knowledge and other non-genetic ways of answering the question "Who am I?", there is rather a curious way in which genetic knowledge gains plausibility, not through any inherent power of science, but by reinforcing already existing cultural and political forms of imagining self and the past in films, popular media, public commemoration, family lore, nationalistic display, and so on. Yet, all efforts to connect to the past are bound to be speculative, fraught with supposition, and troubled by problems of evidence. Indeed, selective editing and interpretation is just as prevalent in the fashioning of historical identity using genetic analysis as it is in the use of other evidence, from family photos to genealogical archives. To put it another way, whatever the data we draw upon to answer the question "Who am I?", whether photographs, family trees, birth certificates, or genetic analysis, we engage in a willful paring down of multiple lines of descent, choosing between mothers and fathers in crafting the story of oneself. Genetic analysis, then, like other forms of historical memory, is as much about making meaning in the present as it is about the past. Hence it is as deeply mired in the politics of identity as are these other forms. Let me offer a personal case in point on the complexities surrounding who I am. Since I was 8 years old, my identity has been that of a migrant and immigrant from South America, and, by 16, a naturalized American citizen. 14. Despite appearing to be phenotypically and culturally African American, the fact of my coming into this identity has been something I know about myself, but something that is not obvious to most people. Where I emigrated from is less relevant here than the fact that it was to the United States that I emigrated. My coming to America immigration narrative still figures in the stories I choose to tell my children about who I am. Because of my age when this journey took place, the transition to America was traumatic and memorable, more so than if I had been a 5 or 2-year-old with few vibrant recollections. I can still recall 40 years later the way my accent, even though I was an English speaker, marked me off in elementary classes. I can recall having to explain where it was that I had arrived from. Even as time passed and I learned to speak like an American, merging different intonations from my New York City surroundings, I knew I was from somewhere else even if others did not or chose to forget. But at some point, people ceased asking, because I had learned a new way of talking. My parents, by contrast, still retain the old world lingo, marking them distinctly as from somewhere else. For many new Americans who come from somewhere else, that old place is marked by one's parents' ways of speaking, by one's memories, and by one's family. Like many Americans, I have relatives who remain back home, linking me to one version of who I am. For me, this form of identity is still powerful and resonant, strong enough for me to want to pass the knowledge on to my children and to keep it alive, so that they know where they are from. Before genetics and even after the rise of genetic genealogy, this remains one of the powerful ways in which I know, perform, and understand who I am. Geneticists might argue that this is a fable, a myth I tell myself because, in truth, my people were only passing through South America on our way to the United States. In the ultimate truth of genetics, no one can truly, historically be from South America because South Americans, even indigenous people, are migrants and New World beings. In history as told through genetic analysis, there must be a deeper historical story. Against this backdrop, the language of genetics makes a bold claim that this knowledge that I have carried for decades about who I am, could be richer and deeper. It could also be plain wrong. Why stop in the old country? Why not go further back or travel in different directions to build a more expansive sense of myself, especially by reflecting on ancestors I have never met and who lived thousands of years ago? Genetic analysis promises to take me back even further. How should one think of this option? And are these opportunities offered by genetic genealogy truly radical departures from the pathways previously available to me? My strong sense is that the difference is not as great as one might think. Indeed, the genetic options available to us are filled with all of the same interpretive complexities associated with the conventional sources, the photographs, family lore, and documents that we commonly use to decide who we are. As it happens, all ways of answering the question, "Who am I?" contain false narratives based on incomplete samples, and they are false in surprisingly consistent ways. 15. Starting points and stopping points. When I am asked where I'm from, first I pause to decode what the questioner is asking and to decide where to begin. Does he mean where was I born? Where I grew up? Or does the questioner mean the name of the country, the state, or the region of my birth and early years? How specific should I be? I usually choose to speak about the country of my birth, a small country with a British colonial past and a diverse population defined by the in-migration of South Asians, Africans, and Europeans during the century-plus of British imperial rule. Based on what I know about my grandparents and great-grandparents, I can point to an obvious African heritage. I also point to a South Asian ancestry which, although a small percentage of my family tree, is still attached to me by way of my name privileging my patrilineal descent, as is the custom where I come from. Usually, I skip the details unless asked for them and point to the country of my birth. Doing so appeals to my sense of self, it feels right in most situations. Yet, I know that I have relatives, on one side, who make different choices, pointing for example more insistently to South Asia. I have always believed that the important feature of the country of my birth is that it provides these multiple avenues for anyone confronted with the question, "Who are you?" By contrast, what are the starting points and stopping points of genetic analysis? In order to place myself in the most distant past, the world of genetic genealogy must create that past. It is a past largely defined by genetic material gathered from contemporary individuals around the globe, material contained in vast archives and databases against which snips and sections of any particular person's genes can be compared. As Peter Chow-White explains in another essay in this volume, these data sources, composed by each company or compiler from populations they have selected as representative genetic populations, have become a biomedical and informational paradigm around which new ideas of race and identity are generated. Since the human genomes in these databases, each genome with 3,000,000,000 base pairs, spread across our 23 chromosomes, are 99.9% similar to one another, the starting point of genetic differences analysis is the 0.1%, or 3 million base pairs, where the variations and differences are notable. In most studies, as in one 2004 report in Nature Genetics, an even smaller selection of the 0.1% provides the raw material for locating the sources of our differences. Analyzing just over 100 selected markers in small population samples from sub-Saharan Africa, Western Europe, and East Asia, the authors, a collaboration between a genetics department, a pediatrics unit, and a pharmaceutical company, observed that many studies confirmed that there is a relationship between patterns of genetic variation and geographical ancestry, with a high degree of accuracy and reliability. Using a relatively modest number of multi-locus genotypes, individuals can indeed be allocated to groups that represent broad geographical regions. 3. The power to situate individuals in the past and, in particular, places, based on genes, however, was more limited for certain people and regions. 16. Because of the data itself and because of the complexities of certain populations. As the authors observed, for example, the sampling of individuals from many parts of the world, such as sub-Saharan Africa, India, North and South America, has been extremely limited, even though genetic diversity in some of these regions, such as Africa or India, seems to be higher than in many parts of the world. This very diversity of population raises a set of conceptual problems at the heart of the new genetics/ancestry business. What sources of data are best equipped to link us to the past we seek to create, what populations exist in the genetic databases and how does this shape what past will be found, and if we are all from Africa originally, as genetic genealogy insists, then what should be the endpoint of my quest for an ancestral home? As most historians know, these questions about sources and limitations of evidence are not specific to genetic data, rather, they are inherent to the use of any data linking past to present identity. Choosing a lineage. When I speak about who I am, I have the option of choosing among a range of lineages. I can speak about my mother's side of the family or my father's. Beyond that, I can recall the story of my father's father life as an East Indian child of immigrants to the South American continent, or I can speak of my father's mother's mixture of African and Native American roots, or I can point to my mother's own 4 grandparents all with their own cultural lineages. I have physical markers on my own body linking me, in highly selective ways, to each of these lines. My skin color links presumably to one line. An inherited oddity on the little fingers of my hands is clearly inherited from my mother's mother and has been passed to my daughter, and so on. One cannot, then, speak of a single ancestral lineage but of many lineages, 4 grandparents, 8 great-grandparents, 16 for the next generation, and 32 after that. The lineage chart is a tree pointing back in multiple directions, ever expanding into the past and comprising the individual in the present. Choosing which one of these lineages to speak about is often a situationally shaped social act. Genetic testing offers specific yet highly limited entry into this complex past. As the authors of the 2004 Nature Genetics article noted, much of the genetic data available on many populations is limited to genotypes of the mitochondrial genome and the non-recombining portion of the Y chromosome. For the first type of genetic data points backward along one line, the paternal or father's 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 line, offering insight into that portion of the genome passed down along that hereditary pathway. The second type of genetic data points backward along another line, the mother's 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 line, offering insight into that portion, and analysis of its frequency elsewhere in the world. These two types of testing provide one way of situating oneself in the past but only if one is concerned about the matrilineal past or the patrilineal past. In my own family, the collective memory, evidence, and lore point patrilineally to India, whence my surname, and 17. Matrilineally to somewhere in England or Europe, owing to my mother's 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 place of origin. Ironically, these two forms of testing would not place me where the bulk of my own family history and phenotypic appearance would place me, a self-identified first-generation African American in Africa. To boil down my complex DNA another way, a third type of analysis might be useful. Called Ancestry Informative Marker, AIM, testing, it offers a general statistical comparison of one's markers with those gathered in company databases from populations around the world. AIM testing, each company has its own database, purports to tell me statistically what percentages of supposedly pure Old World identities I embody. These forms of testing were used in the popular American television show Faces of America, in which Professor Henry Louis Gates Jr., and founder of AfricanDNA.com, has the genome of famous Americans tested before presenting them with a dubious pie chart representing their ethnic makeup. The Mexican-American actress Eva Longoria is told that she is 70% European, 27% Asian, and 3% African, and when she is told that this percentage makes her genetically similar to the Parisian-born American cellist of Chinese parents Yo-Yo Ma, her bemused response, "He's Mexican," captures the impossible tension between genetic claims and personal modes of identification. 5. Genetic analysis raises the same question that I raise for myself: do I privilege my mother's mother's lineage or my father's mother's line, while playing down the significance of other ancestors, in telling the story of who I am? As the essays in Part 1 of this volume illustrate, the high-tech memory making of DNA analysis contains the same kinds of uncertainties one finds in many other forms of historical reconstruction. The true difference is that mitochondrial DNA ancestry and Y chromosome ancestry leave these ambiguities about one's true self unstated and unarticulated. 6. Genetic analysis, as we also learn in chapters ahead, blurs the question of starting points and endpoints of analysis, preventing me from seeing South America clearly and locating that continent as my point of origin, or from understanding the more complex story of who I am, that is, how many still genetically invisible strands of my family dispersed over time from several regions and countries that are as yet unmapped genetically, how this process unfolded in highly specific ways and how these many ancestors combined to make me who I am. Any one of us has multiple pathways for building a strong historical sense of self. Genetic analysis offers its own multiple pathways for self-knowledge. In some ways, the social logic of ancestry is not so different from the logic of genetic ancestry, for both depend on selective data that require us to make deliberate human choices in reconstituting the past. Both also depend upon complicated social machinery that makes the past available to us in the present. Finally, both depend upon assemblages of arbitrary databases, mixed with suppositions and memories. The essays in this volume take us, then, into the world of how genetic knowledge is selectively made. They also allow us to examine the question, how different is this new form of analysis from more conventional ways of knowing who I am? 18. Reconciliation projects. From kinship to justice. Alondra Nelson. Among the many possibilities presented by the decoding of the human genome has been the expansion of the types and availability of genetic analysis. These techniques are now ubiquitous. They are employed in biomedical settings, for instance, to examine an individual's genetic predisposition to disease. They have driven developments in forensic investigation, such as the so-called DNA fingerprinting techniques. These post-genomic transformations have also spurred the conception of a range of goods and services that make genetic technologies broadly available for public consumption. Indeed, these direct-to-consumer (DTC) genetic tests that claim to infer racial and ethnic identity, genealogical affiliation, and health potential are among the most visible manifestations of the genomics era. For example, the pervasiveness of DTC genetic ancestry testing is evident in the media's powerful depictions of the unearthing of personal pasts, ranging from journalist Amy Harmon's Pulitzer Prize-winning articles for the New York Times to Harvard University professor Henry Louis Gates Jr.'s television franchise of celebrity-focused genealogy documentaries. Information derived from genetic science is now widespread at a range of social sites. Through this circulation, the logics of DNA analysis, that is, the centrality of the prism of hereditability, to the privileging of molecular scale, the use of statistical methods and probabilistic algorithms alongside biobanks and genetic databases, and so forth, move across and beyond their characteristic domains of biomedicine and forensic science into practices of self-fashioning, kin-keeping, and family formation, among others. Tracking this broader social transmission of the logics and techniques of genetic science, the social life of DNA, we can apprehend how genetics is increasingly relied upon to answer fundamental questions, not only about human identity, but also about national and political community, social justice, and collective memory. 3. In one particular and striking trend in recent years, genetic information is being applied in what I term reconciliation projects, endeavors aimed at ameliorating the 21. Injurious repercussions of the past. Reconciliation projects are efforts to repair the damage caused by fractious social and political struggles, efforts that are being undertaken in many arenas, including courts of law, laboratories, social justice organizations, and museums. The concept, reconciliation projects, of course connotes the idea of reparative justice that underlies late 20th century truth and reconciliation commissions such as those that took place in post-apartheid South Africa, in post-civil rights era Greensboro, North Carolina, and, in post-junta Argentina of the early 1980s, following the fall of the military authoritarian state that had brutally disappeared its critics. For the purposes of this essay, and with the social life of DNA in mind, the phrase furthermore points to the constitutive role played by genetic analysis in endeavors to "mackie whole what has been smashed," to paraphrase the title of sociologist John Torpey's recent comparative study of reparation politics. 5. Genetics has become a medium through which the unsettled past is reconciled, be it through commemoration of historical events or making expiation for past injury. Extending Torpey's reparation metaphor once more, DNA testing may also be relied upon to make whole both formerly opposed parties or formerly unified ones, rejoining broken ties within a community, nation-state, or diaspora. The information yielded from genetic genealogy testing, such as that conducted by African Ancestry and other companies, has been employed in attempts to reunite individuals, for example, by offering the prospect of membership in both kin groups and national communities. A case in point is the Leon H. Sullivan Foundation, a non-profit organization with roots in the U.S. civil rights movement. This organization endorses the use of genetic ancestry testing and DNA affiliation as a medium of African American involvement in entrepreneurship and philanthropy on the African continent. Employing genetic information in another way, other subjects, citizens, or social groups increasingly engage in DNA testing, not to forge cross-national connections, but in the hope of repairing injury and rectifying injustices committed by states, institutions, or other entities. The Innocence Project, a U.S. initiative dedicated to exonerating wrongfully convicted people through DNA testing and reforming the criminal justice system, is one such example. 6. In Argentina, DNA analysis has been used to examine the remains discovered in mass graves and determine the identities of persons suspected to have been abducted by agents of a repressive 7-year military dictatorship that began in 1976. More recently, now adult children suspected to have been taken from their disappeared mothers and placed in adoptive families are now being compelled by the Argentinian government to undergo genetic testing, whether or not the adoptees desire this information. 7. Genetics is in these ways being put to the use of mending what has been smashed. DNA techniques and genetic evidence are now sought to fill perceived voids, and settle disputes, in many social landscapes, as the essays by Jay Aronson, Jennifer Hamilton, and Michelle Jacobs describe and analyze. Aronson, for example, 22. Directs us to the convergence of DNA and history in the context of post-apartheid South Africa. He essays how forensic DNA profiling is used in order to attend to an issue that could not be fully addressed by the country's Truth and Reconciliation Commission: the more than 2,000 missing and disappeared, primarily black, anti-apartheid activists who were abducted and murdered by agents of the state. Forensic DNA analysis, as in the Argentinian example, is used to perform what we might understand as a social autopsy, with the aim of producing post-mortem information that can help reconcile South African society across the color line by restoring to families and to the nation-state the bodies of activists who gave of their lives in the fight for racial justice and equality. As these and other examples in this volume illustrate, the courtroom has been one critically important realm in which the power of genetic information to validate ancestral claims has been deployed, tested, and challenged. Hamilton's contribution, by contrast, examines how genetic analysis is being used to discover and codify unknown or unacknowledged genealogy with the hope of securing legal recognition and, in turn, rights and recompense. She illustrates this process with a close reading of 2 U.S. legal cases in which genetic ancestry tracing has been used as an evidentiary tool: a suit in which the plaintiffs seek reparations for slavery and a suit filed by the freedmen or Black Indians of Oklahoma, who seek to reaffirm their full tribal membership in Native communities. These suits suggest how the legal construction of what Hamilton describes as the genetic ancestor is strategically exercised by the plaintiffs as a way to configure themselves as legitimate, legally cognizable subjects, who can make claims to rights and benefits under the law. Thus, one tension that sits at the heart of the modern collision of DNA, race, and history is this: the employment of genetic ancestry testing or other forms of DNA analysis does not guarantee resolution of historical controversies or claims. For some members of oppressed groups, genetic science, moreover, may be deemed both an undesirable arbitrator and unreliable narrator of the past. As Jacob argues in her essay about the Kennewick Man controversy from a Native American perspective, genetic-based ideas about ancestry may place at risk the land-based identities of indigenous peoples. For these communities, DNA analysis does not offer the horizon of justice, but is rather a threat to their worldview. It is a medium through which both their homeland and legal status come under assault. A genetic framing of history, ethnicity, and the past in this case presents a barrier to mutual understanding, Jacob's analysis asserts how one Native American group renders its history and limbs, how this same community must necessarily contend with different ways of knowing the past as a facet of socialization and cultural transmission. The selling of direct-to-consumer reconciliation. In order to better understand the relationship of DNA and reconciliation projects, it is instructive to look closely at the role that the company African Ancestry has played in such endeavors in the United States. Given the systematic force of racial slavery, colonialism, and imperialism and the enduring effects of this fracturing, it is unsurprising that efforts toward reunion and repair have also been long-standing in African-descended communities. Late 19th and early 20th century ventures by Martin R. Delaney and Marcus Garvey to return enslaved Africans to the African continent, Queen Mother Audley Moore's slavery reparations activism, and Alex Haley's popularization of root-seeking in the 1970s, among other endeavors, readily come to mind. The historical events that propelled the African diaspora, in ensuing decades, inspired varied social and cultural attempts at reconciliation, most notably, documentation of the slave trade and its impact, and the quest of some African Americans for justice and reparations through DNA testing. Among the most recent, and certainly the most technologically facilitated, of these reconciliation enterprises is the DDC, direct-to-consumer, genetic ancestry testing business and its burgeoning use by diasporic blacks intent on inferring African descent. The use of DDC genetics by blacks in the United States and elsewhere represents a small, but active, segment of the larger commercial genetic genealogy terrain. Established in the last decade, genetic ancestry testing continues to grow in popularity and is now a multimillion-dollar industry. These testing services have a particular attraction for those people of African descent for whom, for multiple reasons, it may be especially difficult to track their family history beyond one or two generations. Since the widely available genetic ancestry testing about a decade ago, it has been increasingly called upon to repair the injury and injustice that some understand to be inherent in the African diaspora. These initiatives are apparent in identity politics and self-fashioning, in how the memory of racial slavery has been institutionalized, and in reparations politics. Genetic analysis has been adopted to cement affiliations among members of a transnational network of blacks, to redeem and restore the contemporary, stigmatized African American family by reuniting it with a past, idyllic African one, to inscribe the official memory of slavery, and to adjudicate historical wounding, among other issues. The line between genetics' role in public memory and its role as a business has become increasingly blurred in these DDC enterprises. The prominence of African diaspora reconciliation projects becomes readily apparent if one tracks the phenomenal trajectory of the genetic ancestry tracing company AfricanaNCEStrae.com and of its co-founder, geneticist Rick Kittles. African Ancestry, Inc., a Washington, D.C. based company, purveys what is arguably the most popular brand of genetic genealogy testing among U.S. blacks. 8. Founded in early 2003 by University of Illinois at Chicago human geneticist Kittles and his business partner Gina Page, African Ancestry matches customers to nation-states and ethnic groups on the African continent. Kittles honed the skills and techniques that would facilitate the formation of his African Ancestry company as a doctoral student in genetics at George Washington University. At this time, 23, he was concurrently working as a junior researcher on the team of scientists tasked with investigating the remains of several hundred free and enslaved blacks found in Lower Manhattan in the 1990s. This site is now the African Burial Ground Memorial of the U.S. National Parks Service. The researchers employed a then relatively novel process, in which DNA from the deceased individuals was compared to a database containing genetic samples from contemporary Africans, with the aim of inferring the ethnic origins of these colonial-era American blacks. Kittles left the team before the project was completed. His decision to convert these research techniques, with partner Page, into a commercial enterprise caused a rift amongst the researchers and also created some public controversy among his fellow scientists. Consumers, however, clamored for the company's services. This commercialization of genetics, a theme taken up in the essays ahead, challenges us to think broadly about the nature, meaning, and circulation of genetic claims. This is how African ancestry, and most other DDC genetic genealogy testing, works. After a root seeker has paid a fee, typically from $99 to $500, depending on the company used and the particular service purchased, the company mails test kits to customers that contain the implements necessary to secure a DNA sample. The customer returns the sample to the company by mail. It is amplified and sequenced, and then compared to African Ancestry's proprietary DNA biobank, the African Lineage Database, ALD, which is said to contain more than 25,000 DNA samples from over 30 countries and 200 ethnic groups on the African continent. After several weeks, a customer will receive a results package. 9 Over the last several years, the services of Kittles and Page's African Ancestry Company have come to play a central role not only in the lives of individual consumers, but also in broader reconciliation projects. Present for some time in the criminal justice context, DNA is now moving more squarely into the courts and engaging genetics with other legal arguments and processes. Recently, genetic genealogy testing migrated to the domain of civil law when results of this kind of analysis was introduced as evidence in a well-known U.S. class action suit for reparations for slavery, Farmer Pa Elman v. Fleet Boston Financial Corp. et.al. 10. This case is discussed by Hamilton in this volume. Here I rehearse some of Hamilton's discussion and draw from my own research in order to locate it within the broader circulation of what I term reconciliation projects and, more particularly, to establish what can be revealed through tracing one genetic ancestry testing company's role in these socio-political endeavors. Acts of reparation. From the 40 acres and a mule promised to emancipated blacks after the Civil War to contemporary reparations social movements, U.S. history is punctuated with instances in which bondsmen and bondswomen and their descendants have endeavored to gain restitution for the forced, unpaid labor of slavery. Despite such efforts, prospects for such recompense have never been 24. Promising. During Reconstruction, few emancipated blacks received either land or livestock. In the mid-20th century, black radical Queen Mother Audley E. Moore, the granddaughter of slaves, made several attempts to secure reparations for blacks. In 1959, she presented to the United Nations a petition that charged that genocide had been perpetrated against Black Americans and demanded reparations in the form of land and economic resources. Moore made a similar request in a 1962 meeting with President John F. Kennedy. In this same year, she also founded the Committee for Reparations for Descendants of U.S. Slaves, an entity that works for social repair and economic restitution. 11 But neither Queen Mother Moore's lobbying nor grassroots organizing resulted in any significant movement toward reparations before her death in the 1990s. More recently, Representative John Conyers has introduced Bill H.R. 40, the Commission to Study Reparation Proposals for African Americans Act, every year since 1989. In more than 20 attempts, the bill has never made it out of committee. Attorney Dedria Farmer Pa Elman was well aware of these fits and starts toward the goal of slavery reparations when she decided to take another tack, moving from legislation and lobbying to litigation. In 2002, she became the lead plaintiff in Farmer Pa Elman v. Fleet Boston, a class action suit coalesced from several individual cases, in which corporations were sued by the descendants of slaves for the return of lost wages and, consequently, lost wealth. In March 2002, Farmer Pa Elman's attorney Edward Fagan, who had successfully obtained a settlement of $2 billion from Swiss banks on behalf of Holocaust victims, filed a complaint and demand for a jury trial in a New York federal court on behalf of his client and all other persons similarly situated, against Fleet Boston Financial Corporation, Aetna, and CSX. 12 The plaintiffs sought a national apology to the descendants of slaves and financial reparations from these corporations in the form of large trust funds that would be used for social welfare programs to improve housing, education, and health care. The case was heard in late 2003 by the United States District Court for the Northern District of Illinois. It was discharged in January 2004, when the court granted the corporate defendant's motion requesting a dismissal of the case. District Judge Charles R. Norgal's decision of dismissal was based on several grounds, though primarily he found the plaintiff's case lacking in the area of the legal doctrine of standing. 13. In his ruling, the judge asserted that the plaintiff class did not have a precise, or even approximate, connection to former slaves, and thus the plaintiffs could not sue for injury as their descendants. Norgal noted that the plaintiffs cannot establish a personal injury sufficient to confer standing by merely alleging some genealogical relationship to African Americans held in slavery over 100, 200, or 300 years ago. 14. With this line of reasoning, the court contested the plaintiff class's claim of hereditary or genetic standing, to use the words of legal scholar Eric J. Miller. 15. Put another way, the court rejected the assumption of a familial relationship between the ancestor victim and the descendant plaintiff. 16. 25. The plaintiffs sought to persuade the court of their hereditary injury. 17. And to counter Judge Norgal's assertion that they merely alleged a genealogical relationship to enslaved men and women with scientific evidence of genetic inheritance. In March of 2004, Farmer Pa Elman and the 7 other plaintiffs filed a second, narrower reparations case against just 3 companies, Fleet Boston, Lloyd's of London, and R.J. Reynolds, that they claimed had aided and abetted the commission of genocide by providing insurance and financing for slavers. In this suit, the plaintiffs responded to the court's argument that they lacked standing to bring the slavery reparations case with genetic genealogy results provided free of charge by African ancestry that linked each of them to an ethnic group and/or nation-state on the continent of Africa. 18. Genetic ancestry test results that associated Farmer Pa Elman with the Mende people of Sierra Leone, another plaintiff in the group to Niger, and a third to the Gambia, among other contemporary locations on the African continent, were submitted as an evidential retort to the standing doctrine. The DNA data, the plaintiffs argued, confirmed their hereditary connection to enslaved Africans brought to the United States and thus was also evidence of their legal legitimacy as aggrieved parties. In March 2005, in a lengthy decision, Judge Norgal dismissed the plaintiff's second case once again primarily on the basis of standing. The judge maintained that the genetic genealogy tests did not sufficiently establish a relationship between deceased slaves and the signatories to the class action suit. He wrote that there may well be no perfect method of determining exactly who is a descendant of a slave and thus a member of the group entitled to receive reparations. Continuing this line of argument, the judge noted the strengths and weaknesses of genetic genealogy as hereditary evidence, compared to other indices of race, ethnicity, kinship, and nationality. Genealogical research often fails to provide significant information about a person's ancestry. The blood, or one drop, test, whereby anyone with any trace of African ancestry is deemed part of the group entitled to receive reparations, fails to differentiate between descendants of U.S. slaves and those of other nationalities with African heritage. Genetic mapping, or DNA testing, is more promising than the above 2 methods, but alone is insufficient to provide a decisive link to a homeland. 19. Invoking both the problem of the incomplete archive and the pernicious logic of hypodescent, Norgal concluded, in keeping with legal doctrine, that the only suitable means to establish a decisive link to a homeland was DNA evidence that could show an uninterrupted, definitive line of ancestry from an exploited former slave to an aggrieved present-day descendant or descendants and simultaneously, a direct line of capital gained, and lost, from accused corporation to expropriated laborers and their offspring. Genetic genealogy test results, the court surmised, neither supplied the plaintiffs with genetic standing nor substantiated their hereditary injury. 26. 27. From genetic kinship to social justice? With reconciliation projects, the insights of genetic science are applied to the discovery or confirmation of ancestry in the hopes of securing social inclusion, including rights and reparation. But to what extent can DNA identification be efficacious for African diasporic and/or racial reconciliation? What might be the consequences of the genetic mediation of African diasporic cultural politics that have historically involved social movement tactics and civil rights organizations? To be sure, the reconciliation projects described in this volume suggest that it may not be possible to settle political controversies and correct historical misdeeds on strictly technical grounds. As Aronson demonstrates, the reconciliation sought by the activists' families may remain elusive despite the turn to genetics, because while biological recognition may be accomplished, the social recognition and historical recognition that are sought and are at stake may remain unattainable. In the case of the reparations suit, there is the problem of genetic standing manifested as a gap between how the court and the plaintiffs respectively interpret relatedness. Tort law requires the succession of capital, matrilineage, and patrilineage to constitute what Hamilton calls legal cognizance. The reparations plaintiffs, on the other hand, introduced genetic genealogy tests into the litigation not only to demonstrate hereditary injury but also to highlight the social death that was inherent to the chattel slavery system. 20. The injury that we're focusing on, Farmer Pa Elman proclaimed in an interview, is the loss of the destruction of our ethnic and national groups. African Americans today do not know who we are. That is a human right, to know who you are. There are now DNA tests available where we can determine the precise ethnic and national groups we come from in Africa, so we're able to trace ourselves back to the slave trade and determine who underwrote those slave trading expeditions, which nations, which companies supplied whatever resources necessary to brutally enslave my ancestors. 21. Farmer Pa Elman and the other plaintiffs believe that they have found in genetic genealogy testing a vehicle of racial repair both within and beyond the courtroom. Yet, as with Aronson's analysis, legal cognizance is not fully achieved, because of the incommensurability between how the civil court, on the one hand, and the plaintiffs, on the other, differently perceive ancestry. This fundamental political and epistemological incommensurability leads one strongly toward the conclusion that social repair may not be attainable by means of genetic analysis. Following this line of reasoning, one could conclude that genetic genealogy testing is of little value as a true medium of reconciliation. However, even if the plaintiffs ultimately lose the reparations litigation, they may gain ground in other ways. Legal scholar James Davey explains, for instance, that the reparations case could be considered a form of legal sparring used by counsel in Farmer Pa Elman v. Fleet Boston in order to gain access to the Supreme Court, where the novel nature of the issue might force a change in judicial attitudes to the doctrine of standing. 22. Davey also offers that the lawsuit is a form of quasi-public litigation. 23. With such an understanding, he continues, although the nature of the litigation remains adversarial, the role of the litigant is therefore, in part, to raise awareness of the issues beyond the confines of the courtroom, in wider social, legal and political fora. 24. In this task, Farmer Pa Elman and her allies will likely succeed. And, more to Davies' point, this litigation in the court of popular opinion will be occurring in the context of the increased ubiquity of DNA, with the legal gatekeepers and the public alike being more exposed to the influence of genetics in numerous aspects of their lives. In 1998, before genetic testing became widely available to the public, this analysis was used to test the hypothesis that President Thomas Jefferson fathered children with an enslaved woman owned by him, Sally Hemings. 25. Historian Annette Gordon-Reed exhaustively researched the controversy over the paternity of bondswoman Hemings's children and the nature of her relationship with the founding father and slave owner Jefferson. 26. Gordon-Reed demonstrates that archival evidence that might typically be used by historians to resolve this issue was ignored or selectively interpreted. What lies at the heart of Gordon-Reed's claim is the problem of fact and evidence, and more specifically, the capacity of certain forms of evidence to prove histories that have been disavowed and denied, in particular, the ultimately unknowable, but certainly provable, details of the peculiar institution. Genetic analysis was deemed capable of resolving centuries-old and deeply entrenched disputes and debates about racial slavery in the United States. But as Mia Bay and others have shown, the results of the genetic testing that established Jefferson's possible paternity of one of Hemings's children has not accomplished reconciliation among his descendants and those of Hemings. 27. Clearly, the issues, controversies, and questions we pose to science about race and the unsettled past can never find resolution in the science itself. A troubling reality for these reconciliation projects is the fact that the purposes to which DNA is put are, in the words of Alvin Weinberg, trans-scientific. 28 For Weinberg, some questions posed to science, typically metaphysical questions or moral ones, cannot be answered or resolved by science. The illegibility of genetic testing as proof of ancestry in civil suits and historiography, despite its use in other courts and for other operations of state power, such as the reunification of immigrant families, as described in work in progress by sociologist Catherine Lee, suggests the trans-scientific. As the essays in this volume demonstrate, the stakes of genetic genealogy testing and of the broader issues of race and history in genetics are largely trans-scientific. The issues, controversies, and mysteries we pose to science about race and the unsettled past may never find resolution. Those instances in which genetic science fails to fully resolve concerns suggests that what is sought is not biogenetic facts as proof of injury or vectors of repair, but rather reconciliation in 28. 29. Its fullest sense. The repair that is sought cannot necessarily be found in genetic science solely. Aronson's work reveals that complexity and ambiguity remained, even after DNA technologies helped to identify deceased activists, because social recognition was not fully accomplished even as biological recognition was. The families of deceased anti-apartheid activists also seek recognition of the sacrifice that their loved ones made for a better South Africa. In this sense, DNA can offer an avenue toward recognition, but cannot stand in for reconciliation, voice, acknowledgement, mourning, forgiveness, and healing. These reconciliation efforts also raise interesting and fraught contradictions. They threaten to reify race in the pursuit of repair for injury. They suggest how justice pursuits can be uneasily intertwined with commercial enterprises. They may substitute genetic data for the just outcomes that are sought, and, indeed, they demonstrate well that facts may not, in and of themselves, secure justice. Reconciliation projects are becoming commonplace. It is by tracking genetic analysis from its conditions of possibility into some of its unexpected applications that the profound and expansive manner in which DNA now shapes social arenas and engenders social norms comes into relief. Even if they lack formal, legal efficacy, the very phenomenon of reconciliation projects tells us something about the proliferation and social utility of genetics beyond the hospital, the science bench and the criminal courtroom, and sheds light upon the social life of DNA. The unspoken significance of gender in constructing kinship, race, and nation. Catherine Lee. In 2007, The New York Times reported the 14-year effort of Isaac Owusu to be reunited with the 4 sons he left behind in Ghana. After becoming a citizen in 2002, Owusu petitioned to have his sons join him in the United States, a right afforded to him as a citizen. When given the opportunity to prove his familial claims by taking a DNA test, Owusu confidently swabbed the inside of his cheek. Test results quickly dashed his hopes for reuniting with his children when government officials notified him that the test could verify paternity for his oldest son only. With these test results, Owusu learned that his deceased wife may have been unfaithful and that his 3 younger sons were not biologically his. The government permitted the admission of his oldest son to the United States, but the other 3 were denied entry. The only recourse Owusu had was to petition for the younger boys' entry as his stepsons. Awaiting the government's decision, he had chosen to withhold the information generated by the DNA test from his sons, explaining that he could not tell them they were fatherless when they were already motherless. Although he called himself their daddy as he wept, genetic tests rendered null and false the effective ties of familial bond between father and son that Owusu unequivocally knew for nearly 2 decades. Swarns 2007. The Owusu case illustrates powerfully the ways in which DNA analysis has become a critically important tool in the definition of family and in the administration of national identity. As the U.S. government considers moving toward the use of DNA testing for proving eligibility for immigration, the practice has the potential to drastically affect the implementation of immigration policy as well as the meaning of family and familial ties. 1. Despite the highly personal nature of his experience with genetic testing, Owusu's claim to retain his role as daddy underscores 4 general points illustrated by essays throughout this volume, which range from individual, to group, to population genetics. First, as the case makes clear, genetic analysis does not always provide unwavering answers to how people are related, and certainly not to how they understand the unspoken significance of gender. 33. Their attachments to one another. Owusu's test results did not nullify his feelings of affection and filial responsibility for the boys who were not his biological sons, although they altered the legal parameters of their relationship. Many of the examples discussed in essays in this volume also attest to this point by showing how the construction of populations or groups used in genetics research obscures the complex and contested ways in which familial ties, racial difference, or ancestry is understood and mobilized. Genetics is thus not only an answer to questions of nation, race, or kinship and belonging, but also a way of answering or even framing questions of how collective ties ought to be formulated, evaluated, and understood for purposes of connecting individuals across time and space. The Owusu case illustrates a second point, that there exists an evolving tension between the supposed absolute nature of genetic tests versus the seemingly contingent nature of personal accounts. Seen through the lens of genetic analysis, the stories we repeatedly tell about ourselves and our origins passed down from one generation to the next are deemed to be less real than the results of a buccal swab test. Of course, nationalism scholars have long shown that such ancestral storytelling is part of the mythologizing of nations, and this continues to be true in the era of genetic analysis. The putative claims of nativists and nationalists and of business entrepreneurs marketing genetic ancestry testing are entrenched in various and overlapping measures of fact and fiction. In replacing personal, familial, or national narratives with DNA analysis, some scientists, government officials, business entrepreneurs, and consumers of ancestral testing have failed to recognize that genes tell stories as well, which are rooted in equivocal and challengeable claims. Third, Owusu's experience highlights how these issues of determining collective ties have become matters of widespread legal, administrative, and social contest, as migration increases and as institutional actors assert greater authority to adjudicate kinship claims. In this context, DNA test results have meaning and are consequential to the extent that they provide an avenue for exercising a right, privilege, or demand, such as family reunification provisions in American immigration policy. As such, genetic testing becomes the terrain upon which issues of inequality and access to scarce or contested resources unfold. A fourth important point that is raised by Owusu's story is the role of gender in molding the boundaries and meanings of family, race, or nation. The issue has been paradoxically absent from discussions of genetics and kinship. Gender, the system of meanings that shape actions and expectations about roles and behavior for men and women, is critical to how notions of family, race, or ethnicity, genetic identity, nation, and state are connected in 4 important ways. First, gender frames the questions that individual family members, government officials, or nationalists may demand that genetics answer, since gender helps structure the relations we have with one another, a larger ethnic or racial group, the nation, or the state. Second, gendered rules govern intimate relations, such as marriage and reproduction, as well as more formal ones related to migration and settlement. Catherine Lee 34. Third, these relations shape the development of physical materials, including populations, genome banks, and even DNA and cell lines, which delineate the boundaries, for example, of legal or legitimate families, racial formation, and the nation-state. These physical materials provide the basis upon which genetic, familial, racial, and national claims are made. Finally, gender molds the symbolic meaning of these materials and the significance of the relations from which they arise. Thus, gendered ideals and claims lie at the heart of how individual family members, nationalists, or geneticists collect, interpret, and narrate such materials for familial, racial, and nationalist questions and claims, although these actors often hide, ignore, or deny these processes. Therefore, gender is crucial for how we construct kinship in its various forms and for how it structures cultural and political projects. In the rest of this chapter I examine the significance of gender in these endeavors. Gendered questions and claims. The absence of Owusu's son's mother in the case raises several questions that both Owusu and the U.S. government believed DNA analysis could answer. Gender shaped the relationship Owusu had with his wife, guiding decisions such as migration and child rearing. Questions about sexuality, reproductive choice, and paternal responsibility arise from gendered expectations about men and women. Because Owusu's boys are motherless, the mother's claim to her sexual history are absent, along with critical bits of information that could ostensibly determine where the kids belong, including to which nation. If the mother were still alive, the issue of whether Owusu would make an effort to bring them to the United States would perhaps be uncertain as well. Without her presence, genetics is used to provide answers to the questions of where the sons belong and to whom. Yet the prism of gender guides how Owusu and the government should interpret facts such as DNA, and this meaning is not self-evident. Instead, the apparent contradiction to the decades-long affection Owusu knew and felt forces a reinterpretation of his familial ties in the absence of the mother. The use of biometric tests for evaluating the veracity of ties is not new, especially in the administration of American immigration policy. For example, American immigration officials at various points throughout the 20th century relied on blood analysis and other biometric measurements for assessing familial claims made by would-be Chinese immigrants as well as other excludable groups of immigrants. Lau 2006. The contest over Chinese immigrants' rightful claims to enter the United States as the biological children, often sons of native-born citizens, included applicants that immigration officials derisively called paper sons in order to highlight the presumably forged nature of documents on which these familial claims were based. This was part of a history of immigrant exclusion, especially of women, which led to great gender imbalances and resulted in the formation of bachelor societies and the denial of Chinese family formation. Unsettled, Lee 2010. This fact illustrates the point that genetics stands as part of a long history of our efforts to determine what is real and true about our relations, and that such efforts intertwine with gendered processes such as immigration. Owusu's motherless children and Chinese paper sons exemplify the gendered ways in which nation-building practices operate. Nationalists and immigration officials seek to answer the question of who truly belongs, not just to the family, but to the nation as well. As such, immigration control and border gatekeeping are about the construction and maintenance of a national identity. The contests over this process include the testing of familial claims and measures that dictate which immigrant women have the right to settle physically and give birth to the next generation. The recent debates over anchor babies born to foreign-born, particularly undocumented, immigrants in the United States and demands for changes to the constitutional protection of birthright citizenship further demonstrate this point. Preston 2010. Immigration opponents see the continued and growing number and permanence of immigrant settlement, especially among Mexican immigrants, as an assault on the American identity. Chavez 2008. The facts of genetics may obfuscate this point by ignoring or overshadowing the political and social processes, which generate the gendered relations and negotiations that form the basis for the resulting physical evidence of settlement and birth. However, gender remains an implicit force, shaping the meaning of the family, race, or nation by underlying the construction, collection, and evaluation of genealogies and genomic data for nation-building purposes. Thinking generally about what kinship means can help illustrate these gendered processes more clearly, which is what I turn to in the next section. Gendered ties and DNA. Family, race, or ethnicity, and nation all have similar structural forms as types of kinship. As the anthropologist David Schneider has argued, there is nothing universal about kinship, 1977, 1980. That is, there is no rule about blood, law, or affection that defines its structure or form. To this extent, we can think about kinship in a more general sense. Thus, drawing from his work, I suggest that we think about the constructs of family, race, or ethnicity, and nation as having two important elements: relationship, ties or connection, and natural substance, blood or genes, both of which become codes for conduct. The natural substance is part of the putative claim-making, which may be touted as genetic or biological. Thus, DNA tests may provide evidentiary proof for the natural substance. However, what relationship results from this and how it should be catalogued and formulated as code for conduct has always been up for debate. That is, the stories family members or nationalists tell about their families or nation are not made self-evident by the physical proof of the natural substance. Furthermore, as I discuss below, this substance arises from, is preserved, and is called into service. The unspoken significance of gender 35. Through particular gendered negotiations between individuals, racial or ethnic groups, or nationalists. DNA testing is often part of an elaborate system aimed at shaping codes of conduct, which can dictate both action and emotion. The action may include things like determining the financial support of a parent for a child or enlistment in the military during times of war. Emotion includes the affective ties that may undergird the rationale or justification for such actions' sense of responsibility, duty, or pride. Thus, what kinship tells us how we're related and what that relationship is made of, the natural substance, is no small matter. They help explain, for example, what makes people love, die, or kill for nations, as Benedict Anderson asked and thoughtfully answered. The nationalist appeal rests in part on the notion that the nation is conceived as a deep, horizontal comradeship, 1991, 7. People conceive of nations as imagined communities, wherein members can conceptualize links to one another across time or generations or space that are preternatural. Thus, the ordering is not just horizontal but vertical as well. The vertical, or generational linkage is structured through the family and the gendered work that both men and women perform, which is something Anderson and other scholars of nationalism have largely ignored, Yuval Davis 1998. Therefore, seeing the connections between family and nation may help us to answer more fully Anderson's question if we recognize the emotive ties and the notions of duty and loyalty that familial bonds can command. And as the Owusu case illustrates, these notions are shaped by gender. We can also see the ways in which DNA testing, in the context of the family, can literally transform the family into a microcosm of the nation. This is most apparent in studies of reproductive policies and the state or in ethnic conflict and sexual violence. For example, in Socscos, Romania, anti-abortion and pro-natal policies were intended to secure the continued birthing of the nation, Kligman 1998. During ethnic conflicts in Bosnia and Croatia in the 1990s or in Rwanda in 1994, raping women of the enemy ethnic group helped to blur the ethno-national claims as well as familial lines as part of genocide or ethnic cleansing programs, Card 1996, Mesnarek 1994. These examples highlight the importance of gender and patriarchal notions of sexuality and reproduction, which helps to obscure the lines of division between family and nation by the work that men and women's bodies perform. For example, they demonstrate how women as biological reproducers serve to mark the physical and symbolic boundaries of the nation, achieved through the symbolic and even physical use of their bodies by men or by the male-dominated state, Antheas and Yuval Davis 1992, Bach 1991, Gall and Kligman 2000, Mostov 1995, Nagel 1998, Yuval Davis 1998. Efforts to regulate women's sexuality are endeavors to achieve purity qua patriline for a racial or ethnic group as well as for the nation. For many nationalists and racists, one equals the other to the extent that a biologically distinct and unique group of people constitutes a given nation or race. Women must be sexually pure in order to preserve the purity of the race or nation. The race or nation is Catherine Lee 36. Pure, because the women are sexually pure. The reasoning is circular. What is significant is the use of discourse to make the symbolic connection seem natural and real. Putative claims about the natural substance that defines the relationship between members of a race or nation, like the family, help to make the discursive and practical link between race and nationality. Genetic testing of DNA, whether mitochondrial maternal DNA, or Y chromosome, male, DNA, or other markers, becomes easily woven into the broader framing of sexuality, reproduction, and gender. Men's and women's bodies do the work of making such links between race and nation possible, thereby coupling the meanings of race and gender. The gendered dimension of nationalist or racist projects that dictate rules for reproduction have consequences for how we interpret demographic and genetic genealogies, including the historical records of marriage and the inheritance of mitochondrial DNA. Thus, for example, anti-miscegenation laws and other eugenics programs determined who could marry whom or whose reproductive capabilities would be rewarded. Positive eugenic programs designed to encourage better breeding, or violently denied, negative eugenics programs such as forced sterilization, Kelv's 1985, Stern 2005. Gendered bodies render gendered DNA. Implicitly understood in studies of family, race, or nation and genetics is the importance of gendered rules for determining kinship's dual code for conduct, relationship and natural substance. Obfuscating gender in genetic ties. As different societies grapple with the questions posed by DNA for race and for historical memory and understanding, the gendered dimensions of this collision have been pulled out of focus as geneticists and nationalists consider the meaning and utility of DNA to frame and construct our stories of national origin and national identity. For example, in Canada and in Great Britain, politicians and scientists often ignore or refute the complex gendered rules that shaped migration, intermixing, and settlement. This is evident in Amy Hinterberger's examination, in this volume, of the development of Canada's support for genomics-based biomedical research and the concomitant ways by which its multicultural policy provides both the rationale and classificatory scheme for how groups are identified and counted. Canada and its supported researchers must address tensions that exist with a multiculturalism policy that celebrates diversity and inclusion and genomics research that presumes homogeneity of its settling founders and exclusion of its native peoples. Similarly, the question of national identity and gender is evident in Nina Coley-Lavin's study of how scientists draw lines that define populations according to racial, ethnic, or ancestral logics that privilege a white, French, colonial history in Quebec, which ignores the complexities of native settlement and intermixing in the demographic reconstruction of genealogies documented by church records and DNA sampling. She shows how scientists use these forms of evidence to represent Quebec's mixed frontier society as biologically pure. In doing so, she demonstrates the affinity between scientists' rendering of population boundaries and Quebec. The unspoken significance of Gender 37. Nationalists' historiographic and political agenda. Both groups set out to narrate stories of origin and the founding of Quebec. Similarly, as Marianne Sommer explains, British scholar Brian Sykes successfully markets genetics testing while drawing upon claims to a Celtic heritage in the British Isles that is colourfully articulated and identified as pure, a claim that denies a complex migratory history. How can we understand such obfuscations, contradictions, and inconsistencies in the government's and scientists' approaches to genetic genealogy in Canada and Great Britain? How do these mythic stories of origin deny marital and other intimate relations that existed in frontier society? Genetic genealogy that ignores complex gendered processes is not unlike other nation-building activities, which rely on the symbolic and physical work of men and women's bodies while denying the existence of such efforts. Yuval Davis 1998. Genetic analysis, in this view, is not simply involved with the erasure of a mixed or multi-ethnic colonial history, but with erasing the gendered dimensions of migration and settlement in earlier times and today as well. Migration is always the expression of gendered norms, roles, and expectations about who should stay or leave, work inside or outside the family, and the valuing of productive labor over reproductive labor. These gendered arrangements determined the formation and settlement of the frontier and continue to shape immigrant communities today. Courtwright 1996, Hirata 1979, Hondanyo Sotelo 1994. The boundary-making and nation-making processes that lie at the heart of genetic stories of origin are the mythic narration of the natural substance, which identifies Canada's or Britain's ethno-national history as pure. This is so despite the contradictions presented by the current identification of either country as multicultural or by diverse new immigration. Even ancient history and genetic proof of a more complex past are ignored. Thus, for example, Sykes can claim that the male lines in Great Britain are mainly Celtic, rendering the existence of Y chromosomes that are Saxon, Dane/Viking, or Norman as minorities, which makes the British Isles stubbornly Celtic. 2006, 287. This literal and figurative gendered narration of genes by Sykes is critical to his customers' link to a pure imagined community. In addition to the male lines, Sykes argues that the British female gene pool is Celtic, suggesting it has remained more or less intact. This sort of claim to an ethnic and sexual purity has long been the foundational rhetoric of nationalists. Moss 1985, Nagel 1998. It is notable and striking, as Priscilla Wald notes in her chapter, how women's bodies do the literal work of narrating the past and foretelling of the future. Giving literary and political dimensions to the story of genes, race, and history, Wald illustrates the expansive possibilities of genetic discourse and links these themes ultimately to the issue of colonization. Women, in her analysis, can be both the silently subjugated actors of such colonization efforts and active resistors. As Joan Nagel has argued in her study of sexuality and nationalist politics, women occupy a distinct, symbolic role in nationalist culture, discourse, and collective action, a role that reflects a masculinist definition of femininity and of Catherine Lee 38. Women's Proper Place in the Nation, Nagel 1998, 252, though women often resist such definitions of themselves. Gendered meanings are fundamental to the ways these notions of family, race, or ethnicity, genetic identity, and the nation are constructed and deployed for cultural and political projects, including nation building. New scientific developments such as genetic analysis are asked to adjudicate questions about kinship ties, belonging, and boundaries, matters that have long vexed citizens, nationalists, racists, and illegitimate sons. DNA analysis is perhaps only the most recent iteration for determining eligible groups for migration and settlement or for verifying paternity. Even more significantly though, it is clear that these scientific developments including DNA analysis and genome banks work through gender, and thereby help to frame how kinship ties and boundaries are identified, analyzed, narrated, and remembered. Part 2. Decoding the Genomic Age. 4. A biologist's perspective on DNA and race in the genomics era. Abram Gabriel. 43. Public awareness of DNA has reached a tipping point. In 2008, New York Times reporter Amy Harmon won a Pulitzer Prize for her series of articles on the implications of DNA and DNA-based technology in modern society. In this same year, revenue from publicly traded biotechnology firms was nearly $90 billion. DNA-based evidence is the gold standard in courts for proving individual identity. DNA data are used with increasing frequency to explore ancestral origins, and are particularly marketed to African Americans and others who may lack records of their specific heritage. Companies have sprung up that will analyze an individual's DNA and provide ongoing reports of possible disease susceptibilities and genetic risk factors. Every month, new gene associations for common diseases are announced in the scientific literature, and news of these discoveries is often reported in the lay press. Both genomics, the study of the structure, evolution, and function of all of the DNA in a cell, and personalized medicine, the concept that diagnostic and therapeutic decisions can be made based on analysis of specific variations in an individual's DNA, have been endorsed and heavily promoted by the pharmaceutical industry, government agencies, and human geneticists. And to protect the public, Congress passed and President George W. Bush signed into law the Genetic Information Non-Discrimination Act of 2008, making it illegal to discriminate against individuals in employment and health insurance based on information obtained from genetic testing. It all sounds pretty exciting. As a molecular biologist, I realize that my field has entered the limelight and that knowledge about DNA is no longer the esoteric province of academic researchers. I take pride in the fact that the study of DNA and genomics has progressed so far so fast, and that the science is being recognized as a powerful tool for fundamental advances in disciplines as disparate as biomedicine and human history. But I feel trepidation, too, that the translational process is moving faster than the science itself, potentially leading to public misconceptions, oversimplifications, and unverifiable claims about the power of these discoveries, with consequent lowering of society's trust in its scientists. In particular, genomics has reinvigorated interest in the thorny topic of the significance of DNA variation and genetic differences between and among human races. Race is a key variable in analyses of American society. Disparities in opportunity, access, income, education, and disease rates by race remain among the most pressing impediments to our becoming a more equitable nation. By examining the genomes of individuals sampled from many world populations, human geneticists have identified DNA sequence differences that can indeed predict continental ancestral origins, referred to as ancestry informative markers. Using this information, companies now offer analyses of individuals' ancestry. Some academicians and commercial interests have used the existence of ancestry informative markers to support the notion that genetic differences in disease predisposition can be linked to ancestral population groups. But it is far from obvious what DNA data reveal about race, particularly since most geneticists acknowledge that human races cannot be objectively defined. Hunt and Magese 2008. The concerns of this essay are how race has become part of our current discussions of genomics and whether it belongs there. At the beginning of the 20th century, genetics and race were conflated through the popular pseudo-scientific social movement of eugenics, with its belief that complex cultural, medical, and socio-economic differences between ethnic groups could be explained by genetic differences. Although the experimentally and statistically based discipline of genetics diverged from the dubious tenets of eugenics after the 1920s, the social and political dimensions of the eugenics agenda had lasting and infamous consequences in the United States, England, and Germany. By the second half of the 20th century, it had become generally accepted, within academic circles, that race cannot be defined as a biological entity, but is subjectively defined by the social and cultural milieu. But in today's scientific and popular literature, race is being equated with ancestral DNA markers and genetic causes are being ascribed to racial differences in disease predisposition. It is troubling that these links may become accepted without recognition of the limitations of the underlying science and without putting an individual's genetic makeup in the context of his or her entire life experience. In this essay, I first discuss how the technical advances of recombinant DNA, beginning in the 1970s, and of genomics, in the last decade, have propelled the field of human genetics forward and resurrected the race connection. I then use the examples of race and genetics in ancestry testing and personalized genomics to illustrate how the public's expectations for and faith in the power of genomics may be misguided. Finally, I consider how the biotechnology industry has influenced the direction of human genetics and how the industry contributes to the public's wishful thinking and often unrealistic beliefs in the omniscience of DNA. 44 Abram Gabriel. Human Genetics and the Recombinant DNA Revolution. The field of genetics began in the early 20th century, when scientists rediscovered Gregor Mendel's 1,865 studies of heredity and began to appreciate the consequences of Charles Darwin's theories of natural selection and evolution. Archibald Garrod reported the first inherited disorder, alkaptonuria, in 1902, and later broadened the concept of inherited biochemical abnormalities with the term inborn errors of metabolism. Garrod and Harris 1963, these reports preceded, by more than 40 years, our realization that genes, the units of inheritance, were physically composed of DNA. But human and medical genetics did not assume its preeminent role in biomedical research for still another 40 years. Watson and Crick's discovery of the double helical structure of DNA in 1953 inaugurated the modern era of molecular biology. The succeeding generation of researchers defined the universality of the rules and mechanisms by which genetic information is transmitted through DNA. Most of this pioneering work used bacteria and their viruses as the experimental model systems. During this period, while scientists purified enzymes and developed techniques for their own lines of research, colleagues across the hall, at scientific meetings, or reading papers in scientific journals, gleaned these technical nuggets and adapted them for their own unrelated areas of interest. By the mid-1970s, biologists from many disciplines realized that this composite technical knowledge, particularly the ability to cut out a segment of DNA from one species, recombine it with a segment of DNA from another species, and express it inside of a bacterium, cloning, could be harnessed to tackle genetic questions about organisms much more complex than bacteria. This collective appreciation was the start of the recombinant DNA revolution. Human genetics may be the area where recombinant DNA has had its greatest impact. Through the 1970s, fundamental genetic discoveries made with model organisms like E. coli and Drosophila outshone the contributions of human genetics. Scientists lacked the technological and experimental tools necessary to advance human genetics. Classical genetics, the study of inheritance and mutations and genetic and biochemical pathways, depends on the investigator's ability to manipulate the biological system through controlled experiments, to mate individuals with various observable traits and analyze their offspring, and to use large samples to derive statistically valid frequencies on which to base theories. While geneticists could routinely manipulate model organisms, these approaches did not apply to humans. Physicians could only follow the transmission of disease traits through families or observe chromosomal changes through a microscope. But observation and description did little to explain how or even which defective gene caused a disease. The recombinant DNA revolution changed all of that. Disease genes are mutant versions of normal genes that cause disease because of their malfunction. Human geneticists realized that, if they could identify specific human disease, a biologist's perspective on DNA and race 45 genes, they could then clone them in bacteria, sequence them, and identify the causative mutations. They could generate large quantities of both normal and mutant protein products of the genes and analyze their differences. All of this might lead to treatments or even cures. Almost certainly, identification of disease genes could be useful for population screening, for genetic counseling of couples, for prenatal diagnosis, and for gaining a better understanding of the pathophysiology associated with a given disease. In 1980, Botstein, White, Skolnick, and Davis published an influential paper describing a technique to identify disease genes, Botstein et al. 1980. The technique was based on the fact that, while all humans are 99.9% identical at the level of DNA sequence, the 0.1% differences are not random, but are inherited from one's parents. These sequence differences, scattered throughout the 6 billion bases of our genomes, are called polymorphisms, with the most common type being single nucleotide polymorphisms, SNPs, pronounced SNPs. SNPs can be found within genes, where they may alter a gene's activity in obvious or subtle ways, or where they may be completely innocuous. Polymorphic versions of the same gene are referred to as alleles. Much more commonly, SNPs are found outside of genes, where they have no obvious effect on how a gene functions. Instead, like fingerprints, SNPs generally are markers of individuality. But unlike fingerprints, the pattern of polymorphisms in an individual's DNA is inherited in equal parts from his or her mother's and father's DNA, and therefore also marks lines of descent. The chromosomes we inherit from our parents have gone through a rough shuffling process, meiotic recombination, during the production of germ cells, that is, sperm and egg. Each germ cell contains exactly one half of the parent's genome, but the composition of that half genome is different in each germ cell, due to the shuffling process. Therefore, two siblings will share only 50% of their parent's DNA. Botstein et al. Reasoned that in large extended multigenerational families that carry an inherited disease, investigators could identify the presence or absence of specific polymorphisms along each chromosome, in each family member. Polymorphisms found more commonly in individuals with the disease and less commonly in family members without the disease may be linked to the disease gene. Even though the linked polymorphism might be hundreds of thousands of bases away from the actual disease gene, this approach narrows the hunt for a disease gene to a particular region of a particular chromosome, which can then be explored in fine detail. Starting in the mid-1980s, teams of human geneticists used Botstein-et-al.'s linkage approach to identify genes that are mutated in dozens of inherited disorders including cystic fibrosis, sickle cell anemia, neurofibromatosis, Duchenne's muscular dystrophy, amyotrophic lateral sclerosis, and familial cancer predisposition syndromes. These early successes had an electrifying effect on the fields of genetics and medicine, stoking the optimism that recombinant techniques could reveal the genetic basis of any disease. 46 Abram Gabriel. While the linkage approach has been remarkably successful in identifying mutant genes in diseases caused by the malfunction of single genes, monogenic disorders, such conditions make up only a small fraction of diseases with a genetic component. Despite valiant efforts, human geneticists have been largely unsuccessful in identifying the genetic basis for common chronic diseases using the linkage approach. Common chronic diseases, for example, depression, schizophrenia, autism, essential hypertension, type 2 diabetes, and asthma, are all multifactorial, and therefore difficult to characterize at a genetic level. Defects in several different genes may result in the same signs and symptoms. Additionally, these diseases are influenced by the environment and may be only partially manifested due to either genetic or environmental modifiers. In fact, we do not understand enough about either the genetic or the environmental components of these disorders to describe them comprehensively at the molecular level. By the late 1980s, geneticists were looking past the linkage approach for finding disease genes and beginning to consider the potential benefits of having the entire human genome sequence at their fingertips. The Human Genome Sequencing Project was carried out in part by an NIH-funded effort and in part by private companies. Chief among the rationales for this massive effort were the abilities to understand human biology, identify disease genes, and develop better predictors of disease and more individualized treatments. At the White House ceremony in June 2000 to publicly announce the completion of the draft version of the human genome, President Bill Clinton, Prime Minister Tony Blair, Celera President J. Craig Venter, and National Human Genome Research Institute Director Francis Collins reiterated 3 points. First, that the sequence would transform medicine and mean better health and a better quality of life for mankind. Second, that the ongoing alliance of governments, universities, and biotechnology companies would be key to the future of genomics. Third, that beyond the medical dimension the sequence information illustrated that the concept of race has no genetic or scientific basis and that the information derived from the sequence must be used ethically and fairly. At that critical moment in the history of genetics, issues of race, commercial interests, and the future of medicine were all in the mix. Since the 2000 announcement, the university company government model has dominated advances in genomics. Genome sequencing centers throughout the world, all previously involved in the Human Genome Sequencing Project, have turned their sequence reading and compiling capacity to the job of determining the genome sequence of a wide array of species. As of this writing, October 2010, complete or draft genome sequences are publicly available for more than 280 eukaryotic species, as well as more than 1,300 different bacterial species. This wealth of gene data has made comparative genomics a field unto itself. Detailed knowledge of genome sequence has also spurred technologic advances and experimental approaches that may finally shed light on disease-causing genes in common multifactorial disorders. DNA microarrays, a relatively straightforward A biologist's perspective on DNA and race 47 and reproducible technique, have become a central tool of genomic research, in part because of the massive amount of genetic information that can be collected on a single slide, Skeena et al. 1995. Using DNA data derived from genome sequencing projects, academic investigators and microarray companies have glued hundreds of thousands of unique segments of DNA, spots, representing known SNPs, to defined locations on single microscope slides. The slides are incubated with a solution containing samples of an individual's DNA, and the strength of DNA binding to each spot corresponds to the presence or absence of that SNP. Thus DNA microarrays can identify genetic variation throughout the genome of any individual. Microarrays have been adapted to disease gene hunting through an approach termed genome-wide association studies, Carlson et al. 2004, Isles 2008, McCarthy et al. 2008. The new method has advantages over the earlier linkage approach. Genome-wide association studies do not use the rare family with generations of an inherited disorder. Instead, DNA from large numbers of people with a particular disease and their matched controls are individually analyzed for the presence or absence of specific SNPs at tens to hundreds of thousands of spots around the genome. Computer algorithms then search for SNPs that show up more frequently in the genome of people with the disease than in the controls, at a statistically significant level. As with family linkage studies, a significant difference between the SNP frequency at a particular locus in cases versus controls suggests that the surrounding genomic region is linked to a potential disease gene. If a locus looks promising, investigators can molecularly dissect it to find the potential disease gene and determine what differs between the alleles in the cases compared to those in the controls. The power of the association method comes from being able to sample large numbers of individuals to gain statistical power and to sample so many loci along each chromosome that the potential regions of interest comprise thousands of bases, rather than the millions of bases in family linkage studies. But a disadvantage of the approach is that, with so many independent loci, false positives, that is, significant differences between cases and controls due to chance or unexpected bias, can far outnumber true positives. Choosing the populations for both the cases and controls must be done very carefully. Differences in SNP frequency might be due to differences in the two sampled populations rather than the disease being studied. These can lead investigators down blind alleys or, conversely, cause them to miss real candidates within the noise of the false positives. Further, the method is geared to finding fairly common variants. While this makes reaching statistical significance easier, such variants rarely show very large differences in disease risk when comparing cases to controls. Geneticist David Goldstein has proposed that variants associated with much greater disease risk are likely to be rare, and therefore unlikely to reach statistical significance in microarray-based association studies, Goldstein 2009. Nevertheless, many human geneticists as well as genomic companies and the National Institute for Human Genome Research are heavily invested in these types of studies. New associations between 48 Abram Gabriel. SNPs in specific chromosomal regions and particular diseases are being reported at an annually increasing rate, though rarely are actual gene associations made. Recently, investigators have begun to reconsider the power of genome-wide association studies. Though hundreds of statistically significant polymorphisms have already been associated with specific diseases, they can only explain a small percentage of the genetic component of these conditions, Goldstein 2009. For common diseases, it is likely that many genes in many genomic and physical environments will sum up to different disease risks and different disease outcomes in individuals. In that context, even 1 million SNPs on a very dense microarray slide will not be sufficient to categorize an individual's risks, since the slide is still only a sampling of the total 6 billion bases in each genome. If large numbers of rare variants are the true genetic basis for common diseases, extremely large numbers of cases and controls will need to be compared, to reach a level of statistical significance. Some believe that only the complete genome sequence of each individual can provide sufficient information to identify which specific variants or combinations of variants predict individual disease risks, responses to therapies, or outcomes. While not currently feasible, this approach has inspired a new human genome technology race, epitomized by the Archon X Prize for Genomics. The $10 million prize will be awarded to the first team that can build a device and use it to sequence 100 human genomes within 10 days or less, with an accuracy of no more than 1 error in every 10,000 bases sequenced, with sequences accurately covering at least 98% of the genome, and at a recurring cost of no more than $10,000 per genome, genomics.xprize.org. As of October 2010, 8 teams, consisting of companies or company-university collaborators, have entered the competition. How has the concept of race entered human genetics? The early period of human genetics had ties to the provocative racial doctrine of eugenics. Over time, anthropologists, geneticists, and other academics came to the consensus that grouping humans into distinct races is subjective and cultural, without objective biological criteria. According to this commonly held view, although modern humans have migrated throughout the globe, they all have the same common ancestors. Between isolated populations, the frequency of different alleles of certain genes will vary, but mixing of populations has gone on throughout human history. Genetic similarities far outweigh differences, and variation among humans is due to the evolutionary forces of mutation, isolation, drift, and natural selection, acting on different populations in different environments over many generations. Montague et al. 1949. Despite this consensus, the countervailing notion, that complex traits such as disease susceptibility or intelligence are genetically determined and apportioned by racial categories, has resurfaced with some regularity in the public arena. Along with the well-publicized successes of DNA analysis and genomics has come a biologist's perspective on DNA and race. 49. Hope that genetics can inform this discussion. Below, I describe 3 situations where issues of race, variously defined in terms of geography, ancestry, or history, have been incorporated into genetic studies. Genetic studies of human population migration. Over the past 40 years, geneticists and anthropologists have used biochemical and genetic studies of individuals from many geographically or culturally isolated groups throughout the world to define the origins and historical migrations of human populations around the globe. Populations have been characterized by the frequencies of specific protein variants. Bodmer and Cavalli-Sforza 1976, Cavalli-Sforza et al. 1994, or through examination of the frequency of specific sequence differences, found either in mitochondrial DNA, inherited solely from one's mother, Kin et al. 1987, Wallace 1994, or along the Y chromosome, inherited solely from one's father, Armour et al. 1996, Jord et al. 2000, Underhill et al. 2000. These studies have converged in the recently Out of Africa (ROA) model of human geographic history. According to the ROA model, all modern humans originated in the Rift Valley in northeastern Africa. Small groups migrated at different times during the past 100,000 years throughout Africa, as well as north to Europe and the Middle East, and east to Arabia, the Indian subcontinent, and the rest of Asia, with further migration to North and South America. Each group of émigrés carried in their genomes both a more limited set of genetic variants than was present in the larger African population and specific variants that became more frequent as the founding populations expanded throughout Europe, Asia, and the Americas. Identification of ancestry. Informative markers. Investigators have identified certain DNA markers whose frequencies differ significantly between populations living on different continents. For example, the FIO allele of the dark gene is present in more than 90% of West Africans, but in less than 5% of Europeans or Asians. Hamblin and DiRienzo 2000. A 300 base insertion, ALU sequence, at a particular locus on chromosome 7 is found in more than 50% of Europeans and Asians, but in less than 5% of Africans. Bamshat et al. 2003. Using markers such as these, researchers have sorted individuals into groups that cluster by continent of origin. Presumably these are changes in the DNA that occurred after the European and Asian migrations out of Africa. In one influential study, Rosenberg et al. Rosenberg et al. 2002, looked at 377 genetic loci in the DNA of 1,056 individuals, previously collected from 52 different populations. Approximately 95% of the genetic variation in the data set was among individuals within populations, while less than 5% of the variation was between populations. They interpreted this to mean that the average proportion of genetic differences between individuals from different human populations only slightly exceeds that between unrelated individuals from a single population. Though the differences among populations were minor, Rosenberg et al. Then used 50 Abram Gabriel. A clustering algorithm to divide the sample set into any number of subgroups based on their distinctive allele frequencies. When they set the number of subgroups to 5, the program blindly separated the individuals into clusters that corresponded to the major geographic regions of Africa, Eurasia, East Asia, Oceania, and America. This study and others, Bamshat et al. 2003, Witherspoon et al. 2007, Singh et al. 2009, have demonstrated that, with sufficient number of markers, an individual's ancestry can be determined at the level of continental origin. Admixture mapping. One approach to genome-wide association studies, termed admixture mapping, explicitly uses racial differences to identify disease genes, Chakraborty and Weiss 1988, Makega 1998. The technique is best suited to identify gene variants for diseases whose incidence differs greatly between two populations. Investigators analyze DNA for ancestry-informative SNPs in individuals with the disease and in control individuals, both groups being offspring of matings between the two populations, Selden et al. 2004, Smith and O'Brien 2005. In general, cases and controls should share the same frequency of SNPs at ancestry-informative loci, except near the disease gene locus, where cases are more likely to possess the marker associated with the high-incidence population. Admixture mapping can be carried out with any group of individuals whose recent ancestors came from two or more genetically distinct populations. African Americans have been the population most studied using this approach, because their genomes have an average admixture of approximately 20% European variants and approximately 80% African variants, Para et al. 2001, Smith et al. 2004. Studies have also been conducted with Latin American populations, though they have a more complex mixture of European, Native American, and African ancestry, with significant differences in proportion depending on their nationality. Price et al. 2007. To date, admixture mapping of African Americans has been most definitively used to identify an allele of the dark gene, nearly fixed in West African populations, that correlates with lower white blood cell counts in African Americans, see below, Reich et al. 2009, as well as two variants of the APOL1 gene, present in approximately 40% of a Nigerian population but absent from European, Chinese, and Japanese populations, that are strongly linked to non-diabetic end-stage renal disease in African Americans, Genovese et al. 2010. In these three examples, specific genetic variants have been used to characterize group ancestry, where group refers to continent of origin and ancestry refers to forebears that settled in different geographic locations after leaving Africa. Do these genetic markers define human races? To answer this question would require an agreement on the definition of race. But the concept of race is so dependent on its cultural context that it is difficult to conceive how to objectively define the standard human populations in genetic terms. Without this linkage, the connection between race and genetics remains murky, subjective, and potentially dangerous. A biologist's perspective on DNA and race. 51. One official source of self-identified racial categories is the Federal Office of Management and Budget, OMB, whose definitions are used by the U.S. Census Bureau. These categories have changed more than 10 times since their inception in 1800. The year 2000 categories are based on a mixture of skin color, geographic origin, and shared language. These OMB categories are standard for the myriad studies that have documented differences in disease incidence and disease outcome among Americans by race. But does that fact also put the federal imprimatur on racial classification in biological research? As Brawley explains, the OMB openly states that the categories are not based in scientific derivations, taxonomy or anthropology, but are socio-political categories. These categories are published to collect socio-economic data. Too often, data concerning health are collected with these socio-political categories and scientific conclusions concerning biology are drawn from them. Brawley and Yanni 2007. A recent report suggests that geneticists do not adequately address the racial variables in their own research. 30 geneticists were interviewed about their use of OMB categories of race in their studies. Although the investigators acknowledged the arbitrary vagueness of the classification and its scientific inadequacy, most defended its use in their work, calling racial labels proxy variables. Hunt and Magese 2008. It's surprising that geneticists, known for their care in designing experiments, would be so willingly lax in using OMB race variables for their studies. The value and potential consequences of using racial variables in genetic studies of disease predispositions has engendered considerable debate. Some investigators note the correspondence between clustering of individuals by ancestry informative markers and classifying them by the self-identified OMB racial categories. Given the established literature on differences in disease incidence and outcome by OMB racial categories, they conclude that this justifies the potential link between disease susceptibility and genetic background. Burchard et al. 2003. They maintain that, in cases where allelic variation between population groups does correspond to differences in disease risk, failing to acknowledge or examine these potential differences by genomic methods would be wrong-headed. Mountain and Risch 2004, Risch et al. 2002. Other researchers worry that the presumption of genetic explanations for disease disparities will lead to a genetic determinism that minimizes more complex social considerations and environmental solutions. Duster 2005, Sankar et al. 2004. Similarly, linking race to disease could result in stigmatization of whole populations, opening a backdoor to eugenics, according to sociologist Troy Duster, Duster 2003. An informative case in point is the Duffy antigen, the protein found on the surface of certain cell types, including red blood cells, encoded by the dark gene. Most West Africans carry 2 copies of the FIO allele of dark in their genomes, and consequently lack the protein on their red blood cells. More than 30 years ago, Lou Miller and colleagues demonstrated that individuals lacking the Duffy 52 Abram Gabriel antigen on their red blood cells are absolutely protected from infection by Plasmodium vivax, a non-lethal but often severe form of malaria. Horuk et al. 1993, Miller et al. 1976. These parasites require Duffy antigen as a receptor to enter red blood cells, where they divide and cause their greatest damage. Recently, Reich et al. 2009, demonstrated an extremely strong association between homozygosity of the FIO allele and the previous observation that people of African ancestry tend to have lower peripheral white blood cell counts than those of European descent. This phenomenon has been termed benign ethnic neutropenia. Comparing the dark loci of African Americans and European Americans, they showed that the white blood cell counts of African Americans who were heterozygous for FIO at this locus, or homozygous for the European allele, were indistinguishable from European Americans. Presence of 2 FIO alleles, however, shifted the average white blood cell count by 1.3 standard deviations, Reich et al. 2009. These findings regarding the FIO allele among West Africans, other Africans, African Americans, Europeans, and European Americans have important implications to the discussion of race, ancestry, and human disease. The FIO allele is nearly fixed in West Africans, but almost never observed in other populations. An allele differentiation this extreme is seen in fewer than 0.003% of all human genome variants, Reich et al. 2009. Thus, SNPs that carry so much information about regional ancestry are exceptionally rare. Reich's work demonstrates that the phenotype of low white blood count is predicted by the number of FIO alleles in an individual's genome, not by the individual's self-identified race. Further, it is noteworthy that, in this case of a phenotype associated with an extreme difference in allele frequency between individuals of West African descent and others, the condition does not in fact result in any disease. Thus, even in the presence of such a rare regional ancestry informative marker, the relationship between genetics, one's race, and disease remains extraordinarily complex. The cultural and scientific climate in which race and genetics is joined. In today's society, terms such as DNA, genetics, and genomics are part of the common parlance. Companies, governments, the media, and even many scientists and physicians are invested in the belief that genomic research will benefit individuals. African Americans have been particularly targeted, because of their special interest in ancestry analysis, through efforts to equate their higher incidence of many diseases in the United States with their genetic background, and by the FDA's 2005 endorsement of Bidil, the only drug approved specifically for use in a particular racial group, Ellison et al. 2008, Temple and Stockbridge 2007. But two interrelated trends in our culture make it difficult for the public to clearly judge the promises of genomics or whether the concept of race adds to our understanding of the human genome and human diversity. First, the general public has a biologist's perspective on DNA and race. 53. Complex relationship with biomedical science, both skeptical and rapt, which leads to less than critical evaluation of claims made by, or in the name of, scientists. Second, since the beginning of recombinant DNA technology in the mid-1970s, business interests have become increasingly involved in the fields of genetics and molecular biology. The ascendance of DNA in the public mind. Public awareness of DNA and genetics has rapidly increased over the past 20 years. Whereas DNA was once a term known only to biologists, in 2007, the New York Times published more than 800 articles containing the term DNA, including 126 in the arts sections, 25 in the sports section, 4 in the automobile section, and even 1 in the real estate section, compared to a total of 142 references in 1987. But public familiarity with the word DNA does not translate into a general understanding of its biological meaning. Rather, Americans both revere and mistrust scientists, and this ambivalence leads to unrealistic beliefs about the scientific process. On one hand, polls show that scientists and physicians are among the most respected and trusted professionals. Harris Poll No. 61, August 8, 2006. DNA data has proven to be the most objective source of evidence in criminal cases and in paternity determination. There is a thread of belief among many Americans that science and technology can get us out of any jam. On the other hand, polls show that less than 50% of the population believes in the theory of evolution, the bedrock of all biology. Miller et al. 2006. Many people are doubtful of scientists' motives. Some of this mistrust stems from historic realities such as the eugenics movement and the participation of researchers in the Tuskegee study of untreated syphilis in the Negro male, 1932–1972, or more recent revelations about conflicts of interest by several prominent academic physicians. The public may be influenced by rumored connections between vaccines and autism, nefarious origins of the AIDS epidemic, or even the frequent imagery of mad scientists, colluding with corrupt capitalists and incompetent bureaucrats, that we see in popular films, TV shows, and books, from Jurassic Park to the X-Men. Both views express unrealistic attitudes about science and the scientific process, either overly expectant or overly skeptical. In actuality, scientific progress is incremental. Breakthroughs are unusual and sometimes only appreciated long after they were made. The timing and even the direction of advances are unpredictable. Basic research is inefficient, multi-focused, only moderately directed, simultaneously cooperative and competitive, self-regulating, yet ultimately tremendously successful at advancing knowledge and society. The scientific enterprise is an example where the whole is greater than the sum of its parts. Basic scientists, at the core of the process, are those most likely to understand the power and the limitations of their discoveries. But they are less likely to pursue the commercial applications of their work, that is not their forte. Individual. 54 Abram Gabriel. Scientists may be motivated by being the first to uncover new knowledge, by being passionate about a particular fundamental question, or by the hope that their work will lead to something that betters mankind. They function within a global community of investigators who exchange information and ideas. The importance of a given result is determined when other scientists reproduce it, apply it to other species or situations, and use it to extend or modify their existing concepts. Competing theories, favored by different scientists, can only be reconciled over time by seeing how well each fits the data and how predictive each is of future experimental results. Consequently, the interests and concerns of basic scientists may be quite different from those trying to popularize or apply their knowledge. The development of innovative technology and experimental methods, interpretative models, and real-life applications are all components of the scientific enterprise, but they are rarely in sync with one another. McBride et al. 2008. Whereas basic scientists are more concerned with the experimental design and their models, companies are focused on the equipment and its applications. Consider recent developments in human genomics. Collaborative groups such as the HapMap project and the Human Genome Diversity Project are mapping SNPs and sequences from large numbers of individuals in many populations, filling databases with reams of genomic information. But the techniques to make sense of the incredible diversity within the human genome are only in their early stages. Although genome-wide association studies are revealing an array of potential disease loci, very few of these associations have identified specific disease gene variants, and none have led to basic changes in our understanding of common diseases or changes in diagnosis and treatment. Human geneticists are still debating the proper methods to carry out association studies, and the field does not yet have a foundation for understanding the genetic basis of any common disease. Statistical algorithms and computational models are still being developed to interpret or even to display and fit the huge amounts of generated data. Cousin 2008, McCarthy et al. 2008. Despite these limitations, companies are racing forward with denser microarray slides and better sequencing platforms. Other companies are marketing genomics as the key to ancestry analysis and the path to personalized medicine. Their methods, their levels of certainty, and their basic motivations are different from those of the basic researchers, yet to the public, the distinctions are fuzzy. Much of this blurring is the result of the alliance of academic research, biotechnology, and government. The consequences of the commercialization of genomics. Private investors have been stakeholders in the fields of genetics and molecular biology since the 1976 incorporation of Genentech, the first biotechnology company. Pharmaceutical companies comprise the biggest share of the biotechnology industry. The current genomics era is technology-driven and heavily dominated by a few corporate entities that produce the devices necessary for genomic research. A biologist's perspective on DNA and Race 55. Including microarray readers, massive parallel sequencing platforms, and the consumable supplies required to run this equipment. These expensive and specialized instruments have vastly increased the amount of data obtained in a single experiment. The current mix of basic science, technology development, and biotechnology applications is a fact of life, but the composition of the partnerships has important consequences to the development of the field of genomics. First is its impact on how science is carried out. The influence of corporate and proprietary interests narrows the wiggle room for researchers to explore, expand, and tinker. Although the pharmaceutical industry is heavily invested in research compared to other industries, their marketing budgets are nonetheless typically more than twice those of their research budgets. Angel 2000. Changes in corporate focus may mean that promising basic research or whole areas of investigation are dropped. Companies may decide not to invest in basic research at all, but to restrict their research budgets to applying published findings of academic researchers or obtaining intellectual property from universities through patent licensing. Short-term gains and corporate goals necessarily take precedence over the slow, haphazard, and individually inefficient but globally effective approach that was so successful in the period leading to the recombinant DNA revolution. Second is the lure of biotechnology for academic institutions. Universities have a vested interest in exploiting the intellectual capital of their faculty and in encouraging researchers to patent their ideas. Many schools employ lawyers and businessmen to translate faculty intellectual property into licensed applications with biotechnology and pharmaceutical firms or university-financed startup companies. Proceeds from technology transfer can be a major source of revenue for a university. In 2008, 156 U.S. institutions generated over $2.4 billion from licensing faculty inventions. www.autm.net/right. Third is the dilemma for university scientists. The incentives for academic and corporate research are at odds. Academic researchers have an imperative to publish and share their findings, while company researchers have strong motivations to be secretive about their findings and keep them out of the hands of competitors. The peer review process employed by academic scientists to judge publications and grant proposals is meant to assure that claims are evidence-based and that wishful speculation is kept to a minimum. This is the antithesis of the business model, in which limited data is used to spin the prospect of lucrative future applications and returns. For academic investigators who advise or direct companies on the side, or who have patented an idea and want a company to license it, there are real dangers of losing objectivity and risking conflict of interest. Even the process of carrying out experiments and interpreting results can be problematic when commercial concerns are injected into the scientific process. Experiments succeed or fail for reasons that may not be clear. When interpreting data, investigators must distinguish between alternate explanations, which may only be resolved by further experiments. Experiments that work in one cell type or 56 Abram Gabriel strain may not work in another. The careful investigator does not overgeneralize from his or her results. Only by replicating the results through many experiments, using different cells and/or different conditions, can the investigator reliably generalize from observations. But the public, the shareholders, the special interest groups, and the press may not understand the limitations of the scientific process in delivering speedy or unambiguous results. The multiple roles of the federal government. The federal government influences the directions of scientific inquiry and its connection to the private sector in many ways. The National Institutes of Health, NIH, are the leading funding source to basic scientists for genetic and genomic research. Since the government derives no direct financial benefit from discoveries or patents based on this funding, it in effect subsidizes research and development from which the private sector may eventually profit. By determining funding priorities and soliciting grants for research in particular target areas, the government broadcasts what it believes are the most pressing medical and biological priorities. In addition, NIH encourages and supports academic/private collaboration and commercialization through grants for Small Business Innovation Research, SBIR, and Small Business Technology Transfer Research, STTR. As discussed previously, the federal government also influences the perception that there is a connection between race and genetics. Since 1993, government-sponsored clinical trials and studies on human subjects are required to attempt to represent women and racial minorities, based on OMB definitions, and report this information to the government. While this rule was put in place to ensure inclusion of often underrepresented groups in human research, an unintended consequence is that it appears to validate racial classifications in biological research. Epstein 2007, Lee 2009, Lee and Screntny 2010. The same is true in the case of the drug Bidil. Based on limited studies, the FDA specifically approved the drug for use in African Americans with congestive heart failure. The implication of this approval was that the agency accepted that self-reported racial classifications translated into biological differences in response to a pharmacologic agent. The problem of using race in genetic analysis of ancestry. Many Americans can trace their pre-immigration ancestry without resorting to DNA analysis and take their geographic origins for granted. However, most African Americans have been denied knowledge of a large portion of their history and heritage, due to their ancestors' forced migration to the Western Hemisphere followed by the undocumented genetic admixture that accompanied the period of slavery. In the past decade, Harvard professor Henry Louis Gates Jr. and his PBS television show African American Lives helped popularize the use of DNA testing to delve farther back into individual African Americans' genealogy. Following the success of that show, Gates founded Africandna, a company dedicated to offering both genetic testing and genealogical tracing services for African Americans. A Biologist's Perspective on DNA and Race 57. www.africandna.com/right. Currently, dozens of companies offer individuals' DNA analysis for genealogical purposes. The rising interest in race and DNA has occurred within the business-friendly environment of human genomics. Companies that offer DNA-based ancestry determination to individuals base their knowledge and techniques on previous basic research that identified specific variations in mitochondrial DNA or along Y chromosomes, the two regions of the genome that correlate with matrilineal and patrilineal lines of descent, respectively. Commercial ancestry testing is an unintended spin-off from basic research, but the basic research was designed to answer questions about population migration in a probabilistic manner and not to provide concrete and detailed genealogical information to individuals. At that level, current DNA approaches are neither reliable nor truly informative. One reason for this is the fundamental nature of inheritance of genetic markers. We each inherit half of our DNA from each parent, or stepping back a generation, we inherit, on average, a quarter of our DNA from each of our grandparents. Each of our siblings also inherits a quarter of each grandparent's DNA, but it is not necessarily the same quarter, so there will be only partial overlap between siblings. Assuming 25 years per generation and working back 2 centuries, 256 different individuals, living 8 generations ago, contributed some of their DNA to each of us. Can DNA testing tell us about the geographic origins of all these 256 distant ancestors? Most companies test SNPs on either the mitochondria or Y chromosome, which at best provide information about 2 of these 256 ancestors. Other companies look at markers scattered throughout the chromosomes. But we do not know how many ancestry-informative markers there are, nor do we know how many should be tested. Depending on which variants an individual has inherited from those 256 ancestors, the same DNA test could give different geographic ancestry results for siblings with the same parents. Ancestry testing of individuals has other, more technical, problems. Population standards of allele and marker frequencies have been derived from many populations sampled at different times by different researchers using different sampling methods and different loci. Determination of ancestry beyond the level of continent of origin is a statistical exercise based on differences in frequency of variance at multiple independent loci. The presence or absence of a particular allele at any one locus is usually insufficient to determine ancestry. Variants at each locus occur at a particular mean frequency for each population, surrounded by their own confidence intervals. The job of ancestry analysis is to determine which expected pattern of variation among many tested population groups best matches the set of variants present in an individual's DNA. However, the reliability of the observed population data completely depends on the sample size and representativeness of the standard group analyzed for each population. This is a particularly difficult problem if an individual's ancestors come from different populations. The number of useful loci capable of distinguishing between two populations depends on the degree of mating and mixing between. 58 Abram Gabriel. The two populations, the time since the two populations diverged from one another, and the number of generations separating the individual from his or her ancestral population groups. The more mixing of different ancestral populations in an individual's family history, as is common for many Americans, the less similar a person's genetic pattern will be to the standard populations. If companies stated all of these very real provisos, caveats, and uncertainties, most consumers would likely be left scratching their heads and wondering what new information they had actually learned from ancestry tracing. The problem of using race in the discovery of disease genes ancestry mapping has been referred to as recreational genetics, Balnick et al. 2007, to differentiate it from genetic analysis related to the more medically important area of disease association. It is in the area of disease studies that the relationship between race and genetics becomes the most susceptible to misinterpretation and distortion. Africa contains more than 2,000 different ethno-linguistic groups, Reed and Tishkoff 2006. DNA analysis of present-day Africans reveals 14 ancestral population clusters, Tishkoff et al. 2009. DNA among African populations tends to be more variable and distinct than among populations from other continents. Cardon and Abekasis 2003, Tishkoff and Kidd 2004, Tishkoff and Varelli 2003. Work carried out by geneticist Sarah Tishkoff and others makes it clear that sweeping conclusions about African Americans and disease-associated genetic variants are untenable. These conclusions are relevant to discussions of how race, disease, and genetics are related in the United States. The notion that African Americans share some meaningful collection of specific disease alleles defies logic. Even the term African American makes no sense genetically, as it implies a unified population. The 20% average admixture of European alleles in African Americans, as well as the great genetic variation among different African populations, belies this biogeographic generalization. Even though the ancestors of a majority of African Americans were brought to the New World from West Africa, that region comprises many distinct populations, and a sizable proportion of slaves originated in Central Africa and Southeastern Africa. Since their arrival in the New World, African Americans have admixed among these different original populations, as well as with European and Native American populations. Skin pigmentation is one of the most obvious components of self-described race used for census enumerations and medical studies in the United States. But while variation in skin pigmentation is clearly a genetically determined trait under natural selection, it is not a particularly well-studied area in human genetics. Para 2007, Rees 2003. An unknown number of genes, but probably greater than 10, are involved in determining one's skin color. One reason for the relative lack of scientific interest in the subject may be the paucity of known diseases in which skin pigmentation plays an important etiological role. Only two relatively common conditions come to mind. Skin cancers including melanoma are much. A biologist's perspective on DNA and race 59. More rare in African and Asian populations than in European populations, probably because of the protective effect of melanin from ultraviolet light, UV, induced DNA damage. Conversely, nutritional vitamin D deficiency is a more frequent problem among darker-skinned individuals, since UV exposure is required to synthesize vitamin D in the lower layers of our skin, and melanin reduces the amount of available UV. For most diseases in the United States that differ in incidence by race, racial differences correspond to socioeconomic or cultural differences. Most of the difference in incidence of asthma, hypertension, and heart disease by race can be explained by differences in income and environmental risk factors. Smith et al. 2005, Thomas et al. 2005, Thorpe et al. 2008. Each of these is a multigenic disorder. At the other end of the disease spectrum are the relatively rare inherited diseases like sickle cell anemia, incidence among African Americans approximately 1/700 live births, incidence among European Americans approximately 1/158,000 live births, Laurie et al. 1996, or cystic fibrosis, incidence among non-whites approximately 1/12,000 live births, incidence among whites approximately 1/3400 live births, Kosaruk et al. 1996, that are caused by mutations in single genes. These diseases appear to show the strongest links between race, disease, and genetics. They are clearly genetic disorders, caused by recessive mutations in specific genes that become a problem in one of 4 offspring of parents who each carry a copy of the mutant gene. Upon further scrutiny though, the apparent racial basis for these disorders turns out to be a red herring. Sickle cell anemia is a disease that occurs when an individual inherits a specifically mutated version of the beta-globin gene from each of his or her parents. Children who inherit the mutated gene from only one parent are normal. The mutation involves a particular base change at the position that codes for beta-globin's 6th amino acid. This same mutation arose independently in different populations at least 5 times during human evolution, and has been designated as the Bantu, Benin, Senegal, Cameroon, and Indian haplotype, La Pomeruli et al. 1992. In each place the mutation emerged, the presence of the mutant allele in a single copy likely provided a slight advantage to children from 6 months to 2 years of age in resisting the lethal effects of falciparum malaria. For human populations living in regions where malaria was endemic and a major killer of children, individuals with a single copy of the mutant gene were more likely to live to adulthood and reproduce. Over many generations, this selective advantage increased the fraction of individuals within these populations who carried the mutant allele. Allison 2004. This is a classic example of the subtle power of natural selection. Unfortunately, when a sufficient proportion of a population carries the mutant allele, the probability increases that a child will inherit a mutant allele from both parents and have sickle cell anemia. In pre-antibiotic times, this severe and painful form of anemia was usually fatal in childhood. Over centuries the mutant alleles have spread, through mating, to additional populations in Africa, Europe, and the Middle East. Other population groups in 60 Abram Gabriel. Africa, particularly where malaria was absent or only an occasional burden, have either very low or negligible frequencies of the sickle cell mutation. Coincidentally, the major sources of African slaves to the Caribbean, North and South America were from the very regions where high levels of the sickle beta-globin allele were present in the population. The mutant gene was imported to the Western Hemisphere along with these individuals. An Ethiopian from East Africa or a Namibian from South Africa is no more likely to have sickle cell anemia than a person from Iceland or North Korea. From a genetic perspective, the disease is associated with individuals whose ancestors originated in specific parts of West Africa, Central Africa, and Central India. We know that an individual's genetic makeup, the specific polymorphisms that make him or her unique, will influence what diseases he or she is more or less likely to develop over the course of a lifetime. We also know that in most cases genetic predisposition is heavily influenced by environmental considerations. For most common diseases in the United States, an individual's risk is linked less closely to one's genetic makeup than to factors such as age and sex, as well as environmental and behavioral characteristics like income, diet, smoking, place of residence, and maternal education. Further, genetic risk is determined not by a single variant of a single gene, but by how different variants of many different genes interact in each individual in a more or less protective manner. Given the greater genetic variation among Africans than among European or Asians, I suspect that Africans have very few significant phenotypic traits in common beyond adaptation of greater pigmentation compared to many populations that migrated out of Africa in the past 100,000 years. Even in the extreme case of the Duffy antigen and the phenotype of vivax malaria resistance, discussed above, this is primarily associated with West African populations. Concluding remarks. The early history of human genetics provides a cautionary lesson in the mischaracterization of race as a biological determinant. While it is easy for us to look back in horror at this travesty, it's likely that early population geneticists with eugenic agendas, like Charles Davenport, Francis Galton, and Carl Pearson, worked in good faith within the context of their times and their social and political positions. In one of the essays accompanying Davenport's recently reissued 1911 text, Heredity in Relation to Eugenics, Witkowski et al. 2008, University of Washington geneticist Maynard Olson points out 3 red flags in Davenport's writing that should be kept in mind by today's geneticists. Davenport deeply commingles science and social values. His thinking is often hopelessly muddled. And he overpromises what genetics could achieve even if it were vigorously applied to societal problems. Olson, 79 in Witkowski. As I have described in this perspective, in today's genomic environment, the dominant social value is capitalism. The goals and approaches of business and basic scientific research have traditionally not aligned. How will the continued A biologist's perspective on DNA and race 61. Commingling of science and corporate values affect the types of questions asked, the directions the science follows, the strength of data accepted, and the priorities set by funders? Muddled thinking is a fact of life and an occupational hazard. For example, the impact of individual studies can be compromised when investigators lack an understanding of epidemiology and biostatistics. McCarthy et al. Make a plea for improved study design and for validation and replication of genome-wide association studies, McCarthy et al. 2008. We have no firm conceptual basis for characterizing the genetics of most common diseases and do not even agree on the best method for identifying the genetic components. As McCarthy et al. State, recent discoveries by the genome-wide association approach are nothing more than initial forays into the terra incognita of our genomes. As for overpromising what genomics can achieve, this is reflected today in both the shaky claims of genomics companies and the ebullient optimism that colors each newly announced discovery. We have no evidence that sequencing the entire genome of every individual will result in the predictive powers that proponents of personalized medicine envisage. Nor is there evidence that healthy individuals want to know or even care about their future probabilities of contracting different diseases, particularly if the predictive powers of the tests are imperfect and nothing significant can be done prophylactically. Science is technical and difficult to comprehend, but that does not absolve scientists of the responsibility to inform the public about their work, explain their methods and their rigor, admit the limitations and areas of controversy and uncertainty, and examine its wider relevance. Conversely, the difficulty of understanding and digesting science does not absolve the general public from acknowledging its importance and its contributions. The public should not assume that the public policy aspects of scientific advances are being properly debated and regulated at the state or federal levels. For example, see a case study on the lack of regulation for a pharmacogenetic test of dubious validity in Katansis et al. Katsanis et al. 2008, or that information received from companies will be independently verifiable or meaningful. Personalized genomics companies would like to adapt published associations between chromosomal regions and common diseases to predict disease risk for individual consumers. But these predictions are based on case control studies of limited populations, primarily of European ancestry. Basing prospective risk assessments for diverse individuals on retrospective analyses of restricted populations is risky at best. Questions of how admixture in individuals might affect genetic predictions, or the way in which environmental exposures influence the genomic data, have yet to be addressed. The public should treat the stated or implied claims that companies make about current capabilities with a healthy dose of skepticism. What would it take to derive meaningful and predictive associations between specific genomic variants and medically important diseases? Despite much wishful thinking, it is not clear that this level of personalized genomics will ever 62 Abram Gabriel become a reality. But for microarray-based genome-wide association studies to stand a chance of being validated, millions of marker loci will need to be simultaneously monitored and clustered. Databases of SNP associations will need to contain large numbers of cases and controls with various diseases, where the individuals represent the full range of human population mixing. Analysis of genomic associations will need to be done in the context of an individual's complete environmental history. Such an endeavor would be a massive undertaking, and its utility in improving human health is not assured. Perhaps without the pressure and expectations of the biotechnology industry and an overeager public, scientists could proceed, at a thoughtful and careful pace, to unlock the information within individual genomes. Such an analysis would be based on an individual's idiosyncratic genetic makeup, in which case the arbitrary and non-biological variable of race would be irrelevant. 5. The dilemma of classification. The past in the present. 67. W. Heather. The concept of race captures some degree of underlying biological or genetic homogeneity has been contested for centuries. To resolve the controversy, some biomedical researchers in recent years have called for substituting ethnicity, Institute of Medicine 1999, or microethnicity, Jackson 2004, for racial categories. While efforts to develop more fine-grained methods of classification are commendable, they nonetheless remain rooted in the notion that populations, large or small, are static, or at least so slowly changing that they can be demarcated for scientific purposes. The insufficiently examined concept of population, we suggest, underlies the notion of race deployed in various contexts, be it ancestry testing, forensic analysis, population genetics, or biomedical research. As the geographic site of early human evolution and great human genetic diversity, Africa has assumed increasing importance for researchers interested in human origins, history, and migration, the genetic etiology of complex disease, and racial disparities in disease. Tishkoff and Williams 2002. With attention to improving past practices, African partners are eagerly sought for genetic investigations in Africa. Careful thought is given to informed consent for DNA sampling, and co-authorship on publications is now the norm. But the research agenda remains that of the global North. Moreover, the Africa that informs this agenda is shaped profoundly by images of the continent constructed through travelers' experiences, media accounts generally centered on violence, famine, disease, and chaos, and the history of expert knowledge systems in the human and natural sciences. One commonality to these narratives that hovers uneasily over the science is Africa as a space for adventure and philanthropic zeal, peopled by geographically distinct, remote tribes. The New York Times, Lacey, 2005, in other words, a space of negation that is everything the West is not, Mbembe 2001. In this paper, we focus on Africa to historicize conceptual problems that plague the notions of population and groups, whether macro or micro, and their use in genetic research. Specifically, we trace the processes by which two expert knowledge systems, linguistics, and social anthropology, transformed what were, and are, fluid societies into sharply demarcated, bounded units amenable to scientific analysis. Although certainly building on earlier ideas about Africans as naturally organized into groups, we argue that the conceptualization of populations, ethnic groups, or tribes as discrete entities suitable for scientific definition, sampling, and classification hardened in the 1930s and 1940s. At this time, social anthropologists took to the field to delineate the dynamics of African societies. The field of linguistics became professionalized, and both disciplines of study became institutionalized in Western and South African universities. Once named and studied in depth, knowledge of African societies was further flattened as anthropologists in the United States, notably George's Peter Murdoch, constructed internationally accessible atlases and databases, thereby making natural the existence of populations as bounded entities. Murdoch's grand systematizing project thus set the stage for the use of African societies in large-scale population genetic studies currently underway, and also for the contemporary reinvigoration of broad claims of difference based on population identification. In acquiring the status of transnational, and thus universal, knowledge, the complexity of local knowledge systems, with their blurry boundaries and their varied contributors, was erased. Not surprisingly, the move to finer levels of group analysis has not signaled the end of race. Indeed, many studies that deploy populations as units of analysis are easily reaggregated into what seems eerily akin to traditional racial typologies, in both the scientific and the popular imaginations. From race to population, from population to race. To be useful in biological investigations, a population must represent a gene pool, which is bounded, geographically, linguistically, or culturally, reproductively isolated, and relatively unchanging over a long period of time. The requirement for isolation, evident in the call by leading population geneticists in 1991 to organize a DNA survey of human diversity, known as the Human Genome Diversity Project, HGDP, has a long history, which Jenny Reardon, 2005, and Ahmed M. Karak, 2005, have so insightfully analyzed. The populations that can tell us the most about our evolutionary past, organizers of the HGDP note, are those that have been isolated for some time, are likely to be linguistically and culturally distinct, and are often surrounded by geographic barriers. Such isolated human populations are being rapidly merged with their neighbors, destroying irrevocably the information needed to reconstruct our evolutionary history. Cavalli Sforza et al. 1991, 490. This sense of urgency has been a recurring theme in the writings of Luca Luigi Cavalli Sforza and other scientists, as well as those of linguists and social anthropologists. Despite a long history of contest, McEachern 2000, for organizers of the HGDP, the existence of populations was a given. It was simply a technical question of identifying them and assembling the requisite linguistic expertise to trace the 68. Coevolution of genes and languages and on anthropological expertise to prioritize the units for sampling and describe any cultural traits relevant to genetic research. Yet, maintaining clarity on the unit of study has been a challenge, as illustrated in Genetic Structure of Human Populations, an article published in Science by Rosenberg and colleagues in 2002 using the HGDP-CEHP database. 1. On the basis of genotyping a mere 1,056 individuals from 52 predefined populations, only 6 of which were African, these investigators claimed that allelic frequencies clustered by continent of origin. The methods by which populations were defined did not even warrant a footnote in this article. Despite the many assumptions built into structure, the computer program employed to cluster DNA data from sampled populations, Balnick 2008. What is significant for this discussion is that Rosenberg and colleagues employed the language of population, not race, in their paper. That continental clusters, however, were thinly disguised surrogates for race was made clear when Nicholas Wade of the New York Times, 2002, argued that the Rosenberg study proved that races did, in fact, exist. In interviews with Wade, the authors concurred, perhaps uneasily, that these regions broadly correspond with popular notions of race. Race is thus reproduced, naturalized, and reified, Duster 2005, through complex and largely invisible mechanisms of population. Delimiting tribes in Africa, from missionaries to linguists. As historian Leroy Vail and co-authors, 1989, have illustrated in their fascinating collection The Creation of Tribalism in Southern Africa, ethnicity is not a simple reflection of a traditional or tribal past, insulated from historical change. Rather, in Africa concepts of ethnicity, or tribalism, or what Lisa Gannett, 2001, refers to more broadly as population thinking, were formed and reformed during the 19th and 20th centuries in response to the internal dynamics of African societies, the rapid social, political, and economic changes triggered by colonialism and industrialization, and, of particular relevance to this discussion, intellectual work in linguistics and academic theorizing about the nature of so-called primitive societies. Important to note, this was not a linear process, imposed in any simple way on African peoples. Rather, what took place on the ground was more akin to what Patrick Harries, 2007, 3, refers to as a swirling interaction. Nonetheless, it was the particular frame constructed by Europeans that circulated transnationally and was ultimately incorporated into international databases. Prior to the 20th century, in accounts that still resonate with rich, if offensive, ethnographic detail, travelers, European missionaries, and colonial administrators embraced the project of producing knowledge about Africans, publicizing their work in the metropole and museum exhibits, books, pamphlets, and the popular press, and using their understandings to guide colonial policy and resolve metropolitan socio-cultural anxieties. Coombs 1995. Travelers, such as John Barrow and Mungo Park, were among the first to systematically engage in a 69. broad project of othering as they described, classified, and homogenized the people they encountered. Pratt 1985. Later, working closely with African intellectuals and informants, Europeans conducted anthropological, ethnological, and linguistic studies, writing the history of tribes, constructing written African languages, and detailing the rights and customs of indigenous peoples. Indeed, even in the 19th century, this work was seen as urgent, as the languages and traditions of indigenous races, and their histories and relationships to one another, were thought to be disappearing rapidly. In his magnificent History of Missionaries, the development of linguistic unity, and the emergence of ethnic consciousness among Tsonga speakers of South Africa, Harries, 1989, 2007, recounts the use of names such as the Tonga to describe heterogeneous groups of migrants speaking different language forms and holding different cultural affinities, who fled to the northern and eastern Transvaal from southern Mozambique. Migrating in successive waves in the 19th century to escape domination by the Zulu kingdom, civil war in Mozambique, ecological crises, and disease, the people of southern Mozambique were linked, not by language, but by their skills as traders, their diet and methods of food preparation, their social organization, and significantly their social exclusion as foreigners in the Transvaal. According to Harries, when people from the coastal area entered the Transvaal, they brought with them a number of speech forms, and these changed and developed as they came into contact with local languages. 2007, 160, emphasis added. Signifying their foreignness, they were variously referred to as Gwambas, Kopas, Tongas, Toka, Nobnoses, Chikis, Bonos, and Shangons. By the end of the 19th century, codification of language was a more sophisticated and transnational enterprise. To further their evangelical work and unify their converts, Swiss missionaries worked closely with African assistants and informants to codify the diverse languages of the coastal peoples from Southeast Africa, which had been influenced by Zulu, Gaza, and Swazi, into a single written language, and to teach this language in mission schools. Working within a Western structure of thought, they created grammar, vocabulary, Bibles, and literature. Harries 2007. The key point for this discussion, however, is that once grammars had been constituted, their man-made origins were forgotten and they were perceived as givens, operating according to natural laws of science. Harries 2007, 166. Bitter debates among missionary intellectuals over the precision of classification ensued, which ignored, if not erased, the complex history of African societies. Although the missionaries failed in their efforts to impose a single written language throughout southern Mozambique and the northern Transvaal, they nonetheless categorized the various languages into distinct subgroups. Confident that speakers of these language subgroups were sufficiently cohesive, the Swiss missionary, linguist, natural scientist, and anthropologist Henri Alexander Junod would confer the status of tribe on Tsonga speakers in 1905. Tsonga speakers experienced continued social exclusion and alienation from the land, a sharp 70. Division of labor and housing in the gold mines structured along tribal lines, a native affairs department in South Africa that promoted tribalism, and a mission-educated petty bourgeoisie schooled in written Tsonga and eager to pursue their own social agendas. By the mid-20th century, an ethnic consciousness, which was consolidated by the Bantustan system of the apartheid government, did indeed develop among Tsonga speakers. Yet, Tsonga is thus best understood as an identity assigned to and adopted and reshaped by a diverse group of peoples in a specific historical context. In the 1890s in eastern Zimbabwe, the people who gathered under Chief Makoni did not understand themselves as Menyika. By 1930, a term that, in the pre-colonial period, referred to a narrowly circumscribed political allegiance, and which was later redefined as the Portuguese and British competed for territory, came to describe a cultural identity rooted in a primordial past of a people composed of residents and settlers in a large geographic area. This shift in identity over the course of 4 decades required the construction, out of an array of dialects, of a written Menyika language, with the standardized orthography and rule of grammar, undertaken by missionaries of the American Methodist Episcopal Church, the Anglicans, and the Trappist/Marianne Hill Catholics. In so doing, differences were exaggerated and gradualism of dialect zones was erased. Ranger 1989, 127. Working in close association with African converts, the missionaries wrote and translated religious works, folktales, and literature. Each mission worked among people who differed in their means of subsistence, interest in linguistics and literacy, and receptivity to missionary work. Despite competing interests, a Menyika identity was consolidated in the 1930s under the pressure of the migrant labor system, as residents in eastern Zimbabwe married foreign women and mission-influenced migrant laborers drew on this identity to survive the dislocation of migration. Ranger 1989, 140. Constructing these identities produced purity out of mixture, something of great importance to Europeans. It is certainly the case that ethnic identities have acquired profound social meaning. It does not follow, however, that these identities conform to cohesive biological or genetically circumscribed units, although it is important to note that, at the time, the arguments for cohesiveness were primarily based on cultural unity. Moreover, missionary linguists did not always produce unity. In contrast, in the case of the Zulu and Xhosa, it was rivalries between missionaries that prevented unification of the languages. While promoting tribalism was not necessarily the intent of missionary linguistic work, missionaries were nonetheless working within a European system of knowledge that constructed reality and produced a pattern of domination. Harries 1987. They drew on and respected local knowledge but, authorized with scientific methodologies, technological instruments, visual diagrams, maps, and cameras, it was Europeans who were considered to be the true systematizers and producers of universal knowledge. Harries 2007, 115. The leap from linguistic 71 group to tribe, with defined and fixed characteristics and boundaries, was but a short one in ordering the universe. The pertinent point for this discussion is that the pattern of domination that produced tribes, or populations that are the unit of study in genetic studies, erased a complex history of intermingling of heterogeneous peoples in pre-colonial and colonial Africa, or, in the language of population genetics, continued and constant gene flow. Despite the persistent efforts of the missionaries, the project of standardization of African languages was not yet complete in the late 19th and early 20th centuries. Fixing and maintaining the boundaries of languages required reliable institutional support, which would come as linguistics became institutionalized in South African universities in the third decade of the 20th century, especially with the establishment of the journal Bantu Studies, in 1922, and the Inter-University Committee for African Studies in 1931. Of particular significance, is that professionalization of linguistics was taking place at approximately the same time and place as the ethnographic turn in social anthropology. Social anthropology, ethnographic fieldwork, and population in Africa. The typological thinking of physical anthropology, with its emphasis on the study of racial origins, dominated scientific discourse in South Africa for the first 3 decades of the 20th century, as Saul Dubo, 1995, has written, whereas population-based concepts of race, based on clustering of genetic polymorphisms, characterized the post-World War II period. Reardon 2005. For this shift to take place, populations needed to be scientifically delimited. Beginning in the 1920s and continuing into the 1960s, social anthropologists of the functionalist school, influenced both by Bronislaw Malinowski's meticulous methods of fieldwork and Alfred Reginald Radcliffe Brown's theories of society, turned to more systematic and theoretically informed study of African societies. Now the unit of study shifted in a more focused way to bounded social systems, tribes, ethnic groups, or populations. Anthropologists themselves have explored the complicated history of functionalism, engaging with the many critiques of their tendency to cultural relativism, narrow focus on synchronic, ahistorical sociological problems, and complicity with colonialism. See, for example, Assad 1973, Stocking 1984, Mudimbe 1988, Gordon 1990, Cooklick 1991, Goody 1995, Cooper 1996, Hammond Took 1997, Cohn 2004. Our purpose here is not to rehearse these debates or explicate the specialized details of the field of social anthropology as it changed over time. Rather, we focus our attention on the unit of study deployed by social anthropologists to illustrate how ethnographic fieldwork produced and sustained notions of populations, tribes, or ethnic groups as bounded entities, and the consequences of such conceptualizations for contemporary population genetics research. The question of the unit of study, writes John Komaroff, far from being a methodological nicety, is a consequential theoretical matter. 72. For fields of inquiry are never naturally given, they always reflect substantive assumptions about the constitution of the real world. Komarov 1982, 144. While the intellectual core of the functionalist school is often located in Britain, it was researchers and educators in Africa, particularly Southern Africa, including the liberal social anthropologists such as Godfrey and Monica Wilson, Isaac Schapira, Meyer Fortes, Max Gluckman, Winifred Hoernle, Richard and Eileen Kriege, and Hilda Cooper, who, with funding from metropolitan organizations such as the International Institute of African Languages and Cultures and the Rockefeller Foundation, conducted extensive fieldwork. 2. They went on to direct institutes in Africa, such as the Rhodes Livingstone Institute in northern Rhodesia, and trained many of the ethnographers who would ultimately hold prestigious chairs back in the Metropole, UCT archives. Neglecting culture, at least initially and, of course, not totally, functionalists conceptualized human societies as decontextualized social systems, in which each element had a functional relationship to the whole. They drew on Comte, Herbert Spencer, and especially Émile Durkheim for their theories of society and on the natural sciences for rigorous methodological approaches. For the functionalists, boundedness was conferred by a social structure held together by ties of kinship and political, legal, and religious institutions created to fulfill needs, be they biological needs as in the case of Malinowski, 1929, 1930, or social needs as in the case of Radcliffe Brown, 1946. According to the anthropologist Jack Goody, students of Malinowski were marked by a formalism, which was realized in their use of diagrams, figures, tables, and significantly, detailed and systematic field notes, which also reflected their scientific orientation. Thus, these early ethnographies and the visual imagery they deployed served to cast societies as static and resistant to change, and the people inhabiting these social structures as without history, even though the researchers themselves had more nuanced understandings of social dynamics. This is not to imply that social anthropologists were an intellectually homogeneous group, slavishly beholden to narrow theories of functionalism, insensitive to the Africans they were studying, or uniformly or absolutely ahistorical. Indeed, like missionaries and linguists, social anthropologists were a varied group from across the political spectrum, with complicated and variable relationships with indigenous people. For the most part, they spent years in the field and struggled, often with great compassion, although of a decidedly paternalistic sort, for their research subjects, to rigorously test their hypotheses and models empirically. Nonetheless, by concentrating on descent as the organizing principle of African societies and guided by the scientific method, social anthropologists' social systems were conceptualized theoretically as closed structures with static regularities and uniformities, or, in the words of Radcliffe Brown, as systems of ordered social relations in a given collection of human beings, Radcliffe Brown 1946. This framework conceptually minimized movements of peoples, which for population geneticists would lead to gene flow between populations. 73. Change, when it occurred in simple societies, was conceptualized as slower than that occurring in complex societies and a consequence of exogenous forces. Monica and Godfrey Wilson 1945. The internal dynamics of African societies were considered less important than European contact in triggering social change. For example, in his defense of British social anthropologists, Isaac Schapira, 1962, rightly claims that the relevance of history to the study of social groups depends to a certain extent on the questions being asked. Although generally skeptical of theorizing, Komarov and Komarov 2006, when pushed to do so, he promotes a sense of history centered on what happened after contact. The tribes the functionalists studied had been so greatly influenced by contact with Europeans that to ignore the resulting changes would have led to an incomplete and distorted view of present-day social life, and study of the changes always included study of when, how, and why they had come about. Schapira 1962, 145. The goal of the social anthropologist, Schapira goes on to write, is to ascertain how far the traditional native institutions persist, not only in memory or in practice, but in addition he tries to ascertain how widespread is the adoption of European elements. The modern anthropologist tries to determine why contact with the Europeans has modified native life along certain lines. Shapira 1962, 146, African history before colonial penetration remains an unchanging and forever inaccessible black box. The inescapable conclusion is that pre-contact societies were produced and therefore bounded by traditional institutions, cultures, and social structures, that persist to greater or lesser extents into the ethnographic present. Although Shapira's theorizing does not reflect his own much richer understanding of Tswana societies, this narrowing of history to the period after contact has epistemological consequences. South African-born Meyer Fortes, a leading figure in British social anthropology for many decades, was quite explicit in his articulation of groups as bounded. A group of people bound together within a single social structure have a boundary, though not necessarily one that coincides with a physical boundary or is impenetrable. Fortes 1953, 22, quoted in Cohn 2004. Structures were, according to Fortes, resistant to change. Fortes 1953, 23. For Radcliffe Brown, culture was not bounded but the system of society was contained within a territorially bounded community. Stocking 1984, 172. Like organic life, social systems had a functional unity. Radcliffe Brown 1935. In his writing about the social anthropologists in Africa, Bernard Cohn, 2004, takes a sharply critical stance, arguing that the conceptualization of African societies as organized into unchanging, bounded entities according to principles of descent was a legitimizing practice, enacted by social anthropologists, which was essential to maintenance of the social order under colonialism. Unit, boundary, social structure, and group, Cohn writes, are the central concepts which appear time and time again in the anthropological literature of the 40s and the 50s. A unit meant something that was observable on the ground. Hamlets, villages, lineages, tribes were believed to be bounded, they were countable and mappable. 74. Had names, and above all had social structures, patterned relations between groups. Groups were made up of individuals recruited on known principles, usually genealogical connections which were thought to be real, i.e. met Western concepts of descent traceable to common ancestors and expressed in the metaphor of blood. Cohn 2004, 203. As noted earlier, a sense of urgency characterized the fieldwork of social anthropologists of the 1930s and 1940s. They were fully aware that colonial interventions were changing indigenous societies rapidly and irrevocably. Radcliffe Brown was so concerned by the rapid disappearance of untouched societies that he urged the Rockefeller Foundation to support a Center for Vanishing Cultures at Yale. Stocking 1984, 168. By the late 1960s, structural functionalism was in decline. But, the social anthropologists' social systems, according to scientific principles, survived. George Peters Murdoch, Classifying Culture. Anthropologists and linguists' tribes could easily double as geneticists' populations. But, first they had to be incorporated into standardized data sets in the systematizing project of the American cultural anthropologist George Peters Murdoch, 1897–1985, a renowned comparativist from Yale. Murdoch's project is of particular relevance to this discussion as his work helped to shape the conceptualization of populations that informs the HGDP. As with earlier anthropological systematizers, Murdoch had limited fieldwork experience himself. From early in his career, he focused his efforts on ordering the ethnographic knowledge of others. Interested in cultural universals and animated by the desire to place the study of society on a scientific basis, Murdoch first published a summary of ethnographies in 1934 and later, in the 1930s, took on the mammoth task of creating the Cross-Cultural Survey at Yale's Institute for Human Relations, a data archive of ethnographic information, later to be the Human Relations Area Files, HRAF. It incorporated ethnographies conducted by field workers operating in a variety of widely divergent and sometimes oppositional anthropological traditions, including those influenced by Franz Boas and Malinowski, who were committed to different classificatory systems. Such a systematic effort would facilitate statistical comparison of cultural traits by researchers the world over. While sometimes critical of the functionalists for their lack of attention to culture and history, Murdoch nonetheless admired their ethnographic contributions for the factual social knowledge they produced. Murdoch 1951. From the early years of his career, Murdoch's goal was to define culture in terms of traits that could be compared globally and analyzed statistically for patterns. Murdoch 1932. For this project, the work of the functionalists as well as other anthropologists would be key. Indeed, in the late 1930s, Murdoch attempted to recruit Evans Pritchard to Yale, a plan that was interrupted by the outbreak of World War II. In the same period, he brought Malinowski to Yale, where he died in 1942, shortly after his arrival. Darnell 1938. 75. In 1957, Murdoch published the World Ethnographic Sample, a compilation of groups worldwide with a simple coding system, in the American Anthropologist, Murdoch 1957. In it he sought to synthesize knowledge of world cultures by detailing their distribution and carefully classifying them according to certain standard ethnographic categories. 664. The sample was further developed in his Outline of World Cultures, published in 1958. Several years later, Murdoch began to compile a more comprehensive coded atlas of the world's peoples in ethnology, a journal he founded in 1962, where he expanded on the number of societies available for cross-cultural analysis. The completed ethnographic atlas, which contained a summary of 239 African societies organized into 85 clusters, was published as a single volume in 1967. By codifying social, cultural, and economic characteristics, such as mode of marriage, family organization, community organization, kin groups, settlement patterns, and so on, into a simplified form suitable for entry on punch cards and later computer programs, Murdoch promoted statistical comparisons of various traits of world societies and ushered in an era of new forms of ordering knowledge about Africa. At the same time, in a more hardened way than previous systematizing projects, he reduced dynamic societies to static forms and rendered invisible the more nuanced understandings of social formations held by ethnographers. In Africa, its peoples and their culture history, published in 1959, Murdoch provides an index of African tribes based on the abundant ethnographic work accumulated on Africa in recent decades. By mapping language, culture, and tribe unproblematically onto each other, the definition of groups appears to be straightforward throughout the book. Tribes, he writes, are classified into groups of essentially identical language and culture, arranged numerically in alphabetical order, with reasonably complete synonymies to facilitate identification through an index of tribal names included at the end of the book. Murdoch 1959, 9. For Murdoch, language was particularly informative of ancestral relationship. Recognizing that classical racial typologies were dated, he unapologetically proceeds to describe the 5 classically typological races: Bushmanoid, Caucasoid, Mongoloid, Negroid, and Pygmoid that people the continent of Africa. Thus, we see here early evidence of constant, and intentional, slippage between populations and more typological notions of race that continue to plague many areas of social and natural scientific research. Although criticized extensively by Africanists, Murdoch's works influenced future genetic researchers in Africa, especially for the purposes of our discussion the research and syntheses of Cavalli-Sforza, McEachern 2000. The hunter-gatherer groups described in Murdoch's Africa, its peoples and their culture history were featured on the first page of the To Cavalli-Sforza's African Pygmies, a detailed compilation of virtually all the studies on population structure, genetics, anthropometry, and other biological characteristics of African pygmies. Significantly, Murdoch's classification of Central African pygmies, deep in the 76. Heart of Africa, framed the conceptualization of pygmies as distinct groups and guided blood sampling. Cavalli-Sforza returns again and again to Murdoch in his ambitious compendium of genetic data, The History and Geography of Human Genes, 1994, and more recently in his popular work, Genes, Peoples, and Languages, published in 2002. As noted previously, some of the most prominent social anthropologists were South African, carrying out ethnographies among people referred to as Tswana, Swazi, Zulu, Xhosa, and so on. Asserting their rightful place in this transnational research agenda, South African scientists are now actively using ethnographically defined populations in genetic research and creating their own databases. Sudyal 2003. Murdoch's Africa, Its Peoples and Their Culture History appears as one of only 3 references in the draft document of the internationally representative Sub-Saharan Working Group of the HGDP, Draft Document ND. The Xhosa as a distinct, and presumably genetically homogeneous, population appears on the working group's list of African populations to be studied. While acknowledging that neither in the present nor past is there any simple correlation between ethnicity, language, and gene pool, the Sub-Saharan Working Group nonetheless decided to sample groups based on ethnicity and language, using Murdoch's maps to select populations to be included on the final list. The reliance on outmoded histories to guide genetic research is all the more surprising, given the proliferation for decades of texts in history and historical anthropology that chronicle the making and remaking of ethnicity in Africa. See, for example, the special issue in the Journal of Southern African Studies on Anthropology and History in 1981. While ostensibly theory-neutral, projects that order diffuse and changing societies into fixed and unchanging databases that serve as handy reference guides for researchers from other disciplines mask assumptions about those societies, erase the complexity of their dynamics and historicity, and convey a skewed sense of the world. Boker 2000. The point here is that the very construction of databases raises important questions of knowledge and power. Conclusion. In what is often referred to as the Golden Age of ethnography, university-trained social anthropologists took to the field to systematically study, organize, and order the world's diverse peoples. With its peoples conceptualized, first and foremost, as members of groups, von 1991, 11, Africa was the centerpiece of this enterprise. Intent on creating a scientific methodology of neutral observation, ethnographers replaced amateur travelers, traders, colonial administrators, and physicians, and missionaries as authoritative producers of knowledge about the customs, beliefs, and languages of indigenous peoples. At the same time, linguists were engaged in an intensive project of construction and standardization of African languages, mapping language onto primordial tribal territories and cultural units. 77. It is important to emphasize that this was a messy and incoherent process on the ground. Mozambique was not Leopold's Congo. Nonetheless, ordering projects, be they political, anthropological, linguistic, or biological in nature, erase the complicated reality that people have always been interacting, exchanging goods, social ideas, culture, and genes. Goodman 2007. While socio-cultural exchanges took a particularly violent form in 19th and 20th century colonial interventions in Africa, which profoundly and irreversibly shaped the constitution of groups on this continent, colonialism did not initiate the movement and mixing of peoples. Historical analysis demonstrates that populations are not now and never were isolated, bounded entities. They are in reality actively produced social formations appearing, disappearing, and reappearing over time as part of global socio-scientific projects. Rather than a continent peopled by timeless relics of a tribal past, Africa, like all continents, is built on a mosaic of groups, which incorporates people of different language affiliations. It involved extremely sophisticated ritual, economic, and technological accommodations to a diverse and changing natural and cultural milieu. It allowed for processes of immigration, emigration, and population interchange. McEachern 2000, 363. The legacy of work in the human sciences from the first half of the 20th century, which is almost invisible and unknown to present-day researchers, profoundly shapes contemporary genetic research protocols, whether they deploy racial typologies or finer-grained microgroups. Just as nothing less than state-of-the-art statistical or basic science methodologies would be acceptable to biomedical scientists, the basic unit of analysis, this very first step in conducting population studies, must be subjected to rigorous scrutiny. This begins with the difficult process of uncovering the rich history of the making and remaking of populations and how they are defined and understood. The informationalization of race, communication, databases, and the digital coding of the genome. Peter A. Chow White. 81. In our time at the end of the 20th century, the crisis of race is still raging. In this age of globalization, with its impressive scientific and technological innovations in information, communication, and applied biology, a focus on the lingering effects of racism seems outdated and antiquated. The global cultural bazaar of entertainment and enjoyment, the global shopping mall of advertising and marketing, the global workplace of blue-collar and white-collar employment, and the global financial network of computerized transactions and mega-corporate mergers appear to render any talk about race irrelevant. West and Gates 1997, 68. Something is happening to race. Fausto Sterling 2003, 1. In 2005, a series of publications signaled a new phase of the biopolitics of the human body. In March, an evolutionary developmental biologist wrote an op-ed piece in the New York Times that ran contrary to standing assumptions about race as a social construct. He argued that new scientific evidence has been emerging that showed genetically identifiable racial differences. The next month, a story in the same periodical described how students in an introductory sociology class were taking a DNA test to determine their genetic ancestry by comparing their DNA to 4 parent populations: Western European, West African, East Asian and Indigenous American. Finally, in October, the results from the first phase of the Next Human Genome Project, the HapMap project, were published in the journal Nature. In 2000, leaders of the Human Genome Project concluded that humanity is genetically 99.9% the same and that race is indeed a social construct and not a biological one. However, one of the goals of HapMap has been to map the haplotype groups, or neighborhoods of genome variation, of individuals from different population groups, African, Asian, and European. The HapMap results showed, in figures vividly color-coded in green, orange, and purple, genetic variation between these groups. Instead of following the Millennium Declaration that race has no biological basis, increasing numbers of scientific studies are discovering how race is meaningful at the genetic level. If the late 20th century was characterized by the deconstruction of race, then it is being reconstructed around a biomedical and informational paradigm at the beginning of the 21st century. This development is not simply the result of scientists acting with ideological blinders or the return of the racial science of the 19th century. The context for the genomic turn in racial identity lies at the convergence of race and new technologies. As race becomes twice recoded, in terms of culture or what some refer to as the new racism, Barker 1982, Collins 2004, and into the Internet and other related information and communication technologies, Hammonds 1997, Kalko et al. 2000, Nakamura 2002, 2008, discourses about race are being reimagined. Research into race and digital culture has shown how new technologies reinforce old forms of racial identity in new ways that are less obvious than previous media forms, Nakamura 2008. The conditions for identity building have shifted, as new social, political, and economic formations emerge in and through new media and technoscapes, shaped most significantly by the Internet. This essay examines how the convergence of changing concepts of race with information technologies has produced a new paradigm for race. This paradigm, while it emerges in discourses of the information age that present themselves as colorblind, is, I argue, in fact productive of new regimes of racial knowledge that are oriented around the digital cultures of communication technologies, especially the Internet and databases, both in everyday practices and social institutions. An important area in which to investigate how race is being recoded via culture and technology is human genomics. This burgeoning field has been referred to as an information science because communication technologies, such as computers, the Internet, and digital databases, are essential for sequencing DNA. Without them, genome science would be virtually impossible. It is the meeting ground for genetic, computer, and racial codes and is both challenging preconceived notions of racial meaning and reproducing racial classification. For example, where Craig Venter and Francis Collins, the leaders of the private Celera Genome Project and Public Human Genome Project, HGP, concluded that we are all 99.9% the same at the genetic level, the next HGP, the International HapMap Project, is mapping differences between African, Asian, and European groups. Drawing on interviews with members of the HapMap Project 2 and textual data from biomedical and scientific journals, this study examines technological innovation and cultural and scientific discourses in genomics. 3 utopian visions of this emerging biotechnology suggested that scientists would be able to see into the human body in new ways and begin to map and manipulate. 82. The very building blocks of life to improve health. However, genome research into group differences is also a crucial site of negotiation in the relationship between race and technology. The informationalization of race. Critical scholars have divided racialization into 2 interdependent ontological paradigms, race as biology and race as culture. In the race as biology paradigm, racial groups are identified according to a collection of physical phenotypes, such as skin color, hair texture, shape of eyes and nose, and then tied to a hierarchical order of racial groups with whites at the top ranging to blacks at the bottom. Banton 1998, Jordan 1974, Miles 1989. The formative process of racialization has been linked to the rise of Enlightenment thought, Ease 1997, spread of European colonialism, Césaire 1972, Fanon 1963, 1967, Memmi 1965, Slavery, Jordan 1974, and Scientific Racism, Barkin 1992, Gould 1996, Moss 1978, Stepan 1982. In the post-civil rights era, biological classification shifted to cultural codes, a development that has been referred to as the culturalization of race, Race Act 1998, or the New Racism, Barker 1982, Collins 2004. Group characteristics continue to be ascribed based on a symbolics of the body. Yet the real differences between groups are no longer biological but rather ethnic or cultural. Cultural notions of race are deployed in a manner similar to those of biological ones, homogeneous, dislocated from historical context, static, and containing an implicit association to group position in the social order, a fixed property of social groups, rather than something intrinsically fluid, changing, unstable, and dynamic. Gilroy 2000, 266. Racial signification is re-articulated in cultural terms, where everyday talk and political statements about the cultural characteristics of a particular group often are thinly disguised racial claims. Kim argues that the move to culturally coded racial discourse has in fact stabilized white privilege in the post-civil rights era. It is precisely because it has been revamped in non-racial language that the field of racial positions functions so effectively to reinforce white privilege today. Representing a cultural explanation for group inequalities, the field of racial positions implies that American society is substantially colorblind and that the American dream is still viable. Kim 1999, 117. Scholars refer to the dominant racial ideology characterized by coded discourse about race as colorblind racism, Bonilla Silva 2003, and colorblindness, Brown et al. 2003, Wellman 2003. Bonilla Silva, 2001, suggests that the civil rights movement marked a change in the racialized social system from Jim Crow racism to colorblind racism. In the former phase, blacks and other minorities were considered inferior to whites because of their biological and moral inferiority. One of the most significant changes in the post-civil rights era is the non-racial and cultural terms in which racial differences are articulated in the public sphere. Bonilla Silva, 2001, describes race talk during the Jim Crow era as direct and blunt. 68. Racial claims now tend to be made indirectly. Hockey. 83. basketball, special interests, inner city, thug, welfare, and sickle cell disease are racially coded in a colorblind manner. Instead of the terms of inclusion and exclusion, superiority and inferiority being based in genetics, a group's success in society is reliant on their cultural competency. Many even speak of a post-racial society. In spite of the continued existence of racial inequality in terms of social, economic, and political power, what Lipsitz, 1998, refers to as the possessive investment of whiteness, the turn to colorblind racism attributes differential standings of minorities to market forces, naturally occurring phenomena. Segregation is natural, because people want to live with others who are like them, what Tagif 1990 refers to as the biologization of culture, and cultural variations between groups. Bonilla Silva 2003, 2. A new regime of racial signification characterized by the creation and deployment of information is emerging through the digital space of communication networks, computer codes, computational algorithms, and databases. New communication technologies increasingly make up the central media systems in which racial meanings are created, transformed, and destroyed, to borrow from Omi and Wynant, 1994. This network system is not simply a delivery tool for ideas and meanings. Its very structure and scope, both hypertext and globally linked, is productive of new mechanisms of racialization. Where conventional conceptions of race have been articulated in terms of culture or phenotype, in the digital age information is the material by which racial meaning is worked on. However, race as information does not replace the dependency of racialization on ethnicity or skin color. Rather, as the paradigm of race as culture emerged from the paradigm of race as biology, I would argue that the paradigm of race as information has emerged from both. I call this new racial formation the informationalization of race. What distinguishes race as information from other modes of racialization is the transformation of society due to globalization, the new economy, and communication technologies. Racial identity, meanings, and structures are being created through the use and shaping of new media and communication technologies. The informationalization of race acknowledges that race as a structuring device in society has not diminished in importance with the information age and has continuity with modernity. While at the same time, this research seeks to examine new mechanisms of racialization that are an effect of innovations and applications of communication technologies and the rise of information in a post-civil rights context. In one of the first books on race and new media technologies, Kalko, Nakamura, and Rodman show that, in spite of utopian visions of fluid online identities, race matters no less in cyberspace than it does IRL, in real life. 2004. See also Nakamura 2002. This is significantly different from previous forms of the social construction of race as the body becomes post-human, Hales 1999. That is, the meat has been left behind and cultural signification has become 84. Embedded in computer programs and complex algorithms, hidden from the front end, user interfaces. In an early example of this process, Hammonds, 1997, describes a computer program that could morph people into different races and create entirely new people from an amalgam of a number of facial features of different racialized groups. Rather than deconstructing biological notions of race, she argues, they reinforce centuries-old stereotypes of racial difference and cultural anxieties of miscegenation. Ideologies of bio-race were translated into the seemingly neutral space of the digital. As a space of new media, the Internet has been used to translate racist ideology online and as a site of contestation over racialized identities. Where traditional media, film, television, etc., have been largely one-way media that excluded or marginalized people of color, cyberspace's unique architecture enables the building of communities among minority and transnational groups across time and space. Linda Leung, 2005, explores the presence and community building of racialized minorities in representation, production, and consumption in cyberspace. In an empirical analysis of a research project based in East London called Project Athene, she finds that, although the World Wide Web is dominated by a white, Western-centric notion of technology and media, there are significant points of participation where people from minority groups can and do challenge dominant ideologies of race and ethnicity, either directly or indirectly. Similarly, Gray, 2005, shows how groups such as the Afrofuturists, a movement made up of a loose collection of artists, musicians, writers, and critics, utilize the global networked architecture of cyberspace to stitch together and create cultural production in the digital Black Atlantic. See also Nelson 2002. The computational routines that produce racial representations are new technologies of race, translating ideologies of biorace into the seeming neutrality of digital space. As cultural and phenotypic signification meet computer code, the analog systems of racial signification enter the digital world, producing new modalities as well as reproducing old ones. Traditional media analyses of the mechanisms of racialization tend to focus on representation in television, film, and news. Scholars, such as Vaidyanathan, 2006, working between a number of academic fields, suggest that asking critical questions about the nature, uses, and global flows of information is a crucial practice in understanding emerging relationships between technologies, social norms, and democracy. The concept of the informationalization of race directs attention to the algorithms, data, and discourses produced in the hypertext communication environments of computers, databases, data mining, and the Internet. Unlike the more visible forms of new media technologies such as the mobile phone, the laptop computer, and the iPod, or invisible delivery systems such as Wi-Fi or the web, the database is a central innovation in the information economy. Elmer 2004, see also Qubit 2000, Loro 1995, Minovich 1999, Poster 1991. 85. Similar to old media forms, like the novel, film, or television, the database is a new media technology that structures our personal and institutional experiences both symbolically and materially. Differing from these largely one-way media, databases enable a networked multilog, Loro 1995, 55, between producers and consumers through the process of sorting and storing data, networking information, and constructing knowledge. Data mining is a technique for searching and creating knowledge out of digital databases, KDD. Derived from the computer sciences, data mining is a step in discovering knowledge in data. Within specified parameters, computers program search databases using mathematical algorithms to find significant patterns. Data mining techniques are made up of sophisticated algorithms, neural networks, and artificial intelligence. They can work from predetermined sets of categorical variables, or they can go beyond what a user knows in order to request and discover unseen patterns, facts, or relationships between the data. Dana and Gandhi 2002, Zarsky 2003. As the Internet has been employed by government agencies and marketing firms to gather information on citizens and customers, the goals for data mining have increasingly moved from description to prediction. Gandhi 2006. Companies across all business sectors, from grocery shopping to Amazon.com to genetic services, employ databases and data mining to find out characteristics about their clientele. In order to provide personalized services, firms collect demographic and behavioral data on individuals and groups to understand who they are, what they like, and their future buying potential. The term informationalization builds on the insights of the literature on surveillance and the information society that examines the shift in societies from industrial economies to services economies due to the restructuring of capitalism, the new technological paradigm, and globalization. Webster 2002. Informationalism is a specific form of social organization in which information generation, processing, and transmission become the fundamental resources of productivity and power. Castells 2000, 21. Traditionally, the concept of information denotes a neutral set of facts, data, or observations. When information is networked and takes on the form of an information infrastructure, such as when databases are compiled and linked or the seemingly endless pathways of the World Wide Web, it should not be treated as having a simply reflective role in the social world. Like other media forms, news, television, film, Information infrastructures do not just support cultural, political, social, and scientific processes. They play a constitutive role. It is politically and ethically crucial to recognize the vital role of infrastructures in the built moral environment. Seemingly purely technical issues like how to name things and how to store data in fact constitute much of what we have come to know as natural. Boker and Starr 1999, 326. Technologies and the classification systems that use them tend to make invisible the myriad of decisions that create them. We, the users, see only the interface, the front end of a particular technology. Hidden away inside are the attitudes, values, and politics that are written into code and the arguments, decisions, uncertainties. 86. And processual nature of decision-making, Boker and Starr 1999, 187, see also Garfinkel 2000. Put another way, the seemingly descriptive representations derived from information infrastructures in fact naturalize a whole set of practices, procedures, and ideological premises. Looked at historically, information seems basic to social life. In modern, literate cultures, artificial signs proliferate, and are frequently associated with social order itself. Signs tell us of distant events, places, persons, and processes. Information is relational, connecting by reference persons and things. But whereas information might once have thrown light on reality, or even, through instructions or recipes, contributed to the transformation of reality, once technological devices become the predominant carriers of information, the distinctions blur. Lyon 2005, 225. Information has moved from being factual, to being technical, to being a commodity and a basis for social, technical, political, and cultural organization. Castells argues that it is not only the centrality of knowledge and information that characterizes the current technological revolution, but the application of such knowledge and information to knowledge generation and information processing/communication devices, in a cumulative feedback loop between innovation and the uses of innovation. Castells 2000, 31. Race as information brings into the fore new forms of racialization that previous concepts, such as race as the body, race as nation, race as culture do not. When cultural codes meet computer code, programming and distributed networks have become the new sites of negotiation over norms and the terms of social inclusion and exclusion. As Galloway and Thacker suggest about the logic of the network society, codification, not reification is the new concern. 2007, 134. Where racialization has been about the reduction of cultural practices and social relations to objects, the informationalization of race looks to where bodies and practices become code. This could be in the form of state surveillance, bioprospecting, or self-expression online such as Facebook. At all levels of society, from institutions to individual identities, information has become the material that social and political meaning is constructed in, new companies profit from, and states utilize to govern over. This is a crucial development for the study of racial formations. This research seeks to examine how innovations and applications of communication technologies and the rise of information have produced new mechanisms of racialization in a post-civil rights context. Scholars have pointed out that race has not decreased in significance, but persisted and transformed into colorblind racism. As communication technologies play an increasingly centralized role in the everyday practices and organization of a range of social institutions and industries, there are a number of sites where we can see the informationalization of race at work, such as law enforcement, biomedical research, insurance, and marketing. While each would have its own set of technologies for information storage, classification, and surveillance. 87. They have increasingly employed a similar array of technologies to their own institutional needs and goals. Where the microscope has been a central observational tool in the biomedical sciences, actuarial tables in insurance, and fingerprinting in law enforcement, data mining techniques and the technological infrastructure that it requires are commonly used across these different sectors. Their methods of observation, classification, and knowledge production have incorporated networked, digital, and informational processes. This research explores developments in biomedical research into DNA. In molecular biology, Mackenzie questions the usefulness and the point of tracking computational processing of sequence data, which heavily utilize new media such as the Internet and databases for storage, analysis, and distribution. Does not bioinformatics merely support the more decisive intellectual, social, political, cultural and economics events associated with contemporary biology and genetics? 2003, 316. While scientists debate the accuracy or inaccuracy of scientific data, which is the outcome of computational and statistical routines, it is important to understand how those outcomes stitch together cultural assumptions, molecular particles, microprocessed bits and bytes, and historical context. In what follows, I explore how genomics, the study of DNA, is an effect of the informationalization of race. Biology as an information science and the human genome. There has been a concurrent ascendance of the information society and genetic technologies, Capra 2002, Castells 2000, Myers and Davis 2003. Computer science and genetics have converged to the point where biologists, computer scientists, and engineers work side by side, borrowing from one another both methodologically and theoretically, Marcherano and Chadwick 2004. Modern science relies to a very large extent on computer simulations, computational models, and analyses of large data sets where genetic data points can number in the billions, such as in the case of the Human Genome Project, Gazelter 1999. Genetic technologies are information technologies, since they are focused on the decoding and eventually reprogramming of DNA, the information code of living matter, Moody 2004, Thacker 2004. And, more important, without massive computing power and the simulation capacity provided by advanced software, the HGP would not have been completed, nor would scientists be able to identify specific functions and the locations of specific genes. Castells 2001 p. 164. In addition to this, some philosophical problems arise from the view that DNA and the human genome are pure informational concepts. In one sense, the convergence between the biological and computing might be thought to be associated with the massive use of computer technologies in biology. Computers are convenient tools for genome and protein sequencing. However, the bioinformatics paradigm has been central to the reorganization of disciplines such as molecular biology, Holdsworth 1999. In the process, they have absorbed Shannon's technical notion of information. Genome science has emerged as the next wave of human scientific research. There are a number of important ways that genomics differs from genetics. Genetics 88 is the study of genes and the inherited differences and variation in DNA and its influence on phenotypes. Interview 1001, Interview 1022. The Department of Energy's Human Genome Project website defines genomics as the study of genes and their function, as well as their interactions with environmental factors. Interview 1022. Genome Canada calls genomics big picture science, whose central aim is to understand the complexity of how genes interact with each other and their environment to make living organisms function. 5. Genomics is largely driven by the impetus to understand the differences in genomes, such as the variations in sequences at the same locations in a DNA strand, between different individuals and population groups, and the origins of complex diseases such as cancer. Where genetics looks at individual genes, genomics focuses on the entire collection of the 6 billion chemical bases, the As, Cs, Gs, and Ts, that are strung together in our 23 pairs of chromosomes. These more technical definitions based in biology miss some important technological, social, and cultural characteristics of genomics. One of the main challenges of genomics is the enormous amount of data involved in studying the 3 billion letters of code in a strand of human DNA and the sheer number of relevant variables that has necessitated an enabling link to computing. Developing from the convergence of molecular biology and computing science, genomics can also be defined as the computer-assisted comprehensive study of all genes. Interview 1001. Like many new technologies, boosterism about its scientific potential leads into possible social benefits. Francis Collins, the former director of the National Human Genome Research Institute, NGRI, one of the National Institutes of Health, states about the promises of genomics for society. Genomics has been at the forefront of giving serious attention to the impact of science and technology on society. Although the major benefits to be realized from genomics are in the area of health, genomics can also contribute to other aspects of society. Just as the Human Genome Project and related developments have spawned new areas of research in basic biology and in health, they have also created opportunities for research on social issues, even to the extent of understanding more fully how we define ourselves and each other. Collins 2003, 483. Evelyn Fox Keller, 2000, has shown how the importance and prominence of gene thinking grew in scientific and popular discourse during the 20th century. Genome thinking may be growing at an even faster rate as we have entered the genome era, Bonham et al. 2005, 9. While genetics emerged from the insights of Mendel and the scientific practice of observation by sight, which are analog practices, genomics is emblematic of a cultural shift in scientific practice characterized by digital observation, data mining analysis, and computer automation. If the 20th century was the century of the gene, then the 21st may well be shaping up to become the century of the genome. 89. Genomics goes global, the international HapMap project and database networks. I don't think HapMap could have happened without the internet, honestly. Interview 1016. I think that, in fact, in many circles genomic research has been discussed as developing out of DNA technology. I think it is fair to say that the entire concept of genomics, which is really one of data-rich studies in biology where you have archival quality data that is comprehensive and is shared freely, is as much about, if not more about, computers and the internet as it is about DNA technology. Interview 1001. A key site to examine the intersection of science, bioinformatics, communication technologies, and racialized identity is the next HGP, the International HapMap Project. The project is a multi-site, international venture between scientific teams in Canada, China, Japan, Nigeria, the United Kingdom, and the United States. The project is in the process of mapping haplotypes of human genomes. Haplotypes are identifiable block-like patterns of the DNA nucleotides, A, C, G, and T. A genome consists of individually sequenced strings of nucleotides. The aim of the HGP was to create a comprehensive map sequence of an individual's DNA. In 2001, scientists shifted the focus to haplotypes in the genome. Haplotypes are neighborhoods of DNA that can be identified by common genetic variants in the genome sequence, revealing an underlying structure in a genome. Identifying the locations of the variants, called single nucleotide polymorphisms, or SNPs, can facilitate and speed up subsequent research into the genetic origins of disease. International HapMap Consortium 2003. Since the project began in 2001, Phase I and Phase II of the project sampled groups from Europe, Africa, and Asia, China and Japan. Where the organizers of the HGP declared humanity's genetic similarity, HapMap searches for differences. Like the HGP before, communication technologies are at the heart of mapping, sequencing, and data gathering, storage, analysis, and distribution. Information sharing, data transfer, and analysis operate on a global scale from the sample collection sites in Africa, Asia, and North America to the sequencing and research centers. As the project's network of labs are scattered across the globe, the only way for genome scientists to construct a haplotype map of major geographical groups, as they are named in the project, is to disassemble DNA into digital packets, send them through the internet, and reassemble them in a SNP database. Each team of the HapMap project sequences a portion of the genome, such as chromosome 2 and chromosome 4p by the McGill University/Genome Quebec Group in Canada, chromosome 7p by the group at Washington University in St. Louis and the University of San Francisco, or others, both academic labs and biotechnology companies in China, Japan, and the United Kingdom. The data from each group is collected, curated, and stored for distribution in a database in 90. Bethesda, Maryland, at the National Institutes of Health and released online for public access within 24 hours. The scientists' most important tools for the collection, databasing, and manipulation of genome sequences are communication technologies. With the interaction of computer science and molecular biology, genomics has moved biomedical research to computational biology. Interview 1006. Accordingly, a number of respondents agreed that, without the rich, flexible, and networked databases, as well as increasing speeds of computing, the impact of genomics would be trivial compared to what it is today. Developments in genomics are as much feats of technological management, archiving, and distribution as advances in scientific knowledge. Interview 1001. Genomics simply would not be feasible by hand, which would make it impossible to analyze a single genome or make comparisons between individuals, groups, or even species. Interview 1003, Interview 1011. HapMap participants commonly discussed two technological developments in particular, databases/data mining and the Internet. New databases have been designed to store, analyze, and distribute the data and findings. Data mining techniques and large, easily accessible databases that would allow the extraction and comparison of data were absolutely essential for being able to put together any kind of sequence database. Interview 1014. The Internet enables genome projects to move data between global locations and labs in the same building, as well as providing open access for anyone interested in the data. These large-scale information infrastructures are the back end of scientific information. They are referenced, but not normally discussed, in the scientific journals and media stories about scientific discovery. Further, they have become new technologies of difference in the informationalization of race and crucial to the new information science. According to Leroy Hood, an early developer of sequencing technology in the 1980s, the genome posed such enormous technological challenges with sequencing, mapping, computation, analysis that a new paradigm, discovery science, was needed to tackle the obstacles posed by building and analyzing a comprehensive database. Developed during the heady years of the Human Genome Project, discovery science utilizes KDD to reorganize and sequence the haplotype blocks. Much like the basic assumptions of data mining described above, discovery science takes an object of analysis, such as a strand of DNA, and defines and collects all of the elements in it, rather than sampling or sequencing only part of it, and puts all the information in a database. In contrast to the meticulous method of making theoretically sound hypotheses before collecting and analyzing data, discovery science is more of a collect first and asks questions later approach. Craig Venter and the Celera Genome Project innovated a procedure called the shotgun method. As Internet protocols and capacity grew in the 1990s, the new communication infrastructure became a key conduit for moving data. In the HapMap project, the Internet allowed researchers to upload data from local sites and sequencing centers to the centralized database in Bethesda. 91. The HapMap Consortium collected samples from populations with ancestry from parts of Africa, Asia, and Europe. International HapMap Consortium 2003, 789. While project organizers deliberately decided to refer to the sample groups in terms of populations and not racial groups, the initial groups do match a traditional American taxonomy of race. Lee, 2005, points out that choosing such geographically disparate groups accentuates any genetic distances/differences, rather than using more gradual differences between more historically proximate groups. The gradual differences, she argues, might uproot conventional notions of racial boundaries and inspire new trajectories of research that dispense with age-old notions of racial difference. Lee 2005, 2135. This reinforces the racial triangle of Black, White, and Asian. When the National Human Genome Research Institute, NGRI, of the National Institutes of Health, NIH, decided to build databases in a haplotype map, the scientists involved had to make a decision on which markers would be included. They decided that the groups would be labeled according to geographical, rather than racial, signifiers. I have been told that the discussions at the preliminary HapMap meetings held in the summer of 2001 were very open about the issue of racial identification. When asked about the place of race in the schedule of items being discussed and whether or not it was an important issue or a marginal one, a bioethicist in attendance commented that it was in the fabric of the meeting. Another attendee described the discussions of race and community as at an elementary level. It's been an educational process for some, especially the genetic scientists, but also for the people involved in all aspects. Some scientists were using East Asian or even Asian as a name for the Japanese and Han Chinese sample. We insisted that this is inappropriate, as Asia includes too many different groups, I mean thousands of different groups. China itself includes 50 groups, and you can't call people like this. Therefore we adopted the name JPT, and it was a long discussion, and I think everyone had a kind of contention on this in the end. I think the question of concern about racial discrimination and classifying these HapMap samples in that way was a serious concern for everyone involved. That was the reason for the care in taking the naming of the samples. Inside Japan, I don't think the concern is of any discrimination of Japanese people in Japan. The concern for the Japanese people is discrimination when the population exists as a minority, for example in the Americas or Europe or Asia, or other Asian countries anywhere. Interview 1011. By making a shift from biological notions of race to geographic ones, scientists seem to be making a return to the Linnean racial classification systems of the 18th century, Banton 1988. I would suggest that the impetus for this return is not entirely ideological and may be the result of the emerging ability that communication technologies enable for genome sequencing and more fine-grained analysis of genetic differences. The HapMap database is an effect of the 92. Digital age and new processes of knowledge construction in the discipline of science. When interviewed, most HapMap members are quick to point out that they do not use race but geographical ancestry to define the population groups. Not all the members referred to the groups by geographic ancestry, however. A white statistical geneticist suggested equivalence between the three sort of major continental groups or racial groups or whatever your preferred term is. Interview 1002. When differences in a selected haplotype sequence, patterns of SNPs or single nucleotide polymorphisms, between these three groups are reported, this can easily suggest, especially in the context of a racialized society, the conclusion that the differences are racial, genetic, and biological. For example, Hines et al. 2005, report on whole genome patterns of DNA variation between these three population groups and examine millions of SNPs. While this number seems rather large, the total number of individuals from whom the samples were collected was 71, which is a very low sample size to assess any variation between groups. Further, when scientists collect and name the samples and enter them into databases, the distinctions they make between the social and scientific meanings of race are not clear. Wiley 2007a, 2007b. Lee raises a more important question. If there is no genetic basis for race, then why do large-scale mapping projects continue to use racial categories in identifying research populations? 2005, 2135, see also S. Lee, Chapter 10 in this volume. The answer lies partly in the tradition of population genetics and physical anthropology that provides the scientific basis for choosing the four groups. Clearly, there was an opportunity lost in debunking the relationship between genes and race by choosing populations that are geographically distant from one another, rather than ones closer together genetically and geographically. In addition, and this is an equally important issue for identity, there are socio-political opportunities for states who participate in large-scale genome projects. China and Japan have been eager to assert themselves, not only regionally, as leading countries geopolitically in Asia, but on the world stage. Nigeria occupies a similar position in Africa. HapMap organizers chose groups that were either already being engaged in some genetic research, or they were groups that researchers had already a relationship or a collaboration with these groups or with persons in those communities. They had contacts. They reconsented most of the people who were alive or whose families were part of CEPH. With the other populations, the Chinese population and the Japanese, those populations, the specific populations, the groups that were targeted, well, I shouldn't say targeted, were identified and participated, were really groups where there was some contact or some existing collaboration with those groups, for some researchers who was doing some research for that group or that community or a collaborator in that community. Interview 1022. 93. Choosing the research sites and initial sample populations in the case of HapMap were matters of convenience and accessibility, Duster 2005. This is a common occurrence across the natural and social sciences. As the dominant organizing principle in the information age is the network, power operates through the space of flows. In the case of HapMap, flows of scientific knowledge and social/professional networks are accessible to scholars and states who can tap into them. In the early 1990s, Gilbert warned that the proliferation of databases would create a digital divide. The next tenfold increase in the amount of information in the databases will divide the world into haves and have-nots, unless each of us connects to that information and learns how to sift through it for the parts we need, quoted in Lenore 1999, 18. For example, Cambodia or Vietnam were not chosen or targeted to represent Asia, nor was Sierra Leone for Africa, because HapMap organizers did not have relationships with anyone there and state governments lacked the funds or the international political capital to participate in the new global venture. However, some members see the data coming out of HapMap as being able to overcome this kind of digital divide. I think it's an opportunity for the West and the industrialized economies to efficiently transfer the intellectual benefits of wealth and investment and this technology to the developing world. There's no reason that South Africa has to resequence the human genome to study the parts that are relevant to urban disease there. They can leverage off of what we've done internationally. So, I think that's a fantastic opportunity for international science and humanities as a whole. I think science can bridge boundaries in a way that other cultural enterprises can't do. Interview 1016. Conclusion. As the information age advances and analog social, cultural, and scientific practices are recoded into the digital networks of global communication, the transformation of racial identity and signifying systems pose new challenges for scholars of race and science. In the case of genomics and the HapMap project, the informationalization of race signals a shift in the way that big science is conducted, how the materials used for analysis have become digital information, and how this process is sorting people in new, and old, ways. Many scholars and activists assumed that the decoupling of race and biology and the enclosure of racial identity in a social constructivist paradigm was a fait accompli at the close of the 20th century. However, rather than destroying race as a biological category and providing conclusive proof that we are indeed all the same, as the UNESCO statements after World War II tried to establish and leaders of the Human Genome Project proclaimed 50 years later, the specter of genetic differences that distinguish human groups has not only been raised once again, but given new currency. 94. The context for this gene war of maneuver is not slavery and colonialization in the 18th century, or scientific racism in the 19th century, or the eugenics movement in the first half of the 20th century. At the beginning of the 21st century, new genomic forms of racial knowledge are emerging at the convergence of multiculturalism and the ideology of colorblindness, new database and digital communication networks, globalization, and the ascendancy of biology. Both citizens and scholars need to be a part of this struggle over the nature of defining who we are at the most basic level of human life. The main challenges for those who are against biorace are on two fronts, one socio-technological and one socio-scientific. First, the processes of creating, storing, and transmitting information have become resources for the production of power. The policies, politics, and procedures that make up information infrastructures are hidden in the seeming neutrality of codes and standards. We, the users, only see the interface. Information and the networks that compose a communication infrastructure are much more than the denotative transmission of facts, computer algorithms, and data. Information is not simply descriptive and reflective of the social world. The collection, storage, and analysis of information constitutes what is known and what can be imagined, both of these bases for social action. Information in the global new economy is deeply connotative. In this respect, race as information works in a similar manner to race as culture or race as the epidermal body. However, due to the hypertext of the Internet and the anti-narrative logic of databases and related new media technologies, information is much more contingent and fluid. Critical scholars of race need to continue to address the role of new technologies and new media in the process of racialization and engage in larger debates about surveillance, privacy, and personal information, and intellectual property. The socio-scientific front, like the socio-techno, is well underway. The 5% of funding allocated to social science and humanities research remains in place at the NIH's National Human Genome Research Institute. Public genome projects, such as HapMap, have built into them ethical, legal, and social implications. ELSI, committees made up of interdisciplinary teams composed of scientists, NGOs, bioethicists, lawyers, sociologists, and anthropologists. The Canadian version of ELSI, called GE3LS, sets aside a similar amount of funding, while some social science researchers have managed to secure 10% in their collaborations with applied genomics projects. Genome British Columbia goes a step further by funding applied genomics research projects where there is an integrated social science or humanities (SSH) component. At the proposal level, this has meant that the SSH researcher stands as a CO applicant. It is crucial that this type of configuration continues. With all these provisions and points of contact between the natural and social sciences in place, we are still seeing research results from the HapMap database being reported in prominent publications, such as Science, with declarations 95. Such as in Asians and Whites, gene expression varies by race, Kuzin 2007, 173. This startling article was followed up the next month, where a letter to the editor states, "Race is truly a biological and taxonomic problem." Billinger 2007, 766. Interestingly, while many science publications, including Nature, have instituted editorial policies on the use of race in research, Science still does not. In the absence of such a policy, letters to the editor could be sent to point out the uncritical use of race and ethnicity in such articles and research reports. Similarly, at the point when scientific findings are translated to the public, usually through the news media, editors should be notified and supported when stories such as Amy Harmon's New York Times article in DNA Era, New Worries About Prejudice, 2007, are published. Similarly, we can send words of support to politicians when they make statements against racism, such as Mayor of London's censure of James Watson's comments in 2007. Also, there are a number of NGOs, such as GeneWatch in the United Kingdom and the Council for Responsible Genetics and the Indigenous Peoples Council on Biocolonialism in the United States, who work in the public interest by monitoring scientific research, publishing working papers and newsletters, and representing various community stakeholders. While ethical, legal, and social implications, ELSI, committees attached to genome projects such as HapMap are made cognizant of issues of identity, community consent, and privacy, the role and meaning of new technologies are usually assumed to be instrumental. There is little discussion of the ethical, legal, and social implications of new communication technologies. While the technological utopianism of the 1990s has been replaced by more tempered approaches to the benefits of Web 2.0 that alternate between empowerment and participation on the one hand and surveillance and control on the other, we have seen that the rise of the Internet has not meant the end of racial identities. As research has shown, practices of race are at the same time transcribed and transcoded into cyberspace as well as lived there and here in RL. Further, the seeming neutrality of data mining techniques and database construction is also dependent on the nature of the data and algorithms that tells programs what to do. The standards and codes that make the design infrastructure of databases and related technologies shape their function and meaning at the user interface. In the case of genome and DNA databases, race is inscribed into the front and back ends of the technology. The need for theoretical connections between technology and race from observations of the biomedical sciences is particularly important at this time. With the turn to the 0.1% of the genome that differentiates one person from another, there are over 3 million points of difference that are under intense scrutiny as governments and companies create public and private haplotype maps. DNA as an object of knowledge is not only of interest to molecular biologists. DNA databases are being compiled by law enforcement agencies at both the national and local levels, such as the FBI's CODIS database, and by ancestry companies and biotechnology companies working on pharmaceuticals. 96. The authors in this section explore DNA technologies and instantiations of the informationalization of race in a number of enterprises. Pamela Sankar discusses forensic DNA phenotyping technologies, FDP, that are being developed by law enforcement agencies to visualize DNA evidence. Where DNA evidence is used to confirm the identity of suspects, FDP, by contrast, uses genetic code to predict what the yet-to-be apprehended suspect looks like in terms of facial features and other observable phenotypes. In the courts, John Kahn argues that the validity of DNA evidence is largely taken for granted in identifying suspects and predicting race and ethnicity. His chapter highlights the lack of attention to the technical complexities of using race and ethnicity as a genetic concept by showing, in part, how the informational procedures of coding genetic regions for race have changed since the early 1990s. Lee examines how genomics databases are shaped in the field of pharmacogenomics, which is the application of human genome variation research to the development of genome-based drugs that scientists hope will increase efficacy and safety for patients and reduce adverse reactions. While this type of research has been heralded as a major step in the direction of personalized medicine, tailored to an individual's genetic code, Lee suggests that, since the expense of sequencing technology is still prohibitive for a mass market, scientists tend to focus on differences at the level of populations. This type of focus is producing a growing literature on genetic differences between groups that are coded as African, Asian, and Caucasian. The databases for these various enterprises based on DNA information are built by both public and private organizations. While the public projects operate under the ethos of open access in an effort to democratize the data and community consent models, private firms are under no obligation to adopt such policies. This should be cause for concern, especially as the mapping of DNA turns to the function of DNA. One of the white scientists who has been particularly outspoken about the focus on race in HapMap suggested that ongoing discussions about racialization in genomics is regressive and that people who suggest the HapMap project and other genome mapping ventures can and will reproduce race are naysayers. However, the same scientist offered a future implication of genomics. He suggested to me, the rubber has not really hit the road yet. For him, the ancestral information that may be contained in DNA is a superficial issue. Genome maps of human populations are not productive of or reproducing the scientific racism of the past or reifying race. Knowing where your mother came from through your mitochondria does not say much except what our geographical origins may be. This may be true if one removes social and historical context of that information. However, as I argue in this essay, such knowledge contributes to and is produced in discursive formations of the informationalization of race. The interviewee continued. But what is going to be problematic and we're not prepared to deal with is what if, or not what if because it will happen. What about when someone does find a gene that does affect a trait of high interest that's not medical? 97. Perhaps but sort of behavioral, and that gene variant is not equally represented across different ethnic groups, all of a sudden we won't be in this confused sort of meaningless realm we've been in to some extent, we're going to be in a new realm where there are genes that affect traits and they're not evenly distributed across populations. Then we're going to have a real problem. Interview 1001. This particular problem is surfacing at a time when science, technology, and race are interacting in new ways. The informationalization of race attempts to understand this transformation by recognizing that technological, scientific, and cultural change are not separate processes but are intimately bound up with one another. In order to avoid returning to the altar of biological determinism, debates about genomics and race need to be expanded to incorporate technology beyond simple mentions of the presence of supercomputers in genomic research and their usefulness for sequencing DNA faster and cheaper. Like old media forms, new media technologies, such as databases and the Internet, are sites of negotiation over cultural meaning, social facts, and the politics of racial representation. Appendix. A number of the individuals interviewed were principal investigators of the various research sites. A couple committee chairs also participated. Only the participants' broad areas of expertise are included to protect their identities. Interview 1001 Population Geneticist. Interview 1003 Site Project Manager. Interview 1006 Microbiologist. Interview 1011 Bioethicist. Interview 1014 Human Geneticist. Interview 1016 Population Geneticist. Interview 1017 Bioethicist. Interview 1022 Geneticist and Bioethicist. Acknowledgements. Some passages of this chapter first appeared as The Informationalization of Race, Communication Technologies and the Human Genome in the Digital Age, 2008, in the International Journal of Communication. 7. Forensic DNA Phenotyping. Continuity and Change in the History of Race, Genetics, and Policing. Pamela Sankar. At the 2004 Forensic Bioinformatics Conference in Ohio, a speaker announced that a new software program, DNA Witness, had triggered the start of the revolution in forensics. One ushering in the new era would be the program's capability to decipher an individual's race from crime scene DNA. Based on analysis of the heritable component of race, referred to as biogeographical ancestry, the program would produce a precise estimation of the percentages of different types of ancestry present in the DNA sample, including Indo-European, Sub-Saharan African, East Asian, or Native American and, using these estimates, produce a description of a person's appearance that police could use to narrow down a pool of suspects. While DNA Witness and its parent company DNA Print have not had the success they hoped for, the genetic technology on which the program relies, referred to broadly as forensic DNA phenotyping, FDP, has continued to develop in Europe as well as in the United States. 2. In addition to analysis of genetic ancestry, DNA Print and other companies are working to identify genotypes associated with gait, voice, and predisposition to behavioral traits such as smoking or to medical conditions such as diabetes. FDP technology, should it come into general use, would fundamentally transform the existing function of DNA in law enforcement, limited now to confirming a suspect's identity. FDP efforts to find genetic markers that are associated with physical appearance seek to get past this limit and bring the power of DNA to the antecedent task of predicting who the suspect will be. Law enforcement refers to the capacity to produce information rather than only confirm it as using DNA for intelligence purposes. 3. Unlike DNA typing, there are no accepted standards for procedures or calculations to anchor the results produced by FDP analysis. The few published examples of FDP-based descriptions, such as largely West African for or alike. Forensic DNA phenotyping 105. Skinned black, 5 are notably vague and presumably would require police to rely on implicit stereotypes in order to apply them. Still, FDP has succeeded in effectively redirecting investigations by shifting police attention from suspects in one racial grouping to those in another. 6. It is important to examine these outcomes and consider what they mean relative to the broader claims of FDP. FDP's premise that phenotype is predictable from genotype draws attention to the disjuncture between the relative specificity and measurability of genotype and the more continuous nature of phenotypes, which makes them difficult to categorize and describe. The challenges encountered in moving from genotype to phenotype, absent only in a handful of single gene disorders, are not new. But because FDP operates in law enforcement, these challenges raise issues that go beyond the problems raised in medical genetics. In light of persistent, well-documented racial biases in arrest, conviction, and incarceration rates in the United States, the technology's focus on predicting a suspect's race is particularly worrisome. 7 potential social and ethical drawbacks of FDP have not been widely discussed by the technology's proponents, but some have spoken to these issues. One presentation, for example, cited possible demands to use the technology inappropriately, such as for pre-implantation diagnosis, 8, while another conceded that racial stereotyping concerns might be plausible. 9 left unaddressed, however, is the issue of what it means practically for police to be able to claim to be able to predict a suspect's appearance based on a heritable component of race. 10 In this essay I examine and refute claims that FDP can reliably predict race and, on this basis, appearance. The failure lies less in the basic thrust of the claim, however, than many might suppose. In other words, there are demonstrable relationships between certain genetic markers and a person's self-identified race and, under specific research conditions, such as using a limited number of self-identified races from which subjects can choose, self-identified race roughly corresponds to observer-assigned race. The problem lies instead with the practical details entailed in the series of claims or steps that FDP requires, starting with the predictability of phenotype from genotype and continuing on to the idea that phenotype can be objectively described and understood in such a way that police can use it to routinely and reliably distinguish who might and who might not be a suspect in a particular crime. Arguably the most troubling step in the series is the final one, presuming that police can effectively interpret and judiciously apply a description such as light-skinned black man. 11 This is not because police are somehow less skilled or less trustworthy as a group. It is rather that the nature of their training and demands of their job work against effective use of such information. Furthermore, there are substantial problems with the steps prior to police actually applying FDP descriptions, including the nature of genetic markers that FDP uses and its reliance on individual inferences from population-level data, that argue strongly against allowing the technology to get that far. Pamela Sankar 106. FDP accounts. There are few publicly available detailed accounts of police reliance on FDP. Indeed, it is even difficult to get a realistic estimate of how often police have used it. In 2007, DNA Print claimed that it had provided FDP analysis in over 200 cases since 2003, but the basis for the claim is unstated. 12 Nonetheless, by reviewing 2 cases that have been reported in depth by the media, we can get some sense of the circumstances in which FDP has been used and its results. The first is DNAprint's first case reported in the United States, which also appears to be one of the few that has resulted directly in arrest and conviction. The second is an ongoing case in southeastern England of a serial rapist, dubbed the Night Stalker. The U.S. case concerns a serial murderer-rapist in southern Louisiana, believed active for more than a decade. Despite repeated audacious daylight attacks, the suspect left few eyewitness accounts. Based on what evidence they could gather, police believed they were seeking a white man in a white van. As the murders continued, police grew frustrated with their lack of success in zeroing in on a suspect and began to contact various outside agencies for help. Eventually they got in touch with DNA Print and arranged for an FDP analysis of DNA retrieved from one of the murders. 13 To guard against potential bias, the Louisiana State Police Crime Lab sent to DNA Print DNA from 20 people whose race they had independently determined, along with DNA from the crime scene. Less than 2 weeks later, DNA Print returned racial descriptions for all 21 samples. Those based on the known samples were judged accurate. The description returned for the perpetrator surprised investigators. FDP analysis suggested that the sample belonged to someone whose ancestry was 85% sub-Saharan African and 15% Native American and who most likely was a lighter-skinned black man. 14. This finding forced the police to reconsider evidence they had previously dismissed as unrelated to the case and pointed the investigation in a new direction that led to the capture of Derek Todd Lee, an African American. In 2004, Lee was convicted of 2 murders and DNA evidence linked him to at least 5 more. He was sentenced to death and awaits execution. The British Night Stalker case is similar to the Lee case in that the suspect has succeeded in making repeated attacks while evading capture and escaping observation by potential eyewitnesses. The brutal sexual and physical assaults, largely against older women, have spanned nearly 20 years. Similarly frustrated with their lack of progress, British police decided to try Dinaprint's services. They too submitted multiple samples as a guard against potential bias influencing the analysis of the perpetrator's sample. The finding they were given suggested that the likely suspect had strands of DNA that were Native American, European, and Sub-Saharan African. 15. A detective chief inspector from the investigation concluded that this meant the offender probably came from the Caribbean, most likely an island that was a former British colony. He went on to say that further tests could be done to break down the rapist's biological code so precisely that he could be linked to a particular Caribbean island. 16. Efforts to more precisely identify the perpetrator's ancestral home led police officials to seek DNA samples from several hundred of their own officers of Caribbean descent, a request that many refused and that led to considerable controversy among members of London's Metropolitan Black Police Association. 17. Additional analysis conducted by a government scientist reported that the perpetrator was from the Windward Islands, specifically Trinidad. 18. Eventually a team of police officials actually travelled to Trinidad and gathered DNA samples from willing inhabitants. Upon hearing how the British police had interpreted his company's report, the technical director of DNA Print took issue with their claims, stating, "That's not what our test indicated." As he elaborated, although broad ethnic ancestry can be determined from DNA, geneticists cannot say with any certainty that an individual comes from a specific country. 19. The suspect remains at large and attacks attributed to him continue to be reported. Ancestry informative markers. Both of these FDP cases and the handful of others publicly reported 20 rely on analysis of ancestry informative markers, AIMs, which are a particular category of genes distinguished by having several polymorphisms that exhibit substantially different frequencies between races. 21. The existence and basis of such genes, or alleles, was demonstrated in admixture mapping research well before their use in these cases, but it is testament to the evolving interest in race and genetics that they are now called ancestry informative. 22. The reasoning behind using AIMs to produce race-based identifications is a bit circular, but important to understand. AIMs can be used to distinguish races because AIMs vary by race. The circularity goes to the heart of complaints about FDP, but does not in itself entirely invalidate claims about using FDP to identify a person's race. It does, however, suggest that these claims do not pass muster for use in law enforcement. The basis for treating a particular set of alleles as ancestry informative lies in the link between human genetic variation and population migration. Changes in the human genome that result from mutations, natural selection, or genetic drift are shared and spread through reproduction, which requires contact. As populations fanned out from Africa 40,000 years ago to inhabit the globe, those who traveled the greatest distances from one another had less contact and were less likely to share genetic changes passed down through reproduction. Those who lived closer to one another were more likely to have contact and to share changes. 23. As a result, certain genes or alleles are more common among people whose ancestors come from the same geographic region. Such alleles are rarely wholly absent in other groups, and rarely universal within groups where they do. Forensic DNA Phenotyping 107. Pamela Sankar 108. Appear. It is, rather, that statistically they appear more often in some groups than in others. For some researchers these findings justify claiming that race has a genetic basis. 24. Some, among them FDP proponents, go a step further and claim that some of the alleles found to vary in this way are expressed phenotypically in a person's physical appearance in a way that predictably conforms to socially constructed categories of race. While there are certain practical and logical bases to these assumptions, there are also several mistakes that are particularly pertinent to understanding what is at stake if FDP were introduced into routine policing in the United States. First, not all alleles that might appear to be AIMs actually are. Alleles that vary across geographic regions might also have developed in relation to similar environmental exposures as some alleles related to malaria resistance appear to have. As a result, a shared allele might reflect similar environmental exposures on the part of ancestors, but not shared ancestry. 25. Second, the presence or absence of a particular allele in a person's DNA in itself does not necessarily indicate something about the person's ancestry. This is because findings that show geographic or continental variation in alleles are probabilistic. They exist at a certain frequency within a population. While research has repeatedly demonstrated that certain alleles are more common in certain populations, it provides no basis on which to predict whether any particular individual in that population will or will not have a certain allele. Further, research has shown that the predictability of the link between a particular allele and self-assigned race is even more likely to be wrong among individuals from admixed populations, meaning that their family history draws from two or more ancestral populations. 26. Third, even people who do share aims that are known to influence physical appearance do not necessarily look the same. Gene expression depends on complex interactions with the environment, broadly construed, and the potential for similar phenotypic expression made possible by shared alleles is not always realized. And just as significant, to the extent that it is realized, insufficient research exists to provide a basis for accurate prediction of physical appearance based on genotype. For these reasons, although there is a relationship between aims and popular categories of race, it is neither predictable nor robust. Further, none of this speaks to the challenge of translating racial designations, whatever their basis, into verbal descriptions of personal appearance that could be useful in police work. There are no standards for classifying or recognizing a person as light-skinned or as having dark eyes. This review of aims helps to clarify certain things about the Louisiana and British FDP cases. First, it explains why FDP might work. In the Louisiana case, FDP analysts indicated that the suspect was a light-skinned black man. This statement surprised investigators who had been led by witnesses to look for a white man in a white van. Investigators redirected their inquiry, reconsidered information they had collected but thought irrelevant, and realized that an African American man associated with another case fit the profile for this case. Police arrested this man and found that his DNA matched crime scene samples. However, FDP's success in Louisiana doesn't mean that it will work elsewhere, nor does it even help to predict how often or in what cases it might prove useful. The results might just as easily have led officials to ignore the real suspect if they judged him too light or too dark to qualify as a light-skinned black man. Misapplied, the results might also have led to the arrests of innocent men. Proponents argue that concerns about misidentification based on FDP are unimportant, because the technology is used only to identify, not to prosecute, a suspect. 27. If the arrestee's DNA turns out not to match the crime scene DNA, the police simply release the person. While logically true, this is scarcely reassuring to people under arrest, especially members of racial or ethnic minorities who, according to a U.S.-based study, are approximately 5 times more likely than white suspects, per capita, to die at the hands of a police officer. 28. Little information about mistaken arrests in Britain's Night Stalker case is available, so it is difficult to judge the potential for damage there. However, there is information about how FDP information has shaped the investigation in other ways. The Night Stalker case. A comprehensive review of the Night Stalker case conducted by the British government in 2006 states that the police used the FDP analysis to reprioritize the inquiry, to avoid questioning those uninvolved, and instead to approach relevant individuals. 29. While this use mirrors the stated purpose of FDP, exactly how the reprioritizing unfolded bears scrutiny. It was not, as one might suppose, based on FDP proponents' claims about the predictability of physical characteristics putatively associated with FDP-identified ancestry. It seems, rather, that FDP analysis provided police in the Night Stalker case with a stereotype onto which they could project social information. For example, police statements located the perpetrator's ancestors historically, stating that they originate from Slavi trade Africa, 30 and politically, as having at some point resided in Trinidad. Another police statement claimed that both of the perpetrator's parents must have originated from the Caribbean area. 31 Police also used the FDP analysis to make assumptions about the perpetrator's current life and to justify concentrating their inquiries in London neighbourhoods that the police recognised as having a high number of Caribbean-identified residents. 32 In light of the complex and lengthy relationship between Great Britain and the Caribbean, dating to the early 1600s, the move from a handful of aims to a particular 21st-century London neighbourhood is a leap. The assumption that there will be some visible or publicly knowable contemporary manifestation of this person's putative heritage is difficult to justify. Yet despite their apparent failure to produce a suspect, it would seem that police have continued to rely on such assumptions. Incidents attributed to the Night Stalker in June and October 2008 suggest that he remains as active as ever. 33 The June incident led to the release of the first forensic DNA phenotyping 109. Police artist's sketch of the perpetrator, itself a major breakthrough in the case, accompanied by the statement, the victim saw the suspect in dark conditions but states he is a light-skinned black man, with markings on the side of his face. These could be a number of things such as freckles, scarring, or spots. 34 The sketch, Figure 1, occasioned some comment about the likely racial identity of the person depicted, with one citizen querying, why does the photo fit not look like a black man when the offender is, surely sick? This is misleading. 35 Whether this image, downloaded from the web, accurately reproduces the original police sketch is unclear, both to me and to at least some of the people commenting on it in related blogs. Assuming for the moment that it is accurate, one question of concern to the elderly women and the population of southeastern England at large is whether the sketch resembles the perpetrator sufficiently to facilitate his capture. A rather different question of interest here is what relationship the sketch bears to mental images of the suspect the police have relied on for the last 4 years. The person depicted in the sketch could well trace his ancestry to the Caribbean, but, if so, he apparently would not match the stereotype at least some people have of what a person with Caribbean descent looks like. 36 Of course this begs the questions, what is a person of Caribbean descent supposed to look like? Or, using Dinaprint's language, what is a person with strands of DNA described as Native American, European and Sub-Saharan African supposed to look like? 37 And more to the point, what does the Night Stalker, with his unique personal history, look like? Pamela Sankar 110. Figure 1 Police artist sketch of British serial rapist, dubbed the Night Stalker. The sketch was accompanied by the statement that the subject was probably a light-skinned black man, a description that some observers thought was at odds with the image. London Metropolitan Police, UK/PAWire, Press Association via AP Images. Perhaps the Night Stalker's capture will settle some of these questions. But it is not clear if it will matter then, as the point of FDP is to help predict a suspect's identity, not to confirm it after he is caught. It is possible, of course, that the police know more than they let on and that the public presentation of the inquiry is strategically misleading. Regardless, the point stands. The exact relationship between aims and ancestry for a specific person cannot be stated any more than can the relationship between aims and that person's appearance. And even if such a prediction could be made more precise, the interpretation of the description still eludes standardization. Would most people have recognized the person in the sketch as a light-skinned black man, or as someone with a Caribbean background, or whose parents are from Trinidad? Specifically, would the police or potential witnesses have recognized him as such? It is not that there is no relation between aims and popular race categories, which is why the simple criticism that race is a social not a genetic construct does not suffice against FDP. It is rather that the relationship is based on the frequency and probability of certain historic events in a population. Evidence of these events is predictable at the population level, but not for any one person. And while this point relates most directly to assertions made about the basic premise that aims link predictably to ancestry, it also provides a needed caution for all of the steps implied by FDP use in law enforcement, including that ancestry links to appearance and that appearance described by one person is understood by another as pertaining to the same person. And this caution is that, while any of these predictions or inferences might sometimes work, as they did in the Todd case, they often will not. And at this stage there is no way of knowing which prediction is which. The magnitude of uncertainty underlying FDP predictions suggests that it is unsuitable for its proposed use in law enforcement. 8. Forensic DNA and the inertial power of race in American legal practice. Jonathan Kahn. Race, Genes, and Justice. The time has come to ask how and when, if ever, is it appropriate to use race in the presentation of forensic DNA evidence in a court of law. Recently much attention has been devoted to some of the ethical, legal, and social issues presented by the emerging use of DNA typing to produce phenotypic profiles of crime suspects based on DNA samples found at the scene of a crime. Of particular concern is the growing tendency to use so-called ancestry informative markers, AIMs, to predict a suspect's race or ethnicity. While important and well-deserving of such concern, these discussions largely overlook the conceptually distinct and far more prevalent, indeed standard, use of race in the development and presentation of forensic DNA evidence in criminal trials. In contrast to DNA profiling, which is used to try to identify a suspect, DNA evidence is presented at a trial to try to convict a suspect who has already been apprehended. DNA presented as forensic evidence in a trial tries to establish a match between DNA found at a crime scene and DNA obtained from an apprehended suspect. This match is based on finding an identity across 13 genetic loci, which, in contrast to AIMs, were explicitly chosen for their purported lack of any connection to phenotypic traits. In this context, race is used to help calculate odds regarding the probability that the same DNA profile might match a random individual in the population other than the suspect. One might say that, in such calculations, race is used to generate odds, whereas in DNA profiling odds are used to generate race. Forensic experts have framed DNA evidence in terms of race almost since its inception in the late 1980s. The original justifications for using race involved efforts to refine the accuracy of the evidence. Early applications of forensic DNA generally typed individuals at only 4 distinct loci and then used statistical methods to generate probabilities that a match between 2 samples actually implicated the defendant. In order to refine the odds, forensic experts generated tables calculating the frequencies of each allele in diverse ethnic or racial. 115. Population groups. The idea here was that groups sharing distinct ancestries would have distinct frequencies of these highly variable alleles. Using these racially identified population databases would, it was believed, provide more accurate odds that the DNA found at the crime scene did, in fact, come from the defendant. Many assumptions about the utility and appropriate use of race were questioned early on, but the use of race in forensic DNA analysis soon became normative. Hence race was injected into the science and law of forensic DNA from its outset. Subsequent technological developments greatly enhancing the discriminating power of DNA analysis have largely rendered such concerns moot. As a practical matter, race now adds no relevant refinement to the odds that a match implicates a defendant. Yet the practice of using race persists. It has become commonplace, even standard, in the generation and presentation of DNA evidence to juries. The recent and representative California case of People v. Wilson, too, clearly illustrates the point. In that case, the prosecution presented the following race-specific probabilities that the DNA at the crime scene would have come from someone other than the defendant: Caucasian 1 in 96 billion, Hispanic 1 in 180 billion, and African Americans 1 in 340 billion. One might well ask, if there are only 6.5 to 7 billion people in the whole world, what can possibly be gained from presenting odds of a random match that differentiate among Caucasians, Hispanics, and African Americans, when those odds range from 1 in 96 billion to 1 in 340 billion? Given such a range, it is clear that the prosecution could have produced probabilities with astronomically high denominators without any reference to race. Any loss of precision occasioned by the use of probabilities for a non-racialized general population would have been forensically inconsequential. The question then becomes, why has the use of race persisted long past the time when technological advancement obviated the questionable need to use it? Part 2 of this essay will provide some background to the history and technical aspects of both forensic DNA analysis and the debates regarding the relation between race and genetics. It will begin by introducing some of the basic technical details of early forensic DNA practices and procedures. It will also examine early debates over the appropriate use of racial categories in generating statistical match probabilities. In the early years of forensic DNA analysis, the late 1980s and early 1990s, these debates did not involve questions of whether to use race, but rather how much race to use. The concern of some early forensic DNA analysts was that using too broad a population group would generate random match probabilities or RMPs that were unfairly low. Advocates of using broad racial categories argued that they provided a pragmatic and useful means to generate more accurate statistics than using an undifferentiated general population database, while still providing RMPs that were fair to a defendant. Critics of this approach argued that since there is more genetic variation within racial groups than between them, databases should be characterized by smaller subgroups within the larger racial 116 designation, in order to provide even better information about RMPs. This part of the article will also consider how these arguments relate to broader issues concerning the nature of race in relation to genetics. It moves from these early debates to current scientific opinion regarding the propriety, or lack thereof, of using racial categories in relation to genetic research and practice. This section then concludes by moving back to the mid-1990s to examine how the debates over using race to calculate RMPs were ultimately resolved in favor of using broad racial categories, which then became the norm for forensic DNA practice in the United States. Part 3 will examine the current standards and protocols for conducting forensic DNA analysis and consider how, where, and when forensic experts inject race into their practices. This section begins with an examination of DNA databases, focusing on the FBI's Combined DNA Index System, CODIS, which began as a pilot project in 1990 and has since evolved into a major database, with over 5 million DNA profiles from convicted offenders nationwide. It reviews technological developments that have greatly increased the power and efficiency of forensic DNA analysis, and considers the selection of 13 genetic loci that have become the standard for generating DNA matches and calculating random match probabilities. Part 4 contrasts the elaboration and standardization of such technical protocols for DNA analysis with the protocols, or lack thereof, for producing and using racial and ethnic categories in forensic DNA analysis. Here I argue that the use of racial categories is woefully underconceptualized and wholly inadequate, especially when contrasted with the great care taken to elaborate the technical protocols of DNA analysis itself. I argue that similar care of the data should be given to methods for using racial categories in a genetic context. I put forward the use of general, non-racial reference population databases as the obvious solution to this problem. This section moves on to examine what I call the inertial power of race to remain in a system of practice and analysis long after the initial reasons for using it have faded. It considers, as well, some of the dangers, beyond the courtroom, of allowing race to persist in a context that inappropriately reifies it as genetic. The essay concludes with a brief review of the basic arguments for why there is no longer a place for race in the generation or presentation of forensic DNA evidence in criminal trial proceedings. 2. Race and the early development of forensic DNA. Origins of forensic DNA testing. DNA is made up sequences of 4 nucleotides, adenine, cytosine, guanine, and thymine, commonly represented as A, C, G, and T. Each nucleotide base is paired through a process known as hybridization. A is always paired with T, C is always paired with G. There are approximately 3 billion of these base pairs in the human genome. Butler 2005, 23, 1820 and 18. There are two major steps in using DNA for purposes of forensic identification. First, a sample left at the crime scene by the perpetrator is compared to a sample from a suspect. Second, if there is a match, then statistics must be used to calculate the frequency of that DNA profile in an appropriate reference population, K 1993, 101-104. This latter step is required because, although every person's DNA is unique, it is impractical to compare the full 3 billion nucleotide base pairs between two samples for forensic purposes. Therefore, two samples will be compared only at a limited set, usually between 4 and 13, of loci, or specific parts of the genome. For this practice to be effective, it is necessary to find loci that are highly variable between individuals and test only for them. Humans, however, are essentially identical in about 99.5% of their DNA. 3. Finding the specific points of variation among individuals, therefore, can be difficult. In 1985, English geneticist Alec Jeffreys first described a method for developing a DNA profile of a person in a manner that might be used for purposes of forensic identification. Butler 2005, 23. See also National Commission on the Future of DNA Evidence 2002, 14-15. Jeffreys's innovation consisted of observing that, in particular regions of the human genome, short segments of DNA, the ACGT nucleotide sequence, are repeated between 20 to 100 times. Butler 2005, 23 and 18, Wawonti and Hartle 1991, 1745. These repeat regions became known as variable number of tandem repeats, or VNTRs. Different VNTR alleles or variations are composed of different numbers of repeats. In order to examine and visualize the VNTRs, Jeffreys employed a technique known as restriction fragment length polymorphism, RFLP, which uses a restriction enzyme to cut the regions of DNA surrounding the VNTR. Butler 2005, 23 and 8. By looking at VNTRs from several distinct loci on the genome, it is possible to calculate the probability that a particular genetic profile comprised of distinct sets of VNTRs will appear in one or more individuals in a particular population. A standard way to estimate the frequency of a particular profile is to count occurrences in a random sample of an appropriate reference population and then use classical statistical formulas to place upper and lower confidence limits on the evidence. National Research Council 1992, 10. The resulting conclusion of identity or non-identity between two samples is therefore necessarily probabilistic. Wawonton and Hartle 1991, 1745-1746 N. Cho and Sankar 2004 S8, S9. In conducting the comparison, investigators came to adopt the product rule 4 for determining the random match probability, RMP, the probability of finding the same DNA profile identified in the crime scene sample in a randomly selected, unrelated individual. Butler 2005, 481 N18, Wawonton and Hartle 1991, 1745 N21. 5. Any given VNTR may be calculated to occur at a certain frequency in a random population. By the early 1990s, the standard was to test for VNTRs at 4 independent loci on the genome. The product rule allows for multiplying each independent genotype frequency together to produce an overall probability of a match at all 4 loci. Wawonton and Hartle 1991, 1746 N. 117. 118. Jeffreys's innovation was first used in a forensic setting in England in 1986, Butler 2005, 3N18. Forensic DNA testing was first used in the United States in 1987, McClin 2006, 163. Soon thereafter some commercial laboratories made use of this fingerprinting procedure, and in 1988 the U.S. Federal Bureau of Investigation implemented forensic DNA techniques, National Commission on the Future of DNA Evidence 2002, 14, 15 and 18. Critical to the acceptance of forensic DNA in courts was the development of standards of technical proficiency and accuracy in generating RMPs. The product rule was one such standard, requiring that each chosen loci be understood as being inherited independently of the others. Also important were basic crime scene management techniques for the identification and handling of DNA samples. 6. Early questions and challenges. Questions about the reliability of DNA evidence surfaced as early as 1989, in cases such as People v. Castro 7 in New York and the Minnesota case of Schwartz v. State. 8. Partially in response to these cases, several federal agencies called upon the National Research Council, NRC, an arm of the National Academies of Science, NAS, to study and recommend guidelines for the production and use of DNA evidence, Jezinoff 2004, 339, 340 and 30. The NRC created a Committee on DNA Technology in Forensic Science, which issued a report in 1992. It is in the context of the production of this report that race first enters the story front and center. The committee covered an array of issues relating to the forensic use of DNA technologies. Among its most controversial findings were those relating to reference populations and the appropriate methodology for calculating RMPs. In order to calculate the odds of any particular VNTR allele appearing at a given locus on the genome, one must have an appropriate reference population. The product rule depends on the assumption of statistical independence of the alleles tested, that is, that they do not tend to occur in groups. National Research Council 1992, 12. Generally speaking, the more related a person is to a particular population group, the higher odds are of finding shared alleles or, alternatively stated, the less independence there is among alleles. Siblings would likely share more DNA than cousins, cousins more than others in the same isolated village, members of the same isolated village more than others in the same region, and so forth. Higher odds favor a suspect or defendant because they indicate a greater likelihood that some other person may have left the DNA sample found at a particular crime scene. The choice of reference population, therefore, can play a critical role in shaping the weight and authority of DNA evidence. The choice, however, is not always straightforward. Indeed, some of the earliest and most contentious controversies involving the use of DNA technology in forensic science involved choosing the appropriate population against which a suspect's DNA should be compared and defining just how the suspect may be related to this population. See, generally, Butler 2005, 455-519. Concepts of race played a central role in these debates, and continue to frame the way forensic scientists, law enforcement, and the bar produce and interpret DNA evidence to this day. The basic issue is whether or to what extent racial or ethnic categories should be used to characterize reference populations against which particular DNA samples could be compared in order to generate RMPs. The use of such categories may be particularly problematic in the arena of forensic DNA analysis because racial groups, especially those delineated in the U.S. Census, are fundamentally social, not biological categories. 9. Indeed, at least since the 1970s, scientists have understood that race will statistically explain only a small portion of genetic variations, won't in 1972, 381. As an editorial in Nature Genetics put it, scientists have long been saying that at the genetic level there is more variation between two individuals in the same population than between populations, and that there is no biological basis for race. Editorial 2001, 239. Nonetheless, to the extent that certain population geneticists understand particular racial groups as sharing a common genetic ancestry, usually by using race as a crude surrogate for geographic or continental ancestry, members of those groups can be viewed as more related to each other, like an extended family, than to individuals from other groups. This problematic understanding of relatedness can then affect the calculation of RMPs. Generally speaking, the more fine-grained the characterization of a particular reference population, the higher the odds of a random match. Again, higher odds favoring the suspect/defendant. In the early years of forensic DNA analysis, there were concerns that using a general, undifferentiated population database would produce inappropriately low RMPs. The decision to use race in constructing and categorizing reference populations was introduced into forensic DNA analysis in belief that it would improve the precision of the calculations that generate RMPs, Cho and Sankar 2004 S9. In early 1991, two pairs of eminent population geneticists squared off against each other in the Pages of Science, a highly influential scientific journal, to debate the problem of using racial categories in forensic DNA analysis. On one side were professors Richard Lewontin of Harvard University and Daniel Hartle of the University of Washington, described by an editorial accompanying the article as two of the leading lights of population genetics. Roberts 1991, 1721. On the other side were Ranajit Chakraborty of the University of Texas and Kenneth Kidd of Yale University. Their dispute did not revolve around the question of whether to use race but rather how much race to use in constructing reference population databases from which to calculate match probabilities. Lewontin and Hartle questioned the then current practice of calculating allele frequencies in the racial categories used in the census such as Caucasian, Black, or Hispanic to provide the basis for calculating RMPs. Lewontin and Hartle 1991, 1747n. They argued that such groupings were too broad, and that substantial genetic substructuring occurred within the broad racial groupings that should be taken into account in calculating match probabilities. Using the broad racial groupings could produce RMPs with substantially lower odds than those 119. That might be produced using more fine-grained ethnically identified subpopulations, IBID. These concerns grew logically out of Lewontin's earlier path-breaking work showing how genetic variation within socially identified racial groupings was actually greater than variation observed between such groups. Lewontin 1972, 381. This work laid the foundations for understanding that race was incoherent as a genetic concept, or at best, an overly crude surrogate for genetic variation that improperly tended to reify race as genetic. 10. Thus Lewontin and Hartle observed. Among genes that are polymorphic in European national or ethnic groups, the magnitude of the differences in allele frequency among subpopulations differs from one gene to the next. For example, there are striking geographical clines of allele frequency across Europe for the ABO blood groups. The frequency of the B allele is 5 to 10% in Britain and Ireland, increases across Eastern Europe, and reaches 25 to 30% in the Soviet Union. The frequency of the O allele is 70 to 80% in Sardinians, Irish, and Scottish populations, but lower in Eastern European populations. These clines reflect the migrations and political history of Europe over the last few thousand years. Lewontin and Hartle 1991, 1748n. Problems were even greater for the heterogeneous assemblage known as Hispanic, which was perhaps the worst case for calculating reliable probabilities, IBID, 1749. Consequently, they concluded that using reference databases organized by the broad racial groupings Caucasian, Black, and Hispanic was unjustified, IBID, 1747. Chakraborty and Kidd argued that Lewontin and Hartle exaggerated both the extent of ethnic substructuring in America and its significance for calculating match probabilities. Chakraborty and Kidd 1991, 1735. While conceding that some substructuring existed, they argued that its effects upon frequency estimates generated by using the broader racial databases was trivial. Chakraborty and Kidd did not deny that using finer-grained ethnic reference populations might produce more precise allele frequency estimates. Rather, their point was that such an approach was unnecessary and unnecessarily burdensome. Current technology and understandings of population genetics, they asserted, justified the use of broad racial and ethnic categories, which were, additionally, far more practical and currently available, IBID. Race was at the center of this early debate. But, again, for these eminent scientists, it was not a question of whether to use race but how, or more specifically how much, that is, how fine-grained, race to use. This debate took place while the NRC committee was conducting its study of DNA technology in forensic science. Its report, issued in 1992, discussed both sides of the issue without specifically taking sides. It did, however, choose to assume for the sake of discussion that population substructure may exist and to provide a method for estimating population frequencies in a manner that may account for it. National Research Council 2002, 13. The report recognized that population 120 genetic studies show some substructure within racial groups for genetic variants. Thus, North American Caucasians, Blacks, Hispanics, Asians, and Native Americans are not homogeneous groups, IBID, 80. In effect, this approach reflected the concerns expressed by Lewontin and Hartle, recognizing that social categories of race did not map neatly onto discrete genetically definable population groups.